A scuba diver is underwater near the wreck of a ship. Directly adjacent to the diver is a large gun with coral or sea plants growing on it. Whether they think about it in mathematical terms or not, scuba divers must consider the impact of functional relationships in order to remain safe. The gas laws, which are a series of relations and equations that describe the behavior of most gases, play a core role in diving. This diver, near the wreck of a World War II Japanese ocean liner turned troop transport, must remain attentive to gas laws during their dive and as they ascend to the surface. Credit, Eikoku Aft Gun, modification of work by Monterediver/Flickr. Chapter outline 5.1 Quadratic functions, 5.2 Power functions, and polynomial functions 5. 3 Graphs of polynomial functions 5. 4 Dividing polynomials 5. 5 Zeros of polynomial functions 5. 6 Rational functions 5 7 Inverses and radical functions 5 8 Modeling. Using variation, you don't need to dive very deep to feel the effects of pressure. As a person in their neighborhood pool moves 8, 10, 12 feet down, they often feel pain in their ears as a result of water and air pressure differentials. Pressure plays a much greater role at ocean diving depths. Scuba and free divers are constantly negotiating the effects of pressure in order to experience enjoyable, safe, and productive dive ease. Gases in a person's respiratory system and diving apparatus interact according to certain physical properties, which upon discovery and evaluation are collectively known as the gas laws. Some are conceptually simple, such as the inverse relationship regarding pressure and volume, and others are more complex. While their formulas seem more straightforward than many you will encounter in this chapter, the gas laws are generally polynomial expressions. Learning objectives in this section, you will recognize characteristics of parabolas. Understand how the graph of a parabola is related to its quadratic function. Determine a quadratic function's minimum or maximum value. Solve problems involving a quadratic function's minimum or maximum value. Satellite dishes. Figure 1 An array of satellite dishes. Credit, Matthew Colvin Duval. Flickr curved antennas, such as the ones shown in Figure 1, are commonly used to focus microwaves and radio waves to transmit television and telephone signals, as well as satellite and spacecraft communication. The cross-section of the antenna is in the shape of a parabola, which can be described by a quadratic function. In this section, we will investigate quadratic functions, which frequently model problems involving area and projectile motion. Working with quadratic functions can be less complex than working with higher-degree functions, so they provide a good opportunity for a detailed study of function behavior. Recognizing characteristics of parabolas, the graph of a quadratic function is a U-shaped curve called a parabola. One important feature of the graph is that it has an extreme point, called the vertex. If the parabola opens up, the vertex represents the lowest point on the graph, or the minimum value of the quadratic function. If the parabola opens down, the vertex represents the highest point on the graph, or the maximum value. In either case, the vertex is a turning point on the graph. The graph is also symmetric with a vertical line drawn through the vertex, called the axis of symmetry. These features are illustrated in Figure 2. Graph of a parabola showing where the x and y intercepts, vertex, and axis of symmetry are. Figure 2, the y-intercept is the point at which the parabola crosses the y-axis. The x-intercepts are the points at which the parabola crosses the x-axis. If they exist, the x-intercepts represent the zeros, or roots, of the quadratic function, the values of x at which letter 1d466 equals 0. Example 1, identifying the characteristics of a parabola determine the vertex, axis of symmetry, zeros, and y-intercept of the parabola shown in Figure 3. Graph of a parabola with a vertex at 3, 1, and a y-intercept at 0, 7. Figure 3 solution. The vertex is the turning point of the graph. We can see that the vertex is at 31. Because this parabola opens upward, the axis of symmetry is the vertical line that intersects the parabola at the vertex. So the axis of symmetry is. This parabola does not cross the x-axis, so it has no zeros. It crosses the y-axis at 7, so this is the y-intercept. Understanding how the graphs of parabolas are related to their quadratic functions, the general form of a quadratic function, presents the function in the form letter 1d453. Letter 1d465 equals letter 1d44 letter 1d465, 2 plus letter 1d44f letter 1d465 plus letter 1d450, where a, b, and c are real numbers and letter 1d44 not equal to 0. If letter 1d44 is 0, the parabola opens upward. If letter 1d44 is 0, the parabola opens downward. We can use the general form of a parabola to find the equation for the axis of symmetry. The axis of symmetry is defined by, if we use the quadratic formula, letter 1d465 equals minus letter 1d44f, plus or minus letter 1d44f, 2 minus 4 letter 1d44 letter 1d450, square, root 2 letter 1d44. To solve letter 1d44 letter 1d465, 2 plus letter 1d44f letter 1d465 plus letter 1d450 equals 0 for the x-intercepts, or zeros. We find the value of x halfway between them is always letter 1d465 equals minus letter 1d44f2a. The equation for the axis of symmetry. Figure 4 represents the graph of the quadratic function written in general form as letter 1d466 equals letter 1d4652 plus 4 letter 1d465 plus 3. In this form, letter 1d44 equals 1, letter 1d44f equals 4, and letter 1d450 equals 3. Because letter 1d44 is 0, the parabola opens upward. The axis of symmetry is letter 1d465 equals minus 42, 1 equals minus 2. This also makes sense because we can see from the graph that the vertical line letter 1d465 equals minus 2 divides the graph in half. The vertex always occurs along the axis of symmetry. For a parabola that opens upward, the vertex occurs at the lowest point on the graph, in this instance, minus 2, minus 1. The x-intercepts, those points where the parabola crosses the x-axis, occur at minus 3, 0, and minus 1, 0. Graph of a parabola showing where the x and y-intercepts, vertex, and axis of symmetry are for the function y equals x2 plus 4x plus 3. Figure 4, the standard form of a quadratic function, presents the function in the form letter 1d453. Letter 1d465 equals letter 1d44, letter 1d465 minus letter 210e2 plus letter 1d458, where hk is the vertex. Because the vertex appears in the standard form of the quadratic function, this form is also known as the vertex form of a quadratic function. As with the general form, if letter 1d44 is 0, the parabola opens upward and the vertex is a minimum. If letter 1d44 is 0, the parabola opens downward and the vertex is a maximum. Figure 5 represents the graph of the quadratic function written in standard form as letter 1d466 equals minus 3, letter 1d465 plus 2, 2 plus 4. Since letter 1d465 letter 210e equals letter 1d465 plus 2 in this example, letter 210e equals 2. In this form, letter 1d44e equals minus 3, letter 210e equals minus 2, and letter 1d458 equals 4. Because letter 1d44 is 0, the parabola opens downward. The vertex is at minus 2, 4. Graph of a parabola showing where the x and y-intercepts, vertex, and axis of symmetry are for the function y equals 3, x plus 2, 2 plus 4. Figure 5, the standard form is useful for determining how the graph is transformed from the graph of letter 1d466 equals letter 1d4652. Figure 6 is the graph of this basic function. Graph of y equals x2. Figure 6, if letter 1d4580, the graph shifts upward, whereas if letter 1d4580, the graph shifts downward. In figure 5, letter 1d4580, so the graph is shifted 4 units upward. If letter 210 is 0, the graph shifts toward the right, and if letter 210 is 0, the graph shifts to the left. In figure 5, letter 210 is 0, so the graph is shifted 2 units to the left. The magnitude of A indicates the stretch of the graph. If letter 1d44 is 1, the point associated with a particular x value shifts farther from the x-axis, so the graph appears to become narrower, and there is a vertical stretch. But if letter 1d44 is 1, the point associated with a particular x value shifts closer to the x-axis, so the graph appears to become wider, but in fact, there is a vertical compression. In Figure 5, letter 1d44e1, so the graph becomes narrower. The standard form and the general form are equivalent methods of describing the same function. We can see this by expanding out the general form and setting it equal to the standard form. Letter 1d44e. Letter 1d465 minus letter 210e2 plus letter 1d458 letter 1d44e letter 1d465 2 minus 2 letter 1d44e letter 210e letter 1d465 plus letter 1d44e letter 210e 2 plus letter 1d458 equals letter 1d44e letter 1d465 2 plus letter 1d44f letter 1d465 plus letter 1d450 letter 1d. For the linear terms to be equal, the coefficients must be equal. 2 letter 1d44 letter 210e equals letter 1d44f. So letter 210e equals minus letter 1d44f2a. This is the axis of symmetry we defined earlier. Setting the constant terms equal, letter 1d44 letter 210e 2 plus letter 1d458 letter 1d458 equals letter 1d450 letter 1d450 minus letter 1d44 letter 210e to letter 1d450 minus letter 1d44e minus letter 1d44f to letter 1d44e2 letter 1d450 minus letter 1d44f 24 letter 1d44e in practice. Though it is usually easier to remember that k is the output value of the function when the input is h, so letter 1d453 letter 210e equals letter 1d458. Forms of quadratic functions. A quadratic function is a polynomial function of degree 2. The graph of a quadratic function is a parabola. The general form of a quadratic function is letter 1d453. Letter 1d465 equals letter 1d44 letter 1d465 2 plus letter 1d44f letter 1d465 plus letter 1d450, where a, b, and c are real numbers and letter 1d44e not equal to 0. The standard form of a quadratic function is letter 1d453. Letter 1d465 equals letter 1d44e. Letter 1d465 minus letter 210e2 plus letter 1d458, where letter 1d44e not equal to 0. The vertex h, k, is located at letter 210e equals letter 1d44f2a. Letter 1d458 equals letter 1d453. Letter 210e equals letter 1d453 minus letter 1d44f2a. How to given a graph of a quadratic function. Write the equation of the function in general form. Identify the horizontal shift of the parabola. This value is h. Identify the vertical shift of the parabola. This value is k. Substitute the values of the horizontal and vertical shift for h and k in the function letter 1d453. Letter 1d465 equals letter 1d44e. Letter 1d465 letter 210e2 plus letter 1d458. Substitute the values of any point, other than the vertex, on the graph of the parabola for x and letter 1d453, letter 1d465. Solve for the stretch factor, letter 1d44e. Expand and simplify to write in general form. Example 2, writing the equation of a quadratic function from the graph. Write an equation for the quadratic function g in Figure 7 as a transformation of letter 1d453. Letter 1d465 equals letter 1d465 and then expand the formula and simplify terms to write the equation in general form. Graph of a parabola with its vertex at -2, -3. Figure 7 solution, we can see the graph of g is the graph of letter 1d453. Letter 1d465 equals letter 1d465 2 shifted to the left 2 and down 3. Giving a formula in the form letter 1d454. Letter 1d465 equals letter 1d44e. Letter 1d465 minus 2. 2 minus 3 equals letter 1d44e. Letter 1d465 plus 3. Substituting the coordinates of a point on the curve, such as 0, -1, we can solve for the stretch factor. -12 letter 1d44e equals letter 1d44e. 0 plus 2 minus 34 letter 1d44e 12 in standard form. The algebraic model for this graph is letter 1d454 letter 1d465 equals 12, letter 1d465 plus 223. To write this in general polynomial form, we can expand the formula and simplify terms. Letter 1d454, letter 1d465, equals 12, letter 1d465 plus 2 minus 312, letter 1d465 plus 2, letter 1d465 plus 2 minus 312, letter 1d465 2 plus 4, letter 1d465 plus 4, minus 312, letter 1d465 2, plus 2, letter 1d465 plus 2 minus 312, letter 1d465 2, plus 2 let. Notice that the horizontal and vertical shifts of the basic graph of the quadratic function determine the location of the vertex of the parabola. The vertex is unaffected by stretches and compressions. Analysis, we can check our work using the table feature on a graphing utility. First, enter y1 equals 12, letter 1d465 plus 2 minus 3. Next, select TBLSET, then use TBL start equals 6 and letter 1d6c5 TBL equals 2 and select table. See table 1. X64202 Y51315 table 1. The ordered pairs in the table correspond to points on the graph. Try it 1. A coordinate grid has been superimposed over the quadratic path of a basketball in figure 8. Assume that the point 4, 7 is the highest point of the basketball's trajectory. Find an equation for the path of the ball. Does the shooter make the basket? Stop motion picture of a boy throwing a basketball into a hoop to show the parabolic curve it makes. Figure 8, credit. Modification of work by Dan Mayer. How to given a quadratic function in general form, find the vertex of the parabola. Identify A, B, and C. Find H, the x-coordinate of the vertex, by substituting A and B into letter 210e equals letter 1d44f2a. Find K, the y-coordinate of the vertex, by evaluating letter 1d458 equals letter 1d453. Letter 210e equals letter 1d453 minus letter 1d44f2a. Example 3, finding the vertex of a quadratic function. Find the vertex of the quadratic function letter 1d453. Letter 1d465 equals 2 letter 1d465, 2 6 letter 1d465 plus 7. Rewrite the quadratic in standard form, vertex form. Solution: the horizontal coordinate of the vertex will be at the vertical coordinate of the vertex will be a t letter 210e letter 1d458 equals minus letter 1d44f to letter 1d44e minus 62 2 6432 letter 1d453. Letter 210e letter 1d453 32 2 32 2 minus 6 32 plus 752, rewriting into standard form. The stretch factor will be the same as the a in the original quadratic. First, find the horizontal coordinate of the vertex. Then find the vertical coordinate of the vertex. Substitute the values into standard form using the a from the general form. Letter 1d453, letter 1d465, letter 1d453. Letter 1d465 equals letter 1d44, letter 1d465, 2 plus letter 1d44f, letter 1d465, plus letter 1d450 to letter 1d465, 2 minus 6 letter 1d465, plus 7, the standard form of a quadratic function prior to writing the function then becomes the following. Letter 1d453, letter 1d465, equals 2, letter 1d465 32, 2 plus 52 analysis. One reason we may want to identify the vertex of the parabola is that this point will inform us where the maximum or minimum value of the output occurs, k, and where it occurs, x. Try it too given the equation letter 1d454, letter 1d465, equals 13 plus letter 1d465, 2 minus 6 letter 1d465. Write the equation in general form and then in standard form. Finding the domain and range of a quadratic function, any number can be the input value of a quadratic function. Therefore, the domain of any quadratic function is all real numbers. Because parabolas have a maximum or a minimum point, the range is restricted. Since the vertex of a parabola will be either a maximum or a minimum, the range will consist of all y values greater than or equal to the y-coordinate at the turning point, or less than or equal to the y-coordinate at the turning point, depending on whether the parabola opens up or down. Domain and range of a quadratic function. The domain of any quadratic function is all real numbers, unless the context of the function presents some restrictions. The range of a quadratic function written in general form. With a positive a value is letter 1d453, letter 1d465, greater or equal to letter 1d453 minus letter 1d44f2a, or letter 1d453 minus letter 1d44f2a, infinity. The range of a quadratic function written in general form with a negative a value is letter 1d453, letter 1d465 less or equal to letter 1d453 minus letter 1d44f2a, or minus infinity, letter 1d453 minus letter 1d44f2a. The range of a quadratic function written in standard form letter 1d453, letter 1d465 equals letter 1d44e. Letter 1d465 minus letter 210e2 plus letter 1d458 with a positive a value is letter 1d453. Letter 1d465 greater or equal to letter 1d458. The range of a quadratic function written in standard form with a negative a value is letter 1d453, letter 1d465, less or equal to letter 1d458. How to given a quadratic function, find the domain and range. Identify the domain of any quadratic function as all real numbers. Determine whether a is positive or negative. If a is positive, the parabola has a minimum. If a is negative, the parabola has a maximum. Determine the maximum or minimum value of the parabola, k. If the parabola has a minimum, the range is given by letter 1d453, letter 1d465 greater or equal to letter 1d458, or letter 1d458 infinity. If the parabola has a maximum, the range is given by letter 1d453, letter 1d465, less or equal to letter 1d458, or minus infinity, letter 1d458. Example 4, finding the domain and range of a quadratic function. Find the domain and range of letter 1d453, letter 1d465, equals minus 5 letter 1d465 2, plus 9 letter 1d465 minus 1. Solution: as with any quadratic function, the domain is all real numbers. Because a is negative, the parabola opens downward and has a maximum value. We need to determine the maximum value. We can begin by finding the x value of the vertex. Letter 210e equals minus letter 1d44f to letter 1d44e minus 92, minus 5 910. The maximum value is given by letter 1d453 letter 210e. Letter 1d453, 910 equals minus 5 910 2 plus 9 910 minus 16,120. The range is letter 1d453. Letter 1d465 less or equal to 6,120, or minus infinity, 6,120. Try at 3. Find the domain and range of letter 1d453. Letter 1d465 equals 2, letter 1d465 minus 47 2 plus 811. Determining the maximum and minimum values of quadratic functions, the output of the quadratic function at the vertex is the maximum or minimum value of the function, depending on the orientation of the parabola. We can see the maximum and minimum values in Figure 9. Two graphs where the first graph shows the maximum value for f, x equals x22 plus 1, which occurs at 2, 1, and the second graph shows the minimum value for g, x equals x plus 3, 2 plus 4, which occurs at minus 3, 4. Figure 9, there are many real-world scenarios that involve finding the maximum or minimum value of a quadratic function, such as applications involving area and revenue. Example 5, finding the maximum value of a quadratic function. A backyard farmer wants to enclose a rectangular space for a new garden within her fenced backyard. She has purchased 80 feet of wire fencing to enclose 3 sides, and she will use a section of the backyard fence as the 4th side. A. Find a formula for the area enclosed by the fence if the sides of fencing perpendicular to the existing fence have length L. B. What dimensions should she make her garden to maximize the enclosed area? Solution: let's use a diagram such as Figure 10 to record the given information. It is also helpful to introduce a temporary variable, W, to represent the width of the garden and the length of the fence section parallel to the backyard fence. Diagram of the garden and the backyard. Figure 10, A, we know we have only 80 feet of fence available. And letter 1d43f plus letter 1d44a plus letter 1d43f equals 80, or more simply, 2 letter 1d43f plus letter 1d44a equals 80. This allows us to represent the width, w, in terms of L letter 1d44a equals 80 minus 2 letter 1d43f. Now, we are ready to write an equation for the area the fence encloses. We know the area of a rectangle is length multiplied by width, so letter 1d434 letter 1d434. Letter 1d43f equals letter 1d43f letter 1d44a equals letter 1d43f. 80 minus 2 letter 1d43f 80 letter 1d43f minus 2 letter 1d43f 2. This formula represents the area of the fence in terms of the variable length L. The function, written in general form, is letter 1d434, letter 1d43f, equals minus 2 letter 1d43f2 plus 80 letter 1d43f. B, the quadratic, has a negative leading coefficient, so the graph will open downward, and the vertex will be the maximum value for the area. In finding the vertex, we must be careful because the equation is not written in standard polynomial form with decreasing powers. This is why we rewrote the function in general form above. Since a is the coefficient of the squared term, letter 1d44e equals minus 2, letter 1d44f equals 80, and letter 1d450 equals 0. To find the vertex, letter 210e equals minus letter 1d44f to letter 1d44e minus 802, minus 220, nd letter 1d458 equals letter 1d434. 2080. 20 minus 220, 2,800. The maximum value of the function is an area of 800 square feet, which occurs when letter 1d43f equals 20 feet. When the shorter sides are 20 feet, there is 40 feet of fencing left for the longer side. To maximize the area, she should enclose the garden so the two shorter sides have length 20 feet and the longer side parallel to the existing fence has length 40 feet. Analysis, this problem also could be solved by graphing the quadratic function. We can see where the maximum area occurs on a graph of the quadratic function in figure 11. Graph of the parabolic function AL equals 2L2 plus 80L, which the x-axis is labeled length L and the y-axis is labeled area A. The vertex is at 2,800. Figure 11, how to given an application involving revenue, use a quadratic equation to find the maximum. Write a quadratic equation for a revenue function. Find the vertex of the quadratic equation. Determine the y-value of the vertex. Example 6, finding maximum revenue. The unit price of an item affects its supply and demand. That is, if the unit price goes up, the demand for the item will usually decrease. For example, a local newspaper currently has 84,000 subscribers at a quarterly charge of $30. Market research has suggested that if the owners raise the price to $32, they would lose 5,000 subscribers. Assuming that subscriptions are linearly related to the price, what price should the newspaper charge for a quarterly subscription to maximize their revenue? Solution: revenue is the amount of money a company brings in. In this case, the revenue can be found by multiplying the price per subscription times the number of subscribers, or quantity. We can introduce variables, P for price per subscription and Q for quantity, giving us the equation revenue equals letter 1d45d letter 1d444. Because the number of subscribers changes with the price, we need to find a relationship between the variables. We know that currently letter 1d45d equals 30 and letter 1d444 equals 84, 000. We also know that if the price rises to $32, the newspaper would lose 5,000 subscribers, giving a second pair of values. Letter 1d45d equals 32 and letter 1d444 equals 79, 000. From this, we can find a linear equation relating the two quantities. The slope will be, this tells us the paper will lose 2,500 subscribers for each dollar they raise the price. We can then solve for the y-intercept. Q84, 000, letter 1d44f equals minus 2,500 letter 1d45d plus letter 1d44f minus 2,500. 30 plus letter 1d44f, 159. 0 substitute in the point letter 1d444 equals 84, and letter 1d45d equals 30. Solve forb. This gives us the linear equation, letter 1d444 equals -2. 500p plus 159, 0 relating cost and subscribers. We now return to our revenue equation. Revenue equals letter 1d45d, letter 1d444, letter 1d45d. -2, 500p plus 159. 0, 0, 0, -2, 500p2 plus 159. 0p, we now have a quadratic function for revenue as a function of the subscription charge. To find the price that will maximize revenue for the newspaper, we can find the vertex. Letter 210e equals -159, 0002, -2, 531. 8. The model tells us that the maximum revenue will occur if the newspaper charges $31, $80 for a subscription. To find what the maximum revenue is, we evaluate the revenue function. Maximum revenue equals -2, 531. 8, 2 plus 159, 0, 31. 8, 2, 528, 100 analysis. This could also be solved by graphing the quadratic as in figure 12. We can see the maximum revenue on a graph of the quadratic function. Graph of the parabolic function, which the x-axis is labeled price, p, and the y-axis is labeled revenue. The vertex is at 31, 80, 258,100. Figure 12. Finding the x and y-intercepts of a quadratic function, much as we did in the application problems above. We also need to find intercepts of quadratic equations for graphing parabolas. Recall that we find the y-intercept of a quadratic by evaluating the function at an input of 0, and we find the x-intercepts at locations where the output is 0. Notice in figure 13 that the number of x-intercepts can vary depending upon the location of the graph. 3 graphs where the first graph shows a parabola with no x-intercept, the second is a parabola with 1 intercept, and the third parabola is of 2 x-intercepts. Figure 13 number of x-intercepts of a parabola, how to given a quadratic function letter 1d453, letter 1d465, find the y and x-intercepts. Evaluate letter 1d453, 0, to find the y-intercept. Solve the quadratic equation letter 1d453, letter 1d465 equals 0 to find the x-intercepts. Example 7, finding the y and x-intercepts of a parabola, find the y and x-intercepts of the quadratic letter 1d453, letter 1d465, equals 3 letter 1d465 2 plus 5 letter 1d465 minus 2. Solution, we find the y-intercept by evaluating letter 1d453, 0. Letter 1d453, 0, equals 3, 0, 2 plus 5, 0 minus 2, so the y-intercept is at 0 minus 2. For the x-intercepts, we find all solutions of letter 1d453, letter 1d465, equals 0. 0 equals 3 letter 1d465 2 plus 5 letter 1d465 minus 2 in this case. The quadratic can be factored easily, providing the simplest method for solution. 0 equals 3 letter 1d465 minus 1, letter 1d465 plus 2, so the x-intercepts are at 130 and minus 2, 0. Analysis by graphing the function, we can confirm that the graph crosses the y-axis at 0, minus 2. We can also confirm that the graph crosses the x-axis at 130 and minus 2, 0. See figure 14 graph of a parabola which has the following intercepts, minus 2, 0, 1, 3, 0, and 0, minus 2. Figure 14 rewriting quadratics in standard form in example 7, the quadratic was easily solved by factoring. However, there are many quadratics that cannot be factored. We can solve these quadratics by first rewriting them in standard form. How to given a quadratic function, find the x-intercepts by rewriting in standard form. Substitute a and b into letter 210e equals minus letter 1d44f2a. Substitute letter 1d465 equals letter 210e into the general form of the quadratic function. To find k, rewrite the quadratic in standard form using h and k. Solve for when the output of the function will be 0 to find the x-intercepts. Example 8, finding the x-intercepts of a parabola. Find the x-intercepts of the quadratic function letter 1d453, letter 1d465, equals 2 letter 1d4652 plus 4 letter 1d465 minus 4. Solution, we begin by solving for when the output will be 0. Plus 4 letter 1d465 minus 4, because the quadratic is not easily factorable in this case, we solve for the intercepts by first rewriting the quadratic in standard form. We know that letter 1d44e equals 2. Then we solve for h and k letter 210e equals minus letter 1d44f to letter 1d44e minus 42. 2 minus 1 letter 1d458 equals letter 1d453. Minus 1 2 minus 1 2 plus 4 minus 1 minus 4 minus 6. So now we can rewrite in standard form. Letter 1d453, letter 1d465 equals 2. Letter 1d465 plus 1 2 minus 6. We can now solve for when the output will be 0. 0 equals 2. Letter 1d465 plus 1 2 minus 66 equals 2. Letter 1d465 plus 123 equals. Letter 1d465 plus 1 2 letter 1d465 plus 1 equals plus 3 square letter 1d465 equals minus 1 plus or minus 3 square. The graph has x-intercepts at minus 1 minus 3 square, 0, and minus 1 plus 3 square 0. We can check our work by graphing the given function on a graphing utility and observing the x-intercepts. See Figure 15. Graph of a parabola which has the following x-intercepts, minus 2, 732, 0, and 0, 732, 0. Figure 15 analysis, we could have achieved the same results using the quadratic formula. Identify letter 1d44e equals 2, letter 1d44f equals 4, and letter 1d450 equals minus 4. Letter 1d465 equals minus letter 1d44f plus or minus letter 1d44f. 2 minus 4 letter 1d44 letter 1d450 square root 2 letter 1d44 minus 4 plus or minus 42 minus 4 2. Minus 4 square root 2. 2 minus 4 plus or minus 48 square root 4 minus 4 plus or minus 3. 16. Square root 4 minus 1 plus or minus 3 square, so the x-intercepts occur at minus 1 minus 3 square, 0, and minus 1 plus 3 square 0. Try it 4 and a try it. We found the standard and general form for the function letter 1d454, letter 1d465, equals 13 plus letter 1d465, 2 minus 6 letter 1d465. Now find the y and x-intercepts, if any. Example 9, applying the vertex and x-intercepts of a parabola, a ball is thrown upward from the top of a 40-foot-high building at a speed of 80 feet per second. The ball's height above ground can be modeled by the equation letter 1d43b, letter 1d461, equals minus 16 letter 1d461 2 plus 80 letter 1d461 plus 40. A. When does the ball reach the maximum height? B. What is the maximum height of the ball? C. When does the ball hit the ground? Solution: the ball reaches the maximum height at the vertex of the parabola. Letter 210e equals minus 802, minus 16, 8,032,522. 5. The ball reaches a maximum height after 5 seconds. B. To find the maximum height, find the y-coordinate of the vertex of the parabola. Letter 1d458 equals letter 1d43b minus letter 1d44f to letter 1d44e letter 1d43b 2. 5 minus 16, 2. 5 2 plus 80, 2. 5 plus 40,140, the ball reaches a maximum height of 140 feet. C. To find when the ball hits the ground, we need to determine when the height is 0, letter 1d43b, letter 1d461, equals 0. We use the quadratic formula. Letter 1d461 equals minus 80 plus or minus 802 minus 4, minus 16. 40, square root 2, minus 16, minus 80 plus or minus 8,960 square minus 32. Because the square root does not simplify nicely, we can use a calculator to approximate the values of the solutions. Letter 1d461 equals minus 80 minus 8,960 square minus 32, approximately 5. 458, or letter 1d461 equals minus 80, plus 8,960 square minus 32 approximately minus 0. 458, the second answer is outside the reasonable domain of our model, so we conclude the ball will hit the ground after about 458 seconds. See Figure 16. A graph is shown on a set of x and y axes. The scale is -5 to +5 for both x and y. The graph rises from below in the third quadrant, crossing the x-axis at x equals -2, has a turning point at -1, 3, crosses the x-axis again at the origin, has another turning point at 1, -3, and crosses the x-axis one last time at x equals 2, rising from there. Figure 16. Note that the graph does not represent the physical path of the ball upward and downward. Keep the quantities on each axis in mind while interpreting the graph. Try at 5. A rock is thrown upward from the top of a 112-foot high cliff, overlooking the ocean at a speed of 96 feet per second. The rock's height above ocean can be modeled by the equation letter 1d43b, letter 1d461, equals -16 letter 1d461 2 plus 96 letter 1d461 plus 112. A. When does the rock reach the maximum height? B. What is the maximum height of the rock? C. When does the rock hit the ocean? Media access: these online resources for additional instruction and practice with quadratic equations. Graphing quadratic functions in general form, graphing quadratic functions in standard form, quadratic function, review characteristics of a quadratic function 5. 1 section, exercises verbal 1. Explain the advantage of writing a quadratic function in standard form. 2. How can the vertex of a parabola be used in solving real-world problems? 3. Explain why the condition of letter 1d44e not equal to 0 is imposed in the definition of the quadratic function. 4. What is another name for the standard form of a quadratic function? 5. What two algebraic methods can be used to find the horizontal intercepts of a quadratic function? Algebraic for the following exercises, rewrite the quadratic functions in standard form and give the vertex. 6. Letter 1d453, letter 1d465 equals letter 1d465 2 minus 12 letter 1d465 plus 32 7. Letter 1d454 letter 1d465 equals letter 1d465 2 plus 2 letter 1d465 minus 38. Letter 1d453. Letter 1d465 equals letter 1d465 2 minus letter 1d465 9. Letter 1d453, letter 1d465 equals letter 1d465 2 plus 5 letter 1d465 minus 210. Letter 210e, letter 1d465 equals 2 letter 1d465 2 plus 8 letter 1d465 minus 1011. Letter 1d458, letter 1d465 equals 3 letter 1d465 2 minus 6 letter 1d465 minus 912. 13. Letter 1d453, letter 1d465 equals 3 letter 1d465 2 minus 5 letter 1d465 minus 1 for the following exercises. Determine whether there is a minimum or maximum value to each quadratic function. Find the value and the axis of symmetry. 14. Letter 1d466, letter 1d465 equals 2 letter 1d465 2 plus 10 letter 1d465 plus 12 15. Letter 1d453, letter 1d465 equals 2 letter 1d465 2 minus 10 letter 1d465 plus 4 16. Letter 1d453, letter 1d465 equals minus letter 1d465 2 plus 4 letter 1d465 plus 317. Letter 1d453, letter 1d465 equals 4 letter 1d465 2 plus letter 1d465 minus 118. Letter 210e, letter 1d461 equals minus 4 letter 1d461 2 plus 6 letter 1d461 minus 119. Letter 1d453, letter 1d465 equals 12 letter 1d465 2 plus 3 letter 1d465 plus 120. Letter 1d453, letter 1d465 equals minus 13 letter 1d465 2 minus 2 letter 1d465 plus 3 for the following exercises. Determine the domain and range of the quadratic function. 21. Letter 1d453, letter 1d465 equals letter 1d465 minus 32 plus 222. Letter 1d453, letter 1d465 equals minus 2, letter 1d465 plus 3 2 minus 623. Letter 1d453, letter 1d465 equals letter 1d465 2 plus 6 letter 1d465 plus 424. Letter 1d453, letter 1d465 equals 2 letter 1d465 2 minus 4 letter 1d465 plus 225. Letter 1d458, letter 1d465 equals 3 letter 1d465 2 minus 6 letter 1d465 minus 9 for the following exercises. Use the vertex, hk, and a point on the graph, xy, to find the general form of the equation of the quadratic function. 26. Letter 210e, letter 1d458 equals 20. Letter 1d465, letter 1d466 equals 4 4 27. Letter 210e, letter 1d458 equals minus 2 minus 1. Letter 1d465, letter 1d466 equals minus 4 3 28. Letter 210e, letter 1d458 equals 0 1. Letter 1d465, letter 1d466 equals 2 5 29. Letter 210e, letter 1d458 equals 2 3. Letter 1d465, letter 1d466 equals 5 12 30. Letter 210e, letter 1d458 equals minus 5 3. Letter 1d465, letter 1d466 equals 2 9 31. Letter 210e, letter 1d458 equals 3 2. Letter 1d465, letter 1d466 equals 10 1 32. Letter 210e, letter 1d458 equals 0 1. Letter 1d465, letter 1d466 equals 1 0 33. Letter 210e, letter 1d458 equals 1 0. Letter 1d465, letter 1d466 equals 0 1. Graphical for the following exercises. Sketch a graph of the quadratic function and give the vertex, axis of symmetry, and intercepts. 34. Letter 1d453, letter 1d465 equals letter 1d465 2 minus 2, letter 1d465 35. Letter 1d453, letter 1d465 equals letter 1d465 2 minus 6, letter 1d465 minus 136. Letter 1d453, letter 1d465 equals letter 1d465 2 minus 5, letter 1d465 minus 637. Letter 1d453, letter 1d465 equals letter 1d465 2 minus 7, letter 1d465 plus 338. Letter 1d453, letter 1d465 equals minus 2, letter 1d465 2 plus 5, letter 1d465 minus 839. Letter 1d453, letter 1d465 equals 4, letter 1d465 2 minus 12, letter 1d465 minus 3 for the following exercises. Write the equation for the graphed quadratic function. 40. Graph of a positive parabola with a vertex at 2, minus 3 and y-intercept at 0, 1. 41. Graph of a positive parabola with a vertex at minus 1, 2 and y-intercept at 0, 3, 42. Graph of a negative parabola with a vertex at 2, 7. 43. Graph of a negative parabola with a vertex at minus 1, 2, 44. Graph of a positive parabola with a vertex at 3, minus 1 and y-intercept at 0, 3. 5, 45. Graph of a negative parabola with a vertex at minus 2, 3. Numeric for the following exercises, use the table of values that represent points on the graph of a quadratic function. By determining the vertex and axis of symmetry, find the general form of the equation of the quadratic function. 46. X, 21012y5212 X, 21012y10144948. X, 21012y 2121 X, 21012y 8301050. X, 21012y 82028. Technology for the following exercises, use a calculator to find the answer. 51. Graph on the same set of axes the functions letter 1d453, letter 1d465 equals letter 1d465 2, letter 1d453, letter 1d465 equals 2 letter 1d4652, and letter 1d453. Letter 1d465 equals 13 letter 1d4652. What appears to be the effect of changing the coefficient? 52. Graph on the same set of axes letter 1d453. Letter 1d465 equals letter 1d4652. Letter 1d453. Letter 1d465 equals letter 1d4652 plus 2 and letter 1d453. Letter 1d465 equals letter 1d4652. Letter 1d453. Letter 1d465 equals letter 1d4652 plus 5 and letter 1d453. Letter 1d465 equals letter 1d465 minus 3. What appears to be the effect of adding a constant? 53. Graph on the same set of axes letter 1d453. Letter 1d465 equals letter 1d465 letter 1d453. Letter 1d465 equals letter 1d465 minus 2 letter 1d453. Letter 1d465 minus 3 2, and letter 1d453. Letter 1d465 equals letter 1d465 plus 4 2. What appears to be the effect of adding or subtracting those numbers? 54. The path of an object projected at a 45-degree angle with initial velocity of 80 feet per second is given by the function letter 210e. Letter 1d465 equals minus 32. 82 letter 1d465 2 plus letter 1d465, where x is the horizontal distance traveled and letter 210e. Letter 1d465 is the height in feet. Use the trace feature of your calculator to determine the height of the object when it has traveled 100 feet away horizontally. 55. A suspension bridge can be modeled by the quadratic function letter 210e, letter 1d465 equals 1x2 with, where letter 1d465 is the number of feet from the center and letter 210e. Letter 1d465 is height in feet. Use the trace feature of your calculator to estimate how far from the center does the bridge have a height of 100 feet. Extensions for the following exercises: use the vertex of the graph of the quadratic function and the direction the graph opens to find the domain and range of the function. 56. Vertex 1 minus 2 opens up. 57. Vertex minus 1 2 opens down. 58. Vertex minus 5 11 opens down. 59. Vertex minus 100 100 opens up. For the following exercises, write the equation of the quadratic function that contains the given point and has the same shape as the given function. 60. Contains 11 and has shape of letter 1d453, letter 1d465 equals 2 letter 1d4652. Vertex is on the y-axis. 61. Contains minus 1 4 and has the shape of letter 1d453, letter 1d465 equals 2 letter 1d4652. Vertex is on the y-axis. 62. Contains 23 and has the shape of letter 1d453, letter 1d465 equals 3 letter 1d4652. Vertex is on the y-axis. 63. Contains 1 minus 3 and has the shape of letter 1d453, letter 1d465 equals minus letter 1d4652. Vertex is on the y-axis. 64. Contains 43 and has the shape of letter 1d453, letter 1d465 equals 5 letter 1d4652. Vertex is on the y-axis. 65. Contains 1 minus 6, has the shape of letter 1d453, letter 1d465 equals 3 letter 1d4652. Vertex has x-coordinate of minus 1. Real-world applications 66. Find the dimensions of the rectangular dog park producing the greatest enclosed area given 200 feet of fencing. 67. Find the dimensions of the rectangular dog park split into 2 pens of the same size producing the greatest possible enclosed area given 300 feet of fencing. 68. Find the dimensions of the rectangular dog park producing the greatest enclosed area split into 3 sections of the same size given 500 feet of fencing. 69. Among all of the pairs of numbers whose sum is 6, find the pair with the largest product. What is the product? 70. Among all of the pairs of numbers whose difference is 12, find the pair with the smallest product. What is the product? 71. Suppose that the price per unit in dollars of a cell phone production is modeled by letter 1D45D equals $45 minus 0. 125x, where x is in thousands of phones produced, and the revenue represented by thousands of dollars is letter 1D445 equals letter 1D465, letter 1D45D. Find the production level that will maximize revenue. 72. A rocket is launched in the air. Its height, in meters above sea level, as a function of time in seconds is given by letter 210e, letter 1D461, equals minus 4. 9t2 plus 229t plus 234. Find the maximum height the rocket attains. 73. A ball is thrown in the air from the top of a building. Its height, in meters above ground, as a function of time in seconds is given by letter 210e, letter 1D461, equals minus 4. 9t2 plus 24t plus 8. How long does it take to reach maximum height? 74. A soccer stadium holds 62,000 spectators. With a ticket price of $11, the average attendance has been 26,000. When the price dropped to $9, the average attendance rose to 31,000. Assuming that attendance is linearly related to ticket price, what ticket price would maximize revenue? 75. A farmer finds that if she plants 75 trees per acre, each tree will yield 20 bushels of fruit. She estimates that for each additional tree planted per acre, the yield of each tree will decrease by 3 bushels. How many trees should she plant per acre to maximize her harvest? Learning objectives in this section, you will identify power functions. Identify end behavior of power functions. Identify polynomial functions. Identify the degree and leading coefficient of polynomial functions. 3 birds on a cliff with the sun rising in the background. Figure 1, credit. Jason Bay, Flickr, suppose a certain species of bird thrives on a small island. Its population over the last few years is shown in Table 1. Year 2009, 2010, 2011, 2012, 2013, bird population 800, 897, 992, 1083, 1169, Table 1. The population can be estimated using the function letter 1D443. Letter 1D461 equals minus 0. 3t3 plus 97t plus 800, where represents the bird population on the island t years after 2009. We can use this model to estimate the maximum bird population and when it will occur. We can also use this model to predict when the bird population will disappear from the island. In this section, we will examine functions that we can use to estimate and predict these types of changes. Identifying power functions before we can understand the bird problem, it will be helpful to understand a different type of function. A power function is a function with a single term that is the product of a real number, a coefficient, and a variable raised to a fixed real number. As an example, consider functions for area or volume. The function for the area of a circle with radius r is letter 1D434. Letter 1D45f equals letter 1D70b letter 1D45f 2, and the function for the volume of a sphere with radius r is letter 1D449. Letter 1D45f equals 43 letter 1D70b letter 1D45f. 3 both of these are examples of power functions because they consist of a coefficient. Letter 1D70b, or 43 letter 1D70b, multiplied by a variable r raised to a power. Power function, a power function, is a function that can be represented in the form letter 1D453, letter 1D465, equals letter 1D458, letter 1D465, letter 1D45d, where k and p are real numbers, and k is known as the coefficient. Q and a is letter 1D453, letter 1D465 equals 2 letter 1D465 a power function? No. A power function contains a variable base raised to a fixed power. This function has a constant base raised to a variable power. This is called an exponential function, not a power function. Example 1, identifying power functions. Which of the following functions are power functions? A. Constant function identity, function quadratic, function cubic, function reciprocal squared, function square root, function cube, root function solution. All of the listed functions are power functions. The constant and identity functions are power functions because they can be written as letter 1d453, letter 1d465 equals letter 1d4650, and letter 1d453, letter 1d465 equals letter 1d4651, respectively. The quadratic and cubic functions are power functions with whole number powers letter 1d453, letter 1d465 equals letter 1d4652, and letter 1d453, letter 1d465 equals letter 1d4653. The reciprocal and reciprocal squared functions are power functions with negative whole number powers because they can be written as letter 1d453, letter 1d465 equals letter 1d465 minus 1, and letter 1d453, letter 1d465 equals letter 1d465 minus 2. The square and cube root functions are power functions with fractional powers because they can be written as letter 1d453, letter 1d465 equals letter 1d465 12, or letter 1d453, letter 1d465 equals letter 1d465 13. Try it 1, which functions are power functions. Letter 1d453, letter 1d465, letter 1d454, letter 1d465, letter 210e, letter 1d465 equals 2, letter 1d465 4, letter 1d465 3 minus letter 1d465 5 plus 5, letter 1d465 32, letter 1d465 5 minus 13, letter 1d465 2 plus 4. Identifying end behavior of power functions. Figure 2 shows the graphs of letter 1d453, letter 1d465 equals letter 1d465 2, letter 1d454, letter 1d465 equals letter 1d465 4, and letter 210e, letter 1d465 equals letter 1d465 6, which are all power functions with even, positive integer powers. Notice that these graphs have similar shapes, very much like that of the quadratic function in the toolkit. However, as the power increases, the graphs flatten somewhat near the origin and become steeper away from the origin. Graph of three functions, h x equals x2 in green, g x equals x4 in orange, and f x equals x6 in blue. Figure 2 even power functions to describe the behavior as numbers become larger and larger. We use the idea of infinity. We use the symbol infinity for positive infinity and minus infinity for negative infinity. When we say that x approaches infinity, which can be symbolically written as letter 1d465 right infinity, we are describing a behavior. We are saying that x is increasing without bound. With the positive even power function, as the input increases or decreases without bound, the output values become very large positive numbers. Equivalently, we could describe this behavior by saying that as x approaches positive or negative infinity, the letter 1d453, letter 1d465, values increase without bound. In symbolic form, we could write as letter 1d465 right plus infinity, letter 1d453, letter 1d465, right infinity. Figure 3 shows the graphs of letter 1d453, letter 1d465, equals letter 1d4653, letter 1d454, letter 1d465 equals letter 1d4655, and letter 210e, letter 1d465 equals letter 1d4657, which are all power functions with odd whole number powers. Notice that these graphs look similar to the cubic function in the toolkit. Again, as the power increases, the graphs flatten near the origin and become steeper away from the origin. Graph of three functions, f x equals x3 in green, g x equals x5 in orange, and h x equals x7 in blue. Figure 3 odd power functions. These examples illustrate that functions of the form letter 1d453, letter 1d465 equals letter 1d465, letter 1d45b reveal symmetry of one kind or another. First, in Figure 2, we see that even functions of the form letter 1d453, letter 1d465 equals letter 1d465, letter 1d45b, and even are symmetric about the y-axis. In Figure 3, we see that odd functions of the form letter 1d453, letter 1d465 equals letter 1d465, letter 1d45b, and odd are symmetric about the origin. For these odd power functions, As x approaches negative infinity, letter 1 d453, letter 1 d465 decreases without bound. As x approaches positive infinity, letter 1 d453, letter 1 d465 increases without bound. In symbolic form, we write as letter 1 d465 right minus infinity, letter 1 d453, letter 1 d465. Right minus infinity as letter 1 d465 right infinity. Letter 1 d453, letter 1 d465. Right infinity the behavior of the graph of a function as the input values get very small, letter 1 d465 right minus infinity, and get very large, letter 1 d465 right infinity, is referred to as the end behavior of the function. We can use words or symbols to describe end behavior. Figure 4 shows the end behavior of power functions in the form letter 1 d453, letter 1 d465, equals letter 1 d458, letter 1 d465, letter 1 d45b, where n is a non-negative integer, depending on the power and the constant. Graph of an even-powered function with a positive constant. As x goes to negative infinity, the function goes to positive infinity. As x goes to positive infinity, the function goes to positive infinity. Graph of an odd-powered function with a positive constant. As x goes to negative infinity, the function goes to positive infinity. As x goes to positive infinity, the function goes to negative infinity. Graph of an even-powered function with a negative constant. As x goes to negative infinity, the function goes to negative infinity. As x goes to positive infinity, the function goes to negative infinity. Graph of an odd-powered function with a negative constant. As x goes to negative infinity, the function goes to negative infinity. As x goes to positive infinity, the function goes to negative infinity. Figure 4 how to given a power function, letter 1 d453. Letter 1 d465 equals letter 1 d458, letter 1 d465, letter 1 d45b, where n is a positive integer. Identify the end behavior. Determine whether the power is even or odd. Determine whether the constant is positive or negative. Use figure 4 to identify the end behavior. Example 2, identifying the end behavior of a power function, describe the end behavior of the graph of letter 1 d453. Letter 1 d465 equals letter 1 d465 8. Solution: the coefficient is 1 positive, and the exponent of the power function is 8, an even number. As x approaches infinity, the output value of letter 1 d453, letter 1 d465, increases without bound. We write as letter 1 d465 right infinity, letter 1 d453, letter 1 d465, right infinity. As x approaches negative infinity, the output increases without bound. In symbolic form, as letter 1 d465 right minus infinity, letter 1 d453, letter 1 d465, right infinity. We can graphically represent the function as shown in figure 5. Graph of f, x equals x8. Figure 5, example 3, identifying the end behavior of a power function. Describe the end behavior of the graph of letter 1 d453, letter 1 d465, equals minus letter 1 d465 9. Solution: the exponent of the power function is 9, an odd number. Because the coefficient is 1 negative, the graph is the reflection about the x-axis of the graph of letter 1 d453, letter 1 d465, equals letter 1 d465 9. Figure 6 shows that as x approaches infinity, the output decreases without bound. As x approaches negative infinity, the output increases without bound. In symbolic form, we would write as letter 1 d465 right minus infinity, letter 1 d453, letter 1 d465. Right infinity as letter 1 d465 right infinity, letter 1 d453, letter 1 d465, right minus infinity graph of fx equals x9. Figure 6 analysis. We can check our work by using the table feature on a graphing utility. X letter 1 d453, letter 1 d465, 10 1 0 0 0 5 1 953, 125 0 0 5 1 953, 125 10 1 0 0 0. Table 2. We can see from table 2 that when we substitute very small values for x, the output is very large. and when we substitute very large values for x, the output is very small, meaning that it is a very large negative value. Try it to describe in words and symbols the end behavior of letter 1d453, letter 1d465, equals minus 5 letter 1d4654. Identifying polynomial functions, an oil pipeline bursts in the Gulf of Mexico, causing an oil slick in a roughly circular shape. The slick is currently 24 miles in radius, but that radius is increasing by 8 miles each week. We want to write a formula for the area covered by the oil slick by combining two functions. The radius r of the spill depends on the number of weeks w that have passed. This relationship is linear. Letter 1d45f, letter 1d464, equals 24 plus 8 letter 1d464. We can combine this with the formula for the area A of a circle. Letter 1d434, letter 1d45f equals letter 1d70b letter 1d45f. 2 composing these functions gives a formula for the area in terms of weeks. Letter 1d434, letter 1d464 equals letter 1d434, letter 1d45f, letter 1d464, letter 1d434, 24 plus 8 letter 1d464 letter 1d70b, 24 plus 8 letter 1d464 2 multiplying gives the formula. Letter 1d434, letter 1d464 equals 576 letter 1d70b plus 384 letter 1d70b letter 1d464 plus 64 letter 1d70b letter 1d464. 2. This formula is an example of a polynomial function. A polynomial function consists of either 0 or the sum of a finite number of non-zero terms, each of which is a product of a number, called the coefficient of the term, and a variable raised to a non-negative integer power. Polynomial functions, let n be a non-negative integer. A polynomial function is a function that can be written in the form letter 1d453, letter 1d465 equals letter 1d44 letter 1d45b letter 1d465 letter 1d45b plus a to x2 plus a1x plus a0. This is called the general form of a polynomial function. Each letter 1d44 letter 1d456 is a coefficient and can be any real number, but letter 1d44 letter 1d45b not equal to 0. Each expression, letter 1d44 letter 1d456 letter 1d465 letter 1d456, is a term of a polynomial function. Example 4. Identifying polynomial functions. Which of the following are polynomial functions? Letter 1d453, letter 1d465, letter 1d454, letter 1d465, letter 210e, letter 1d465, equals 2 letter 1d465, 3 letter 1d465, plus 4 minus letter 1d465, letter 1d465, 2 minus 4, 5 letter 1d465, plus 2 square solution. The first two functions are examples of polynomial functions because they can be written in the form letter 1d453, letter 1d465 equals letter 1d44 letter 1d45b letter 1d465 letter 1d45b plus a to x2 plus a1x plus a0, where the powers are non-negative integers and the coefficients are real numbers. Letter 1d453, letter 1d465 can be written as letter 1d453, letter 1d465 equals 6 letter 1d465 4 plus 4. Letter 1d454, letter 1d465 can be written as letter 1d454, letter 1d465 equals minus letter 1d465 3 plus 4 letter 1d465. Letter 210e, letter 1d465 cannot be written in this form and is therefore not a polynomial function. Identifying the degree and leading coefficient of a polynomial function. Because of the form of a polynomial function, we can see an infinite variety in the number of terms and the power of the variable. Although the order of the terms in the polynomial function is not important for performing operations, we typically arrange the terms in descending order of power, or in general form. The degree of the polynomial is the highest power of the variable that occurs in the polynomial. It is the power of the first variable if the function is in general form. The leading term is the term containing the highest power of the variable, or the term with the highest degree. The leading coefficient is the coefficient of the leading term. Terminology of polynomial functions: we often rearrange polynomials so that the powers are descending. Diagram to show what the components of the leading term in a function are. The leading coefficient is an, and the degree of the variable is the exponent in xn. Both the leading coefficient and highest degree variable make up the leading term. So the function looks like f x equals a nx n plus a 2x2 plus a 1x plus a 0. When a polynomial is written in this way, we say that it is in general form. How to, given a polynomial function, identify the degree and leading coefficient. Find the highest power of x to determine the degree of the function. Identify the term containing the highest power of x to find the leading term. Identify the coefficient of the leading term. Example 5. Identifying the degree and leading coefficient of a polynomial function. Identify the degree, leading term, and leading coefficient of the following polynomial functions. Letter 1 D453, letter 1 D465, letter 1 D454, letter 1 D461, letter 2 1 0 e, letter 1 D45D, equals 3 plus 2 letter 1 D465, 2 minus 4 letter 1 D465, 35 letter 1 D461, 5 minus 2 letter 1 D461, 3 plus 7 letter 1 D461, 6 letter 1 D45D minus letter 1 D45D, 3 minus 2, solution for the function. Letter 1 D453, letter 1 D465. The highest power of x is 3, so the degree is 3. The leading term is the term containing that degree, minus 4 letter 1 D4653. The leading coefficient is the coefficient of that term, minus 4. For the function letter 1 D454, letter 1 D461, the highest power of t is 5, so the degree is 5. The leading term is the term containing that degree, 5t5. The leading coefficient is the coefficient of that term, 5. For the function letter 210e, letter 1d45d, the highest power of p is 3, so the degree is 3. The leading term is the term containing that degree, minus letter 1d45d3. The leading coefficient is the coefficient of that term, minus 1. Try it 3. Identify the degree, leading term, and leading coefficient of the polynomial letter 1 D453. Letter 1 D465 equals 4 letter 1 D465 2 minus letter 1 D465 6 plus 2 letter 1 D465 minus 6. Identifying end behavior of polynomial functions. Knowing the degree of a polynomial function is useful in helping us predict its end behavior. To determine its end behavior, look at the leading term of the polynomial function. Because the power of the leading term is the highest, that term will grow significantly faster than the other terms as x gets very large or very small, so its behavior will dominate the graph. For any polynomial, the end behavior of the polynomial will match the end behavior of the power function consisting of the leading term. See Table 3. Polynomial function, leading term graph of polynomial function, letter 1 D453, letter 1 D465, equals 5 letter 1 D465 4 plus 2 letter 1 D465 3 minus letter 1 D465 minus 4 5x4 graph of fx equals 5x4 plus 2x3x4. Letter 1 D453, letter 1 D465 equals minus 2 letter 1 D465 6 minus letter 1 D465 5 plus 3 letter 1 D465 4 plus letter 1 D465 3 minus 2 letter 1 D465 6 graph of f x equals 2x6x5 plus 3x4 plus x3. Letter 1 D453, letter 1 D465 equals 3 letter 1 D465 5 minus 4 letter 1 D465 4 plus 2 letter 1 D465 2 plus 1 3x5 graph of f x equals 3x5 dash 4x4 plus 2x2 plus 1. Letter 1 D453, letter 1 D465 equals minus 6 letter 1 D465 3 plus 7 letter 1 D465 2 plus 3 letter 1 D465 plus 1. Graph of fx equals 6x3 plus 7x2 plus 3x plus 1. Table 3, Example 6. Identifying end behavior and degree of a polynomial function. Describe the end behavior and determine a possible degree of the polynomial function in Figure 7. Graph of an odd degree polynomial. Figure 7, try it 4. Describe the end behavior and determine a possible degree of the polynomial function in Figure 8. Graph of an even degree polynomial. Figure 8. Example 7. Identifying end behavior and degree of a polynomial function. Given the function letter 1d453, letter 1d465 equals minus 3 letter 1d4652, letter 1d465 minus 1, letter 1d465 plus 4. Express the function as a polynomial in general form and determine the leading term, degree, and end behavior of the function. Solution. Obtain the general form by expanding the given expression for letter 1d453, letter 1d465, letter 1d453, letter 1d465 equals minus 3 letter 1d4652, letter 1d465 minus 1, letter 1d465 plus 4 minus 3 letter 1d4652, letter 1d4652 plus 3 letter 1d465 minus 4 minus 3 letter 1d465, 4 minus 9 letter 1d4653 plus 12 letter 1d4652. The general form is letter 1d453, letter 1d465, equals minus 3 letter 1d465, 4 minus 9 letter 1d465, 3, plus 12 letter 1d4652. The leading term is minus 3 letter 1d4654. Therefore, the degree of the polynomial is 4. The degree is even 4, and the leading coefficient is negative, 3, so the end behavior is, as letter 1d465, right minus infinity. Letter 1d453, letter 1d465, right minus infinity, as letter 1d465, right infinity. Letter 1d453, letter 1d465, right minus infinity. Try it 5. Given the function letter 1d453, letter 1d465 equals 0, 2 letter 1d465 minus 2, letter 1d465 plus 1, letter 1d465 minus 5. Express the function as a polynomial in general form and determine the leading term, degree, and end behavior of the function. Identifying local behavior of polynomial functions. In addition to the end behavior of polynomial functions, we are also interested in what happens in the middle of the function. In particular, we are interested in locations where graph behavior changes. A turning point is a point at which the function values change from increasing to decreasing or decreasing to increasing. We are also interested in the intercepts. As with all functions, the y-intercept is the point at which the graph intersects the vertical axis. The point corresponds to the coordinate pair in which the input value is 0. Because a polynomial is a function, only one output value corresponds to each input value, so there can be only one y-intercept, 0, a0. The x-intercepts occur at the input values that correspond to an output value of 0. It is possible to have more than one x-intercept. See Figure 9. Figure 9. Intercepts and turning points of polynomial functions. A turning point of a graph is a point at which the graph changes direction from increasing to decreasing or decreasing to increasing. The y-intercept is the point at which the function has an input value of 0. The x-intercepts are the points at which the output value is 0. How to? Given a polynomial function, determine the intercepts. Determine the y-intercept by setting and finding the corresponding output value. Determine the x-intercepts by solving for the input values that yield an output value of 0. Example 8. Determining the intercepts of a polynomial function. Given the polynomial function letter 1d453, letter 1d465 equals letter 1d465 minus 2, letter 1d465 plus 1, letter 1d465 minus 4. Written in factored form for your convenience, determine the y and x-intercepts. Example 9. Determining the intercepts of a polynomial function with factoring. Given the polynomial function letter 1d453, letter 1d465 equals letter 1d465, 4 minus 4, letter 1d465, 2 minus 45. Determine the y and x-intercepts. Try it 6. Given the polynomial function letter 1d453, letter 1d465 equals 2 letter 1d465, 3 minus 6, letter 1d465, 2 minus 20 letter 1d465. Determine the y and x-intercepts. Comparing smooth and continuous graphs, the degree of a polynomial function helps us to determine the number of x-intercepts and the number of turning points. A polynomial function of letter 1d45bth. Degree is the product of letter 1d45b. Factors, so it will have at most letter 1d45b. Roots or zeros or x-intercepts. The graph of the polynomial function of degree letter 1d45b must have at most letter 1d45b 1 turning points. This means the graph has at most one fewer turning point than the degree of the polynomial or one fewer than the number of factors. A continuous function has no breaks in its graph. The graph can be drawn without lifting the pen from the paper. A smooth curve is a graph that has no sharp corners. The turning points of a smooth graph must always occur at rounded curves. The graphs of polynomial functions are both continuous and smooth. Intercepts and turning points of polynomials. A polynomial of degree, letter 1d45b, will have at most letter 1d45b, x-intercepts, and letter 1d45b minus 1. Turning points. Example 10. Determining the number of intercepts and turning points of a polynomial. Without graphing the function, determine the local behavior of the function by finding the maximum number of x-intercepts and turning points for letter 1d453. Letter 1d465 equals minus 3 letter 1d465 10 plus 4 letter 1d465 7 minus letter 1d465 4 plus 2 letter 1d465 3. Try it 7. Without graphing the function, determine the maximum number of x-intercepts and turning points for letter 1d453. Letter 1d465 equals 108 minus 13 letter 1d465, 9 minus 8 letter 1d465, 4 plus 14 letter 1d465 12, plus 2 letter 1d465 3. Example 11. Drawing conclusions about a polynomial function from the graph. What can we conclude about the polynomial represented by the graph shown in Figure 12, based on its intercepts and turning points? Graph of an even degree polynomial, Figure 12. Try at 8. What can we conclude about the polynomial represented by the graph shown in Figure 14, based on its intercepts and turning points? Graph of an odd degree polynomial, Figure 14. Example 12. Drawing conclusions about a polynomial function from the factors. Given the function letter 1d453, letter 1d465 equals minus 4 letter 1d465, letter 1d465 plus 3, letter 1d465 minus 4. Determine the local behavior. Try at 9. Given the function letter 1d453, letter 1d465 equals 0. 2 letter 1d465 minus 2, letter 1d465 plus 1, letter 1d465 minus 5. Determine the local behavior. Media. Access these online resources for additional instruction and practice with power and polynomial functions. Find key information about a given polynomial function, end behavior of a polynomial function, turning points and letter 1d465, intercepts of polynomial functions, least possible degree of a polynomial function. 5. Two-section exercises. Verbal. 1. Explain the difference between the coefficient of a power function and its degree. 2. If a polynomial function is in factored form, what would be a good first step in order to determine the degree of the function? 3. In general, explain the end behavior of a polynomial with odd degree if the leading coefficient is positive. 4. What is the relationship between the degree of a polynomial function and the maximum number of turning points in its graph? 5. What can we conclude if, in general, the graph of a polynomial function exhibits the following end behavior? As letter 1d465 right minus infinity, letter 1d453, letter 1d465, right minus infinity. And as letter 1d465 right infinity, letter 1d453, letter 1d465, right minus infinity. Algebraic. For the following exercises, identify the function as a power function, a polynomial function, or neither. 6. Letter 1d453, letter 1d465 equals letter 1d465 5. 7. Letter 1d453, letter 1d465 equals letter 1d465 2 3. 8. Letter 1d453, letter 1d465 equals letter 1d465 minus letter 1d465 4. 9. Letter 1d453, letter 1d465 equals letter 1d465 to letter 1d465 2 minus 1. 10. Letter 1d453, letter 1d465 equals 2 letter 1d465, letter 1d465 plus 2, letter 1d465 minus 1 2. 11. Letter 1d453, letter 1d465 equals 3 letter 1d465 plus 1. For the following exercises, find the degree and leading coefficient for the given polynomial. 12 minus 3 letter 1d465 4. 13 7 minus 2 letter 1d465 2. 14 minus 2 letter 1d465 2 minus 3 letter 1d465 5 plus letter 1d465 minus 6. 15 letter 1d465 4 minus letter 1d465 2. 2 letter 1d465 plus 1. 16 letter 1d465 2. 2 letter 1d465 minus 3 2. For the following exercises, determine the end behavior of the functions. 17 letter 1d453 letter 1d465 equals letter 1d465 4. 18 letter 1d453 letter 1d465 equals letter 1d465 3. 19 letter 1d453 letter 1d465 equals minus letter 1d465 4. 20 letter 1d453 letter 1d465 equals minus letter 1d465 9. 21 letter 1d453 letter 1d465 equals minus 2 letter 1d465 4 minus 3 letter 1d465 2 plus letter 1d465 minus 1. 22 letter 1d453 letter 1d465 equals 3 letter 1d465 2 plus letter 1d465 minus 2. 23 letter 1d453 letter 1d465 equals letter 1d465 2 2 letter 1d465 3 minus letter 1d465 plus 1. 24 letter 1d453 letter 1d465 equals 2 minus letter 1d465 7. For the following exercises, find the intercepts of the functions. 25 letter 1d453 letter 1d461 equals 2 letter 1d461 minus 1 letter 1d461 plus 2 letter 1d461 minus 3. 26 letter 1d454 letter 1d45b equals minus 2 3 letter 1d45b minus 1 2 letter 1d45b plus 1. 27 letter 1d453 letter 1d465 equals letter 1d465 4 minus 16. 28 letter 1d453 letter 1d465 equals letter 1d465 3 plus 27. 29 letter 1d453 letter 1d465 equals letter 1d465 letter 1d465 2 minus 2 letter 1d465 minus 8. 30 letter 1d453 letter 1d465 equals letter 1d465 plus 3 4 letter 1d465 2 minus 1. Graphic. For the following exercises, determine the least possible degree of the polynomial function shown. 31 graph of an odd degree polynomial. 32 graph of an even degree polynomial. 33 graph of an odd degree polynomial. 34 graph of an odd degree polynomial. 35 graph of an odd degree polynomial. 36 graph of an even degree polynomial. 37 graph of an odd degree polynomial. 38 graph of an even degree polynomial. For the following exercises, determine whether the graph of the function provided is a graph of a polynomial function. If so, determine the number of turning points and the least possible degree for the function. 39 graph of an odd degree polynomial. 40 graph of an equation. 41 graph of an even degree polynomial. 42 graph of an odd degree polynomial. 43 graph of an odd degree polynomial. 44 graph of an equation. 45 graph of an odd degree polynomial, numeric. For the following exercises, make a table to confirm the end behavior of the function. 46 letter 1d453 letter 1d465 equals minus letter 1d465 3. 47 letter 1d453 letter 1d465 equals letter 1d465 4 minus 5 letter 1d465 2. 48 letter 1d453 letter 1d465 equals letter 1d465 2 1 minus letter 1d465 2. 49 letter 1d453 letter 1d465 equals letter 1d465 minus 1 letter 1d465 minus 2 3 minus letter 1d465. 50 letter 1d453 letter 1 d465 equals letter 1 d465 510 minus letter 1 d465 4. Technology. For the following exercises, graph the polynomial functions using a calculator. Based on the graph, determine the intercepts and the end behavior. 51. Letter 1 d453, letter 1 d465 equals letter 1 d465 3, letter 1 d465 minus 2. 52. Letter 1 d453, letter 1 d465 equals letter 1 d465, letter 1 d465 minus 3, letter 1 d465 plus 3. 53. Letter 1 d453, letter 1 d465 equals letter 1 d465, 14 minus 2 letter 1 d465, 10 minus 2 letter 1 d465. 54. Letter 1 d453, letter 1 d465 equals letter 1 d465, 14 minus 2 letter 1 d465, 10 minus 2 letter 1 d465 2. 55. Letter 1 d453, letter 1 d465 equals letter 1 d465, 3 minus 16 letter 1 d465. 56. Letter 1 d453, letter 1 d465 equals letter 1 d465, 3 minus 27. 57. Letter 1 d453, letter 1 d465 equals letter 1 d465, 4 minus 81. 58. Letter 1 d453, letter 1 d465 equals minus letter 1 d465, 3 plus letter 1 d465, 2 plus 2 letter 1 d465. 59. Letter 1 d453, letter 1 d465 equals letter 1 d465, 3 minus 2 letter 1 d465, 2 minus 15 letter 1 d465. 60. Letter 1 d453, letter 1 d465 equals letter 1 d465, 3 minus 0. Extensions. For the following exercises, use the information about the graph of a polynomial function to determine the function. Assume the leading coefficient is 1 or 1. There may be more than one correct answer. 61. The letter 1 d466. Intercept is 0 minus 4. The letter 1 d465. Intercepts are minus 2, 0. At 20. Degree is 2. End behavior. As letter 1 d465 right minus infinity. Letter 1 d453, letter 1 d465, right infinity. As letter 1 d465 right infinity. Letter 1 d453, letter 1 d465, right infinity. 62. The letter 1 d466. Intercept is 9. The letter 1 d465. Intercepts are minus 3, 0. 30. Degree is 2. End behavior. As letter 1 d465, right minus infinity. Letter 1 d453, letter 1 d465, right minus infinity. As letter 1 d465, right infinity. Letter 1 d453, letter 1 d465, right minus infinity. 63. The letter 1 d466. Intercept is 0. The letter 1 d465. Intercepts are 0. 20. Degree is 3. End behavior. As letter 1 d465, right minus infinity. Letter 1 d453, letter 1 d465, right minus infinity. As letter 1 d465, right infinity. Letter 1 d453, letter 1 d465, right infinity. 64. The letter 1 d466. Intercept is 1. The letter 1 d465. Intercept is 10. Degree is 3. End behavior. As letter 1 d465, right minus infinity. Letter 1 d453, letter 1 d465, right infinity. As letter 1 d465, right infinity. Letter 1 d453, letter 1 d465, right minus infinity. 65. The letter 1 d466. Intercept is 1. There is no letter 1 d465. Intercept, degree is 4. End behavior. As letter 1 d465, right minus infinity. Letter 1 d453, letter 1 d465, right infinity. As letter 1 d465, right infinity. Letter 1 d453, letter 1 d465, right infinity. Real-world applications. For the following exercises, use the written statements to construct a polynomial function that represents the required information. 66. An oil slick is expanding as a circle. The radius of the circle is increasing at the rate of 20 meters per day. Express the area of the circle as a function of letter 1 d451. The number of days elapsed. 67. A cube has an edge of 3 feet. The edge is increasing at the rate of 2 feet per minute. Express the volume of the cube as a function of letter 1d45a. The number of minutes elapsed, 68. A rectangle has a length of 10 inches and a width of 6 inches. If the length is increased by letter 1d465 inches and the width increased by twice that amount, express the area of the rectangle as a function of letter 1d465. 69. An open box is to be constructed by cutting out square corners of letter 1d465 inch sides from a piece of cardboard 8 inches by 8 inches and then folding up the sides. Express the volume of the box as a function of letter 1d465. 70. A rectangle is twice as long as it is wide. Squares of side 2 feet are cut out from each corner. Then the sides are folded up to make an open box. Express the volume of the box as a function of the width, letter 1d465. Learning objectives. In this section, you will recognize characteristics of graphs of polynomial functions. Use factoring to find zeros of polynomial functions. Identify zeros and their multiplicities. Determine end behavior. Understand the relationship between degree and turning points. Graph polynomial functions. Use the intermediate value theorem. The revenue in millions of dollars for a fictional cable company from 2006 through 2013 is shown in Table 1. Year 2006-2007, 2008, 2009, 2010, 2011, 2012, 2013. Revenues 52, 452, 851, 249, 548, 648, 648, 747, 1. Table 1. The revenue can be modeled by the polynomial function. Letter 1d445, letter 1d461 equals minus 0. 37t4 plus 1. 414 letter 1d461 3 minus 19. 777t2 plus 118. 696 letter 1d461 minus 205. 332. Where R represents the revenue in millions of dollars and T represents the year with corresponding to 2006, over which intervals is the revenue for the company increasing, over which intervals is the revenue for the company decreasing. These questions, along with many others, can be answered by examining the graph of the polynomial function. We have already explored the local behavior of quadratics, a special case of polynomials. In this section, we will explore the local behavior of polynomials in general. Recognizing characteristics of graphs of polynomial functions. Polynomial functions of degree 2 or more have graphs that do not have sharp corners. Recall that these types of graphs are called smooth curves. Polynomial functions also display graphs that have no breaks. Curves with no breaks are called continuous. Figure 1 shows a graph that represents a polynomial function and a graph that represents a function that is not a polynomial. Graph of f(x) equals x3-0, 1x, figure 1. Example 1. Recognizing polynomial functions. Which of the graphs in figure 2 represents a polynomial function? Two graphs in which one has a polynomial function and the other has a function closely resembling a polynomial but is not. Figure 2. Solution. The graphs of f and are graphs of polynomial functions. They are smooth and continuous. The graphs of g and k are graphs of functions that are not polynomials. The graph of function g has a sharp corner. The graph of function k is not continuous, q and a. Do all polynomial functions have as their domain all real numbers? Yes, any real number is a valid input for a polynomial function. Using factoring to find zeros of polynomial functions. Recall that if f is a polynomial function, the values of x, for which letter 1d453, letter 1d465 equals 0, are called zeros of f. If the equation of the polynomial function can be factored, we can set each factor equal to 0 and solve for the zeros. We can use this method to find x intercepts because at the x intercepts, we find the input values when the output value is 0. For general polynomials, this can be a challenging prospect. While quadratics can be solved using the relatively simple quadratic formula, the corresponding formulas for cubic and fourth-degree polynomials are not simple enough to remember, and formulas do not exist for general higher-degree polynomials. Consequently, we will limit ourselves to 3 cases. The polynomial can be factored using known methods, greatest common factor, and trinomial factoring. The polynomial is given in factored form. Technology is used to determine the intercepts. How to? Given a polynomial function f, find the x-intercepts by factoring. Set letter 1 d453, letter 1 d465 equals 0. If the polynomial function is not given in factored form, factor out any common monomial factors. Factor any factorable binomials or trinomials. Set each factor equal to 0 and solve to find the x. Intercepts. Example 2. Finding the x-intercepts of a polynomial function by factoring. Find the x-intercepts of letter 1 d453, letter 1 d465, equals letter 1 d465 6 minus 3, letter 1 d465 4, plus 2 letter 1 d465 2. Solution. We can attempt to factor this polynomial to find solutions for letter 1 d453, letter 1 d465, equals 0. Letter 1 d465 6 minus 3, letter 1 d465 4, plus 2 letter 1 d465 to letter 1 d465 2. Letter 1 d465 4 minus 3 letter 1 d465 2, plus 2 letter 1 d465 2 letter 1 d465 2 minus 1. Letter 1 d465 2 minus 2 equals 0 0 0. Factor out the greatest common factor. Factor the trinomial. Set each factor equal to 0. X to letter 1 d465 equals 0 0. Or letter 1 d465 2 minus 1 letter 1 d465 to letter 1 d465 equals 0 1 plus or minus 1. Or letter 1 d465 2 minus 2 letter 1 d465 to letter 1 d465 equals 0 2 plus or minus 2 square. This gives us 5 x-intercepts: 0 0 1 0 minus 1 0 2 square 0 and minus 2 square 0. See figure 3. We can see that this is an even function because it is symmetric about the y-axis. For graphs where the first graph is of an even degree polynomial, the second graph is of an absolute function, the third graph is an odd degree polynomial, and the fourth graph is a disjoint function. Figure 3. Example 3. Finding the x-intercepts of a polynomial function by factoring. Find the x-intercepts of letter 1 d453, letter 1 d465, equals letter 1 d465 3 minus 5, letter 1 d465 2 minus letter 1 d465 plus 5. Solution. Find solutions for letter 1 d453, letter 1 d465 equals 0. By factoring. Letter 1 d465 3 minus 5 letter 1 d465 2 minus letter 1 d465 plus 5 letter 1 d465 2, letter 1 d465 minus 5 minus, letter 1 d465 minus 5. Letter 1 d465 2 minus 1, letter 1 d465 minus 5, letter 1 d465 plus 1, letter 1 d465 minus 1, letter 1 d465 minus 5, equals 0 0 0 0. Factor by grouping. Factor out the common factor. Factor the difference of squares. Set each factor equal to 0. Letter 1 d465 plus 1 letter 1 d465 equals 0 minus 1 0 r letter 1 d465 minus 1 letter 1 d465 equals 0 1 0 r letter 1 d465 minus 5 letter 1 d465 equals 0 5. There are 3 x-intercepts, minus 1 0, 1 0, and 50. See figure 4. Graph of f(x) equals x6 3x4 plus 2x2 with its 5 intercepts, sqrt2 0, minus 1 0, 0 0, 1 0, and sqrt2 0. Figure 4. Example 4. Finding the y and x-intercepts of a polynomial in factored form. Find the y and x-intercepts of letter 1 d454, letter 1 d465 equals letter 1 d465 minus 2 2, 2 letter 1 d465 plus 3. Solution. The y-intercept can be found by evaluating letter 1 d454 0. Letter 1 d454 0 equals 0 minus 2, 2, 2, 0, plus 3 12. So the y-intercept is 12. The x-intercepts can be found by solving letter 1 d454. Letter 1 d465 equals 0. Letter 1 d465 minus 2, 2, 2 letter 1 d465 plus 3 equals 0. Letter 1 d465 minus 2, 2 letter 1 d465 minus 2 letter 1 d465 equals 0 0 2 or 2 letter 1 d465 plus 3. letter 1d465 equals 0 minus 32. So the x-intercepts are 2, 0, and minus 32, 0. Analysis. We can always check that our answers are reasonable by using a graphing calculator to graph the polynomial as shown in Figure 5. Graph of f, x equals x3-5x2x plus 5 with its three intercepts, minus 1, 0, 1, 0, and 5, 0. Figure 5. Example 5. Finding the x-intercepts of a polynomial function using a graph. Find the x-intercepts of letter 210e. Letter 1d465 equals letter 1d465 3 plus 4 letter 1d465 2 plus letter 1d465 minus 6. Solution. This polynomial is not in factored form, has no common factors, and does not appear to be factorable using techniques previously discussed. Fortunately, we can use technology to find the intercepts. Keep in mind that some values make graphing difficult by hand. In these cases, we can take advantage of graphing utilities. Looking at the graph of this function, as shown in Figure 6, it appears that there are x-intercepts at letter 1d465 equals minus 3, minus 2, and 1. Graph of g, x equals x22, 2x plus 3 with its two x-intercepts 2, 0 and minus 3, 2, 0 and its y-intercept 0, 12. Figure 6. We can check whether these are correct by substituting these values for x and verifying that letter 210e minus 3 equals letter 210e, minus 2 equals letter 210e, 1 equals 0. Since letter 210e, letter 1d465, equals letter 1d465 3 plus 4 letter 1d465 2 plus letter 1d465 minus 6. We have letter 210e, minus 3 letter 210e, minus 2 letter 210e, 1 equals, minus 3 3 plus 4 minus 3 2 plus, minus 3 minus 6 equals minus 27 plus 36 minus 3 minus 6 equals 0, minus 2 3 plus 4, minus 2 2 plus, minus 2 minus 6 equals minus 8 plus 16 minus 2 minus 6 equals 0, 1 3 plus 4, 1 2 plus, 1 minus 6 equals 1 plus 4 plus 1. Each x-intercept corresponds to a 0 of the polynomial function, and each 0 yields a factor. So we can now write the polynomial in factored form. Letter 210e. Letter 1d465 equals letter 1d465 3 plus 4 letter 1d465 2 plus letter 1d465 minus 6. Letter 1d465 plus 3 letter 1d465 plus 2. Letter 1d465 minus 1. Try it 1. Find the y and x-intercepts of the function letter 1d453. Letter 1d465 equals letter 1d465 4 minus 19 letter 1d465 2 plus 30 letter 1d465. Identifying zeros and their multiplicities. Graphs behave differently at various x-intercepts. Sometimes, the graph will cross over the horizontal axis at an intercept. Other times, the graph will touch the horizontal axis and bounce off. Suppose, for example, we graph the function shown. Letter 1d453, letter 1d465 equals letter 1d465 plus 3, letter 1d465 minus 2 letter 1d465 plus 1 3. Notice in Figure 7 that the behavior of the function at each of the x-intercepts is different. Graph of h, x equals x3 plus 4x2 plus x6. Figure 7 identifying the behavior of the graph at an x-intercept by examining the multiplicity of the 0. The x-intercept, letter 1d465 equals minus 3, is the solution of equation, letter 1d465 plus 3 equals 0. The graph passes directly through the x-intercept at letter 1d465 equals minus 3. The factor is linear, has a degree of 1, so the behavior near the intercept is like that of a line. It passes directly through the intercept. We call this a single 0 because the 0 corresponds to a single factor of the function. The x-intercept letter 1d465 equals 2 is the repeated solution of equation letter 1d465 minus 2 equals 0. The graph touches the axis at the intercept and changes direction. The factor is quadratic, degree 2, so the behavior near the intercept is like that of a quadratic. It bounces off of the horizontal axis at the intercept. Letter 1d465 minus 2 equals letter 1d465 minus 2, letter 1d465 minus 2. The factor is repeated, that is, the factor, letter 1d465 minus 2, appears twice. The number of times a given factor appears in the factored form of the equation of a polynomial is called the multiplicity. The 0 associated with this factor, letter 1d465 equals 2, has multiplicity 2 because the factor, letter 1d465 minus 2, occurs twice. The x-intercept, letter 1d465 equals minus 1, is the repeated solution of factor, letter 1d465 plus 1, 3 equals 0. The graph passes through the axis at the intercept, but flattens out a bit first. This factor is cubic, degree 3, so the behavior near the intercept is like that of a cubic, with the same S-shape near the intercept as the toolkit function letter 1d453, letter 1d465, equals letter 1d4653. We call this a triple zero, or a zero with multiplicity 3. For zeros with even multiplicities, the graphs touch or are tangent to the x-axis. For zeros with odd multiplicities, the graphs cross or intersect the x-axis. See Figure 8 for examples of graphs of polynomial functions with multiplicity 1, 2, and 3. Graph of f, x equals x plus 3, x2, 2, x plus 1, 3. Figure 8. For higher even powers, such as 4, 6, and 8, the graph will still touch and bounce off of the horizontal axis, but for each increasing even power, the graph will appear flatter as it approaches and leaves the x-axis. For higher odd powers, such as 5, 7, and 9, the graph will still cross through the horizontal axis, but for each increasing odd power, the graph will appear flatter as it approaches and leaves the x-axis. Graphical behavior of polynomials at x-intercepts. If a polynomial contains a factor of the form, letter 1d465 minus letter 210e, letter 1d45d, the behavior near the x-intercept h is determined by the power p. We say that letter 1d465 equals letter 210e is a zero of multiplicity. The graph of a polynomial function will touch the x-axis at zeros with even multiplicities. The graph will cross the x-axis at zeros with odd multiplicities. The sum of the multiplicities is the degree of the polynomial function. How to? Given a graph of a polynomial function of degree n, identify the zeros and their multiplicities. If the graph crosses the x-axis and appears almost linear at the intercept, it is a single zero. If the graph touches the x-axis and bounces off of the axis, it is a zero with even multiplicity. If the graph crosses the x-axis at a zero, it is a zero with odd multiplicity. The sum of the multiplicities is less or equal to letter 1d45b. Example 6. Identifying zeros and their multiplicities. Use the graph of the function of degree 6 in Figure 9 to identify the zeros of the function and their possible multiplicities. 3 graphs showing 3 different polynomial functions with multiplicity 1, 2, and 3. Figure 9. Solution. The polynomial function is of degree 6. The sum of the multiplicities must be 6. Starting from the left, the first zero occurs at letter 1d465 equals minus 3. The graph touches the x-axis, so the multiplicity of the zero must be even. The zero of minus 3 most likely has multiplicity 2. The next zero occurs at letter 1d465 equals minus 1. The graph looks almost linear at this point. This is a single zero of multiplicity 1. The last zero occurs at letter 1d465 equals 4. The graph crosses the x-axis, so the multiplicity of the zero must be odd. We know that the multiplicity is likely 3 and that the sum of the multiplicities is 6. Try it too. Use the graph of the function of degree 9 in Figure 10 to identify the zeros of the function and their multiplicities. Graph of an even degree polynomial with degree 6. Figure 10. Determining end behavior. As we have already learned, the behavior of a graph of a polynomial function of the form letter 1d453, letter 1d465 equals letter 1d44, letter 1d45b, letter 1d465, letter 1d45b, plus letter 1d44, letter 1d45b minus 1, letter 1d465, letter 1d45b minus 1 plus a1x plus a0 will either ultimately rise or fall as x, increases without bound, and will either rise or fall as x, decreases without bound. This is because for very large inputs, say 100 or 1000, the leading term dominates the size of the output. The same is true for very small inputs, say 100 or 1000. Recall that we call this behavior the end behavior of a function. As we pointed out when discussing quadratic equations, when the leading term of a polynomial function, letter 1d44e, letter 1d45b, letter 1d465, letter 1d45b, is an even power function, as x increases or decreases without bound, letter 1d453, letter 1d465, increases without bound, when the leading term is an odd power function, as x decreases without bound, letter 1d453, letter 1d465, also decreases without bound, as x increases without bound, letter 1d453, letter 1d465, also increases without bound. If the leading term is negative, it will change the direction of the end behavior. Figure 11 summarizes all four cases. Graph of a polynomial function with degree 5. Figure 11. Understanding the relationship between degree and turning points. In addition to the end behavior, recall that we can analyze a polynomial function's local behavior. It may have a turning point where the graph changes from increasing to decreasing, rising to falling, or decreasing to increasing, falling to rising. Look at the graph of the polynomial function, letter 1d453. Letter 1d465 equals letter 1d465, 4 minus letter 1d465, 3 minus 4 letter 1d465, 2, plus 4 letter 1d465. In figure 12, the graph has three turning points. Graph of an odd degree polynomial with a negative leading coefficient. Note that as x goes to positive infinity, fx goes to negative infinity, and as x goes to negative infinity, fx goes to positive infinity. Figure 12, this function f is a fourth degree polynomial function and has three turning points. The maximum number of turning points of a polynomial function is always one less than the degree of the function. Interpreting turning points, a turning point is a point of the graph where the graph changes from increasing to decreasing, rising to falling, or decreasing to increasing, falling to rising. A polynomial of degree n will have at most letter 1d45b minus 1. Turning points, example 7, finding the maximum number of turning points using the degree of a polynomial function. Find the maximum number of turning points of each polynomial function. A letter 1d453, letter 1d465, equals minus letter 1d465, 3, plus 4 letter 1d465, 5 minus 3 letter 1d465, 2, plus 1. B letter 1d453, letter 1d465 equals minus letter 1d465 minus 1, 2, 1 plus 2 letter 1d465, 2. Solution. First, rewrite the polynomial function in descending order. Letter 1d453, letter 1d465, equals 4 letter 1d465, 5 minus letter 1d465, 3 minus 3 letter 1d465, 2, plus 1. Identify the degree of the polynomial function. This polynomial function is of degree 5. The maximum number of turning points is 5 minus 1 equals 4. B. First, identify the leading term of the polynomial function if the function were expanded. Graph of f, x, equals x4x3-4x2 plus 4x, which denotes where the function increases and decreases and its turning points. Then, identify the degree of the polynomial function. This polynomial function is of degree 4. The maximum number of turning points is 4 minus 1 equals 3. Graphing polynomial functions. We can use what we have learned about multiplicities, end behavior, and turning points to sketch graphs of polynomial functions. Let us put this all together and look at the steps required to graph polynomial functions. How to. Given a polynomial function, sketch the graph, find the intercepts, check for symmetry. If the function is an even function, its graph is symmetrical about the y-axis, that is, letter 1d453 minus letter 1d465 equals letter 1d453, letter 1d465. If a function is an odd function, its graph is symmetrical about the origin. That is, letter 1d453 minus letter 1d465 equals minus letter 1d453, letter 1d465. Use the multiplicities of the zeros to determine the behavior of the polynomial at the x-intercepts. Determine the end behavior by examining the leading term. Use the end behavior and the behavior at the intercepts to sketch a graph. Ensure that the number of turning points does not exceed one less than the degree of the polynomial. Optionally, use technology to check the graph. Example 8. Sketching the graph of a polynomial function. Sketch a graph of letter 1d453. Letter 1d465 equals -2, letter 1d465 plus 3, 2, letter 1d465 minus 5. Solution. This graph has two x-intercepts. At letter 1d465 equals -3. The factor is squared, indicating a multiplicity of 2. The graph will bounce at this x-intercept. At letter 1d465 equals 5. The function has a multiplicity of 1, indicating the graph will cross through the axis at this intercept. The y-intercept is found by evaluating letter 1d453, 0. Letter 1d453, 0 equals -2, 0 plus 3, 2, 0 minus 5 minus 2, 9, minus 5, 90. The y-intercept is 90. Additionally, we can see the leading term, if this polynomial were multiplied out, would be -2 letter 1d4653. So the end behavior is that of a vertically reflected cubic, with the outputs decreasing as the inputs approach infinity, and the outputs increasing as the inputs approach negative infinity. See Figure 13, showing the distribution for the leading term, Figure 13. To sketch this, we consider that, as letter 1d465 right minus infinity, the function letter 1d453, letter 1d465, right infinity. So we know the graph starts in the second quadrant and is decreasing toward the x-axis, since letter 1d453 minus letter 1d465 equals -2, minus letter 1d465 plus 3, 2, minus letter 1d465, 5, is not equal to letter 1d453, letter 1d465. The graph does not display symmetry. At -3, 0, the graph bounces off of the x-axis, so the function must start increasing. At 90, the graph crosses the y-axis at the y-intercept. See Figure 14. Graph of the end behavior and intercepts, -3, 0, and 0, 90, for the function f(x) equals 2, x plus 3, 2x 5. Figure 14. Somewhere after this point, the graph must turn back down or start decreasing toward the horizontal axis, because the graph passes through the next intercept at 50. See Figure 15. Graph of the end behavior and intercepts, -3, 0, 0, 90, and 5, 0, for the function f(x) equals 2, x plus 3, 2, x 5. Figure 15. As letter 1d465 right infinity, the function letter 1d453, letter 1d465, right minus infinity. So we know the graph continues to decrease, and we can stop drawing the graph in the fourth quadrant. Using technology, we can create the graph for the polynomial function, shown in Figure 16, and verify that the resulting graph looks like our sketch in Figure 15. Graph of f(x) equals 2, x plus 3, 2x 5. Figure 16, the complete graph of the polynomial function, letter 1d453, letter 1d465, equals -2, letter 1d465 plus 3, 2, letter 1d465 minus 5. Try it 3. Sketch a graph of letter 1d453, letter 1d465 equals 14 letter 1d465, letter 1d465 minus 1, 4, letter 1d465 plus 3, 3. Using the intermediate value theorem. In some situations, we may know 2 points on a graph but not the zeros. If those 2 points are on opposite sides of the x-axis, we can confirm that there is a 0 between them. Consider a polynomial function f, whose graph is smooth and continuous. The intermediate value theorem states that for two numbers a and b, in the domain of f, if letter 1d44e, letter 1d44f, and letter 1d453, letter 1d44e not equal to letter 1d453, letter 1d44f, then the function f takes on every value between letter 1d453, letter 1d44e, and letter 1d453, letter 1d44f. While the theorem is intuitive, the proof is actually quite complicated and requires higher mathematics. We can apply this theorem to a special case that is useful in graphing polynomial functions. If a point on the graph of a continuous function, f, at letter 1d465 equals letter 1d44e, lies above the x-axis, and another point at letter 1d465 equals letter 1d44f, lies below the x-axis, there must exist a third point between letter 1d465 equals letter 1d44e, and letter 1d465 equals letter 1d44f, where the graph crosses the x-axis. Call this point letter 1d450, letter 1d453, letter 1d450. This means that we are assured there is a solution C, where letter 1d453, letter 1d450 equals 0. In other words, the intermediate value theorem tells us that when a polynomial function changes from a negative value to a positive value, the function must cross the x-axis. Figure 17 shows that there is a 0 between a and b graph of an odd-degree polynomial function that shows a point f. A, that's negative, f, b, that's positive, and f, c, that's 0. Figure 17 using the intermediate value theorem to show there exists a 0. Intermediate value theorem. Let f be a polynomial function. The intermediate value theorem states that if letter 1d453, letter 1d44e, and letter 1d453, letter 1d44f have opposite signs, then there exists at least one value C between a and b, for which letter 1d453, letter 1d450 equals 0. Example 9. Using the intermediate value theorem, show that the function letter 1d453, letter 1d465 equals letter 1d465 3 minus 5, letter 1d465 2, plus 3 letter 1d465 plus 6, has at least two real zeros between letter 1d465 equals 1 and letter 1d465 equals 4. Solution. As a start, evaluate letter 1d453, letter 1d465. At the integer values letter 1d465 equals 1, 2, 3, and 4. See Table 2. X, 1, 2, 3, 4. Letter 1d453, letter 1d465. 5, 0, 3, 2. Table 2. We see that 1, 0 occurs at letter 1d465 equals 2. Also, since letter 1d453, 3, is negative and letter 1d453, 4, is positive by the intermediate value theorem, there must be at least one real 0 between 3 and 4. We have shown that there are at least two real zeros between letter 1d465 equals 1 and letter 1d465 equals 4. Analysis. We can also see on the graph of the function, in figure 18, that there are two real zeros between letter 1d465 equals 1 and letter 1d465 equals 4. Graph of f, x, equals x3-5x2 plus 3x plus 6 and shows by the intermediate value theorem that there exists two zeros since f, 1 equals 5 and f, 4, equals 2 are positive and f, 3 equals is negative. Figure 18. Try it 4. Show that the function letter 1d453, letter 1d465, equals 7 letter 1d465, 5 minus 9 letter 1d465, 4 minus letter 1d465, 2, has at least one real 0 between letter 1d465 equals 1 and letter 1d465 equals 2. Writing formulas for polynomial functions. Now that we know how to find zeros of polynomial functions, we can use them to write formulas based on graphs. Because a polynomial function written in factored form will have an x-intercept where each factor is equal to 0, we can form a function that will pass through a set of x-intercepts by introducing a corresponding set of factors. Factored form of polynomials. If a polynomial of degree p that can be factored into strictly linear factors has horizontal intercepts at letter 1d465 equals letter 1d465 1, letter 1d465 2, letter 1d465 letter 1d45b. Then the polynomial can be written in the factored form. Letter 1d453, letter 1d465 equals letter 1d44e, letter 1d465 minus letter 1d465 1, letter 1d45d 1, letter 1d465 minus letter 1d465 2, letter 1d45d 2, letter 1d465 minus letter 1d465 letter 1d45b, letter 1d45d letter 1d45b, where the powers pi on each factor can be determined by the behavior of the graph at the corresponding intercept, and the stretch factor a can be determined given a value of the function other than the x-intercept. How to, given a graph of a polynomial function, write a formula for the function. Identify the x-intercepts of the graph to find the factors of the polynomial. Examine the behavior of the graph at the x-intercepts to determine the multiplicity of each factor. find the polynomial of least degree containing all the factors found in the previous step. Use any other point on the graph. The y-intercept may be easiest to determine the stretch factor. Example 10. Writing a formula for a polynomial function from the graph. Write a formula for the polynomial function shown in Figure 19. Graph of a positive even degree polynomial with zeros at x equals 3, 2, 5, and y equals 2. Figure 19. Try it 5. Given the graph shown in Figure 20, write a formula for the function shown. Graph of a negative even degree polynomial with zeros at x equals 1, 2, 4, and y equals 4. Figure 20. Using local and global extrema. With quadratics, we were able to algebraically find the maximum or minimum value of the function by finding the vertex. For general polynomials, finding these turning points is not possible without more advanced techniques from calculus. Even then, finding where extrema occur can still be algebraically challenging. For now, we will estimate the locations of turning points using technology to generate a graph. Each turning point represents a local minimum or maximum. Sometimes, a turning point is the highest or lowest point on the entire graph. In these cases, we say that the turning point is a global maximum or a global minimum. These are also referred to as the absolute maximum and absolute minimum values of the function. Local and global extrema. A local maximum or local minimum at letter 1d465 equals letter 1d44e, sometimes called the relative maximum or minimum, respectively, is the output at the highest or lowest point on the graph in an open interval around letter 1d465 equals letter 1d44e. If a function has a local maximum at a, then letter 1d453, letter 1d44e greater or equal to letter 1d453, letter 1d465. For all x, in an open interval around letter 1d465 equals letter 1d44e. If a function has a local minimum at a, then letter 1d453, letter 1d44e, less or equal to letter 1d453, letter 1d465. For all x, in an open interval, around letter 1d465 equals letter 1d44e. A global maximum or global minimum is the output at the highest or lowest point of the function. If a function has a global maximum at a, then letter 1d453, letter 1d44e greater or equal to letter 1d453, letter 1d465. For all x, if a function has a global minimum at a, then letter 1d453, letter 1d44e, less or equal to letter 1d453, letter 1d465. For all x, we can see the difference between local and global extrema in Figure 21. Graph of an even degree polynomial that denotes the local maximum and minimum and the global maximum. Figure 21. Q&A. Do all polynomial functions have a global minimum or maximum? No. Only polynomial functions of even degree have a global minimum or maximum. For example, letter 1d453, letter 1d465 equals letter 1d465, has neither a global maximum nor a global minimum. Example 11. Using local extrema to solve applications. An open top box is to be constructed by cutting out squares from each corner of a 14 cm by 20 cm sheet of plastic, and then folding up the sides. Find the size of squares that should be cut out to maximize the volume enclosed by the box. Solution. We will start this problem by drawing a picture like that in Figure 22, labeling the width of the cutout squares with a variable, letter 1d464. Diagram of a rectangle with 4 squares at the corners. Figure 22. Notice that after a square is cut out from each end, it leaves a 14-2 letter 1d464. cm by 20-2 letter 1d464. cm rectangle for the base of the box, and the box will be letter 1d464. cm tall. This gives the volume. Letter 1d449. Letter 1d464 equals 20-2 letter 1d464. 14-2 letter 1d464. Letter 1d464, 280 letter 1d464, minus 68 letter 1d464, 2, plus 4 letter 1d464, 3. Notice, since the factors are letter 1d464, 22 letter 1d464, and 14 letter 1d464, the three zeros are 10, 7, and 0, respectively. Because a height of 0 cm is not reasonable, we consider only the zeros 10 and 7. The shortest side is 14, and we are cutting off 2 squares, so values letter 1d464 may take on are greater than 0 or less than 7. This means we will restrict the domain of this function to 0 letter 1d464, Using technology to sketch the graph of letter 1d449, letter 1d464. On this reasonable domain, we get a graph like that in figure 23. We can use this graph to estimate the maximum value for the volume, restricted to values for letter 1d464, that are reasonable for this problem, values from 0 to 7. Graph of V, W equals 20-2W, 14-2W, W where the x-axis is labeled W and the y-axis is labeled V, W. Figure 23. From this graph, we turn our focus to only the portion on the reasonable domain, 0, 7. We can estimate the maximum value to be around 340 cubic cm, which occurs when the squares are about 275 cm on each side. To improve this estimate, we could use advanced features of our technology, if available, or simply change our window to zoom in on our graph to produce figure 24. Graph of V, W equals 20-2W, 14-2W, W where the x-axis is labeled W and the y-axis is labeled V, W on the domain 2. 4, 3. Figure 24. From this zoomed-in view, we can refine our estimate for the maximum volume to about 339 cubic cm, when the squares measure approximately 27 cm on each side. Try it 6. Use technology to find the maximum and minimum values on the interval -1, 4, of the function letter 1d453, letter 1d465 equals -0, 2 letter 1d465 -2, 3, letter 1d465 plus 1, 2, letter 1d465 -4. Media. Access the following online resource for additional instruction and practice with graphing polynomial functions. Intermediate value theorem. 5-3 section exercises. Verbal. 1. What is the difference between in letter 1d465, intercept, and a 0 of a polynomial function letter 1d453? 2. If a polynomial function of degree, letter 1d45b, has letter 1d45b distinct zeros, what do you know about the graph of the function? 3. Explain how the intermediate value theorem can assist us in finding a 0 of a function. 4. Explain how the factored form of the polynomial helps us in graphing it. 5. If the graph of a polynomial just touches the x-axis and then changes direction, what can we conclude about the factored form of the polynomial? Algebraic. For the following exercises, find the letter 1d465, or t-intercepts of the polynomial functions. 6. Letter 1d436, letter 1d461 equals 2, letter 1d461 minus 4, letter 1d461 plus 1, letter 1d461 minus 6. 7. 8. Letter 1d436, letter 1d461 equals 4, letter 1d461, letter 1d461 minus 2, 2, letter 1d461 plus 1. 9. Letter 1d436, letter 1d461 equals 2, letter 1d461, letter 1d461 minus 3, letter 1d461 plus 1, 2. 10. Letter 1d436, letter 1d461 equals 2, letter 1d461, 4 minus 8, letter 1d461, 3, plus 6, letter 1d461, 2. 11. Letter 1d436, letter 1d461 equals 4, letter 1d461, 4, plus 12, letter 1d461, 3 minus 40, letter 1d461, 2. 12. Letter 1d453, letter 1d465 equals letter 1d465, 4 minus letter 1d465, 2. 13. Letter 1d453, letter 1d465 equals letter 1d465, 3 plus letter 1d465, 2 minus 20, letter 1d465. 14. Letter 1d453, letter 1d465 equals letter 1d465, 3 plus 6, letter 1d465, 2 minus 7, letter 1d465. 15. Letter 1d453, letter 1d465 equals letter 1d465, 3 plus letter 1d465, 2 minus 4, letter 1d465 minus 4. 16. Letter 1D453. Letter 1D465 equals letter 1D4653 plus 2 letter 1D465, 2 minus 9 letter 1D465 minus 18. 17. Letter 1D453. Letter 1D465 equals 2 letter 1D465, 3 minus letter 1D465, 2 minus 8 letter 1D465 plus 4. 18. Letter 1D453. Letter 1D465 equals letter 1D465, 6 minus 7, letter 1D465, 3 minus 8. 19. Letter 1D453. Letter 1D465 equals 2 letter 1D465, 4 plus 6, letter 1D465, 2 minus 8. 20. Letter 1D453. Letter 1D465 equals letter 1D465, 3 minus 3, letter 1D465, 2 minus letter 1D465 plus 3. 21. Letter 1D453. Letter 1D465 equals letter 1D465, 6 minus 2, letter 1D465, 4 minus 3, letter 1D465, 2. 22. Letter 1D453. Letter 1D465 equals letter 1D465, 6 minus 3, letter 1D465, 4 minus 4, letter 1D465, 2. 23. Letter 1D453. Letter 1D465 equals letter 1D465, 5 minus 5, letter 1D465, 3 plus 4, letter 1D465. For the following exercises, use the intermediate value theorem to confirm that the given polynomial has at least one zero within the given interval. 24. Letter 1D453, letter 1D465 equals letter 1D465, 3 minus 9, letter 1D465. Between letter 1D465 equals minus 4, and letter 1D465 equals minus 2. 25. Letter 1D453, letter 1D465 equals letter 1D465, 3 minus 9, letter 1D465. Between letter 1D465 equals 2, and letter 1D465 equals 4. 26. Letter 1D453, letter 1D465 equals letter 1D465, 5 minus 2, letter 1D465. Between letter 1D465 equals, and letter 1D465 equals 2. 27. Letter 1D453, letter 1D465 equals minus letter 1D465, 4 plus 4. Between letter 1D465 equals, and letter 1D465 equals 3. 28. Letter 1D453, letter 1D465 equals minus 2, letter 1D465, 3 minus letter 1D465. Between letter 1D465 equals, and letter 1D465 equals 1. 29. Letter 1D453, letter 1D465 equals letter 1D465, 3 minus 100, letter 1D465 plus 2. Between 1 and letter 1D465 equals 0, 1. For the following exercises, find the zeros and give the multiplicity of each. 30. Letter 1D453, letter 1D465 equals letter 1D465 plus 2, 3, letter 1D465 minus 3, 2. 31. Letter 1D453, letter 1D465 equals letter 1D465, 2, 2, letter 1D465 plus 3, 5, letter 1D465 minus 4, 2. 32. Letter 1D453, letter 1D465 equals letter 1D465, 3, letter 1D465 minus 1, 3, letter 1D465 plus 2. 33. Letter 1D453, letter 1D465 equals letter 1D465, 2, letter 1D465, 2, plus 4, letter 1D465 plus 4. 34. 35. Letter 1D453, letter 1D465 equals 3, letter 1D465 plus 2, 5, letter 1D465, 2 minus 10, letter 1D465 plus 25. 36. Letter 1D453, letter 1D465 equals letter 1D465, 4, letter 1D465, 2 minus 12, letter 1D465 plus 9. Letter 1D465, 2 plus 8, letter 1D465 plus 16. 37. Letter 1D453, letter 1D465 equals letter 1D465, 6 minus letter 1D465, 5 minus 2, letter 1D465, 4. 38. Letter 1D453, letter 1D465 equals 3 letter 1d465, 4 plus 6 letter 1d465, 3 plus 3 letter 1d465, 2. 39. Letter 1d453, letter 1d465, equals 4 letter 1d465, 5 minus 12 letter 1d465, 4 plus 9 letter 1d465, 3. 40. Letter 1d453, letter 1d465, equals 2 letter 1d465, 4 letter 1d465, 3 minus 4 letter 1d465, 2 plus 4 letter 1d465. 41. Letter 1d453, letter 1d465, equals 4 letter 1d465, 4, 9 letter 1d465, 4 minus 12 letter 1d465, 3 plus 4 letter 1d465, 2. Graphic. For the following exercises, graph the polynomial functions. Note letter 1d465 and letter 1d466, intercepts, multiplicity, and end behavior. 42. Letter 1d453, letter 1d465 equals letter 1d465 plus 3, 2, letter 1d465 minus 2. 43. Letter 1d454, letter 1d465 equals letter 1d465 plus 4, letter 1d465 minus 1, 2. 44. Letter 210e, letter 1d465 equals letter 1d465 minus 1, 3, letter 1d465 plus 3, 2. 45. Letter 1d458, letter 1d465 equals letter 1d465 minus 3, 3, letter 1d465 minus 2, 2. 46. Letter 1d45a, letter 1d465 equals minus 2 letter 1d465, letter 1d465 minus 1, letter 1d465 plus 3. 47. Letter 1d45b, letter 1d465 equals minus 3 letter 1d465, letter 1d465 plus 2, letter 1d465 minus 4. For the following exercises, use the graphs to write the formula for a polynomial function of least degree. 48. Graph of a positive odd degree polynomial with zeros at x equals 2, 1, and 349. Graph of a negative odd degree polynomial with zeros at x equals 3, 1, and 350. Graph of a negative odd degree polynomial with zeros at x equals 1 and 251. Graph of a positive odd degree polynomial with zeros at x equals 2 and 352. Graph of a negative even degree polynomial with zeros at x equals 3, minus 2, 3, and 4. For the following exercises, use the graph to identify zeros and multiplicity. 53. Graph of a negative even degree polynomial with zeros at x equals 4, minus 2, 1, and 354. Graph of a positive even degree polynomial with zeros at x equals 4, minus 2, and 3. 55. Graph of a positive even degree polynomial with zeros at x equals 2 and 356. Graph of a negative odd degree polynomial with zeros at x equals 3, minus 2, and 1. For the following exercises, use the given information about the polynomial graph to write the equation. 57. Degree 3. Zeros at letter 1d465 equals 2. Letter 1d465 equals 1. And y-intercept at 0, 4. 58. Degree 3. Zeros at letter 1d465 equals 5. Letter 1d465 equals 2. And letter 1d465 equals 1. Y-intercept at 6. 59. Degree 5. Roots of multiplicity 2 at. And letter 1d465 equals 1. And a root of multiplicity 1 at letter 1d465 equals 3. Y-intercept at 9. 60. Degree 4. Root of multiplicity 2 at. And a roots of multiplicity 1 at. And letter 1d465 equals 2. Y-intercept at 0, 3. 61. Degree 5. Double 0 at letter 1d465 equals 1. And triple 0 at letter 1d465 equals 3. Passes through the point 215. 62. Degree 3. Zeros at letter 1d465 equals 4. And letter 1d465 equals 2. Y-intercept at 0 minus 24. 63. Degree 3. Zeros at letter 1d465 equals minus 3. Letter 1d465 equals minus 2. And letter 1d465 equals 1. Y-intercept at 12. 64. Degree 5. Roots of multiplicity 2 at letter 1d465 equals minus 3. And letter 1d465 equals 2. and a root of multiplicity, 1, at letter 1 d465 equals minus 2. Y-intercept at 0, 4, 65, degree 4. Roots of multiplicity 2 at letter 1 d465 equals 12, and roots of multiplicity 1 at letter 1 d465 equals 6, and letter 1 d465 equals minus 2. Y-intercept at 18, 66, double 0 at letter 1 d465 equals minus 3, and triple 0 at letter 1 d465 equals 0. Passes through the point 132. Technology. For the following exercises, use a calculator to approximate local minima and maxima, or the global minimum and maximum 67. Letter 1 d453. Letter 1 d465 equals letter 1 d465 3 minus letter 1 d465 minus 1. 68. Letter 1 d453. Letter 1 d465 equals 2 letter 1 d465 3 minus 3 letter 1 d465 minus 1. 69. Letter 1 d453. Letter 1 d465 equals letter 1 d465 4 plus letter 1 d465. 70. Letter 1 d453. Letter 1 d465 equals minus letter 1 d465 4 plus 3 letter 1 d465 minus 2. 71. Letter 1 d453. Letter 1 d465 equals letter 1 d465 4 minus letter 1 d465 3 plus 1. Extensions. For the following exercises, use the graphs to write a polynomial function of least degree. 72. Graph of a positive odd degree polynomial with zeros at x equals 2/3 and 4, 3 and y equals 8. 73. Graph of a positive odd degree polynomial with zeros at x equals 200 and 500 and y equals 50 million. 74. Graph of a positive odd degree polynomial with zeros at x equals 300 and 100 and y equals 90,000. Real-world applications. For the following exercises, write the polynomial function that models the given situation. 75. A rectangle has a length of 10 units and a width of 8 units. Squares of letter 1 d465. By letter 1 d465, units are cut out of each corner, and then the sides are folded up to create an open box. Express the volume of the box as a polynomial function in terms of letter 1 d465. 76. Consider the same rectangle of the preceding problem. Squares of 2 letter 1 d465. By 2 letter 1 d465, units are cut out of each corner. Express the volume of the box as a polynomial in terms of letter 1 d465. 77. A square has sides of 12 units. Squares letter 1 d465 plus 1. By letter 1 d465 plus 1, units are cut out of each corner, and then the sides are folded up to create an open box. Express the volume of the box as a function in terms of letter 1 d465. 78. A cylinder has a radius of letter 1 d465 plus 2 units and a height of 3 units greater. Express the volume of the cylinder as a polynomial function. 79. A right circular cone has a radius of 3 letter 1 d465 plus 6 and a height 3 units less. Express the volume of the cone as a polynomial function. The volume of a cone is letter 1 d449 equals 13 letter 1 d70 b letter 1 d45f to h, for radius letter 1 d45f, and height letter 210e. Learning objectives in this section, you will use long division to divide polynomials. Use synthetic division to divide polynomials. Lincoln Memorial. Figure 1 Lincoln Memorial, Washington, D.C., credit. Ron Cogswell, Flickr. The exterior of the Lincoln Memorial in Washington, D.C., is a large rectangular solid with length 61. 5 meters m, width 40 m, and height 30 m. 1. We can easily find the volume using elementary geometry. Letter 1 d449 equals letter 1 d459, letter 1 d464, letter 210e, 61. 543,073, 800, so the volume is 73,800 cubic meters, m3. Suppose we knew the volume, length, and width. We could divide to find the height. Letter 210e equals letter 1 d449, letter 1 d459, letter 1 d464, 73. 80,061. 4,030, as we can confirm from the dimensions above, the height is 30 m, we can use similar methods to find any of the missing dimensions. We can also use the same method if any, or all, of the measurements contain variable expressions. For example, suppose the volume of a rectangular solid is given by the polynomial 3 letter 1d465, 4 minus 3 letter 1d465, 3 minus 33 letter 1d465, 2 plus 54 letter 1d465. The length of the solid is given by 3x. The width is given by letter 1d465 minus 2. To find the height of the solid, we can use polynomial division, which is the focus of this section. Using long division to divide polynomials, we are familiar with the long division algorithm for ordinary arithmetic. We begin by dividing into the digits of the dividend that have the greatest place value. We divide, multiply, subtract, include the digit in the next place value position, and repeat. For example, let's divide 178 by 3 using long division. Steps of long division for integers. Another way to look at the solution is as a sum of parts. This should look familiar, since it is the same method used to check division in elementary arithmetic. Dividend 178 equals divisor quotient plus remainder 359 plus 1177 plus 1178. We call this the division algorithm, and we'll discuss it more formally after looking at an example. Division of polynomials that contain more than one term has similarities to long division of whole numbers. We can write a polynomial dividend as the product of the divisor and the quotient added to the remainder. The terms of the polynomial division correspond to the digits and place values of the whole number division. This method allows us to divide two polynomials. For example, if we were to divide 2 letter 1d465 3 minus 3 letter 1d465 2 plus 4 letter 1d465 plus 5 by x plus 2 using the long division algorithm, it would look like this. We have found 2 letter 1d465 3 minus 3 letter 1d465 2 plus 4 letter 1d465 plus 5 letter 1d465 plus 2 equals 2 letter 1d465 2 minus 7 letter 1d465 plus 18 minus 31 letter 1d465 plus 2. 2 letter 1d465 3 minus 3 letter 1d465 2 plus 4 letter 1d465 plus 5 equals letter 1d465 plus 2. 2 letter 1d465 2 minus 7 letter 1d465 plus 18 minus 31. We can identify the dividend, the divisor, the quotient, and the remainder. Identifying the dividend, divisor, quotient, and remainder of the polynomial 2x3-3x2 plus 4x plus 5, which is the dividend. Writing the result in this manner illustrates the division algorithm. The division algorithm states that, given a polynomial dividend letter 1d453, letter 1d465, and a non-zero polynomial divisor letter 1d451, letter 1d465, where the degree of letter 1d451, letter 1d465 is less than or equal to the degree of letter 1d453, letter 1d465. There exist unique polynomials letter 1d45e, letter 1d465, and letter 1d45f, letter 1d465, such that letter 1d453, letter 1d465 equals letter 1d451, letter 1d465, letter 1d45e, letter 1d465 plus letter 1d45f, letter 1d465, letter 1d45e, letter 1d465 is the quotient, and letter 1d45f, letter 1d465 is the remainder. The remainder is either equal to 0 or has degree strictly less than letter 1d451, letter 1d465. If letter 1d45f, letter 1d465 equals 0, then letter 1d451, letter 1d465 divides evenly into letter 1d453, letter 1d465. This means that, in this case, both letter 1d451, letter 1d465, and letter 1d45e, letter 1d465, are factors of letter 1d453, letter 1d465. How to given a polynomial and a binomial, use long division to divide the polynomial by the binomial. Set up the division problem. Determine the first term of the quotient by dividing the leading term of the dividend by the leading term of the divisor. multiply the answer by the divisor and write it below the like terms of the dividend. Subtract the bottom binomial from the top binomial. Bring down the next term of the dividend. Repeat steps 2-5 until reaching the last term of the dividend. If the remainder is non-zero, express as a fraction using the divisor as the denominator. Example 1, using long division to divide a second-degree polynomial, divide 5 letter 1d4652 plus 3 letter 1d465 minus 2 by x plus 1. Solution: the quotient is 5 letter 1d465 minus 2. The remainder is 0. We write the result as 5 letter 1d4652 plus 3 letter 1d465 minus 2 letter 1d465 plus 1 equals 5 letter 1d465 minus 2, or 5 letter 1d4652 plus 3 letter 1d465 minus 2 equals letter 1d465 plus 1, 5 letter 1d465 minus 2. Analysis: this division problem had a remainder of 0. This tells us that the dividend is divided evenly by the divisor, and that the divisor is a factor of the dividend. Example 2, using long division to divide a third-degree polynomial, divide 6 letter 1d465 3 plus 11 letter 1d465 2 minus 31 letter 1d465 plus 15 by 3 letter 1d465 minus 2. Solution: there is a remainder of 1. We can express the result as 6 letter 1d465 3 plus 11 letter 1d465 2 minus 31 letter 1d465 plus 153 letter 1d465 minus 2 equals 2 letter 1d465 2 plus 5 letter 1d465 minus 7 plus 13 letter 1d465 minus 2. Analysis: we can check our work by using the division algorithm to rewrite the solution. Then multiply 3 letter 1d465 minus 2, 2 letter 1d465 2 plus 5 letter 1d465 minus 7, plus 1 equals 6 letter 1d465 3 plus 11 letter 1d465 2 minus 31 letter 1d465 plus 15. Notice, as we write our result, the dividend is 6 letter 1d465 3 plus 11 letter 1d465 2 minus 31 letter 1d465 plus 15. The divisor is 3 letter 1d465 minus 2. The quotient is 2 letter 1d465 2 plus 5 letter 1d465 minus 7. The remainder is 1 try. It 1 divides 16 letter 1d465 3 minus 12 letter 1d465 2 plus 20 letter 1d465 minus 3 by 4x plus 5. Using synthetic division to divide polynomials, as we've seen, long division of polynomials can involve many steps and be quite cumbersome. Synthetic division is a shorthand method of dividing polynomials for the special case of dividing by a linear factor whose leading coefficient is 1. To illustrate the process, recall the example at the beginning of the section. Divide 2 letter 1d465 3 minus 3 letter 1d465 2 plus 4 letter 1d465 plus 5 by x plus 2 using the long division algorithm. The final form of the process looked like this. There is a lot of repetition in the table. If we don't write the variables but instead line up their coefficients in columns under the division sign and also eliminate the partial products, we already have a simpler version of the entire problem. Synthetic division of the polynomial 2x3-3x2 plus 4x plus 5 by x plus 2, in which it only contains the coefficients of each polynomial. Synthetic division carries this simplification even a few more steps. Collapse the table by moving each of the rows up to fill any vacant spots. Also, instead of dividing by 2, as we would in division of whole numbers, then multiplying and subtracting the middle product, we change the sign of the divisor to 2, multiply and add. The process starts by bringing down the leading coefficient. Synthetic division of the polynomial 2x3-3x2 plus 4x plus 5 by x plus 2, in which it only contains the coefficients of each polynomial. We then multiply it by the divisor and add, repeating this process column by column until there are no entries left. The bottom row represents the coefficients of the quotient. The last entry of the bottom row is the remainder. In this case, the quotient is 2 letter 1d465 2 7 letter 1d465 plus 18, and the remainder is 31. The process will be made more clear in example 3. Synthetic division. Synthetic division is a shortcut that can be used when the divisor is a binomial in the form letter 1d465 minus letter 1d458, where k is a real number. In synthetic division, only the coefficients are used in the division process. How to given two polynomials, use synthetic division to divide. Write k for the divisor. Write the coefficients of the dividend. Bring the lead coefficient down. Multiply the lead coefficient by k. Write the product in the next column. Add the terms of the second column. Multiply the result by k. Write the product in the next column. Repeat steps 5 and 6 for the remaining columns. Use the bottom numbers to write the quotient. The number in the last column is the remainder. The next number from the right has degree 0. The next number has degree 1, and so on. Example 3. Using synthetic division to divide a second-degree polynomial, use synthetic division to divide 5 letter 1d465 2 minus 3 letter 1d465 minus 36 by letter 1d465 minus 3. Solution. Begin by setting up the synthetic division. Write k and the coefficients. A collapsed version of the previous synthetic division. Bring down the lead coefficient. Multiply the lead coefficient by k. The setup of the synthetic division for the polynomial 5x2-3x36 by x3, which renders 5 minus 3 by 3. Continue by adding the numbers in the second column. Multiply the resulting number by k. Write the result in the next column, then add the numbers in the third column. Multiplied by the lead coefficient, 5, in the second column, and the lead coefficient is brought down to the second row. The result is 5x plus 12. The remainder is 0. So letter 1d465 minus 3 is a factor of the original polynomial. Analysis. Just as with long division, we can check our work by multiplying the quotient by the divisor and adding the remainder. Letter 1d465 minus 3. 5 letter 1d465 plus 12 plus 0 equals 5 letter 1d465 2 minus 3 letter 1d465 minus 36. Example 4. Using synthetic division to divide a third-degree polynomial. Use synthetic division to divide 4 letter 1d465 3 plus 10 letter 1d465 2 minus 6 letter 1d465 minus 20 by x plus 2. Solution. The binomial divisor is x plus 2, so letter 1d458 equals minus 2. Add each column, multiply the result by 2, and repeat until the last column is reached. Synthetic division of 4x3 plus 10x2-6x20 divided by x plus 2. The result is 4 letter 1d465 2 plus 2 letter 1d465 minus 10. The remainder is 0. Thus, is a factor of 4 letter 1d465 3 plus 10 letter 1d465 2 minus 6 letter 1d465 minus 20. Analysis. The graph of the polynomial function letter 1d453. Letter 1d465 equals 4 letter 1d465 3 plus 10 letter 1d465 2 minus 6 letter 1d465 minus 20. In figure 2, shows a 0 at letter 1d465 equals letter 1d458 equals minus 2. This confirms that x plus 2 is a factor of 4 letter 1d465 3 plus 10 letter 1d465 2 minus 6 letter 1d465 minus 20. Synthetic division of 4x3 plus 10x2-6x20 divided by x plus 2. Figure 2, Example 5, using synthetic division to divide a fourth-degree polynomial. Use synthetic division to divide minus 9 letter 1d465, 4 plus 10 letter 1d465 3 plus 7 letter 1d465 2 minus 6 by letter 1d465 minus 1. Solution. Notice there is no x term. We will use a 0 as the coefficient for that term. The result is minus 9 letter 1d465 3 plus letter 1d465 2 plus 8 letter 1d465 plus 8 plus 2 letter 1d465 minus 1. Try it too. Use synthetic division to divide 3 letter 1d465 4 plus 18 letter 1d465 3 minus 3 letter 1d465 plus 40 by x plus 7. Using polynomial division to solve application problems, polynomial division can be used to solve a variety of application problems involving expressions for area and volume. We looked at an application at the beginning of this section. Now, we will solve that problem in the following example. Example 6, using polynomial division in an application problem, the volume of a rectangular solid is given by the polynomial 3 letter 1d465, 4 minus 3 letter 1d465, 3 minus 33 letter 1d465, 2 plus 54 letter 1d465. The length of the solid is given by 3x, and the width is given by letter 1d465 minus 2. Find the height, h, of the solid. Solution: there are a few ways to approach this problem. We need to divide the expression for the volume of the solid by the expressions for the length and width. Let us create a sketch, as in Figure 3. Graph of f, x, equals 4x3 plus 10x2 dash 6x20 with a close-up on x plus 2. Figure 3, we can now write an equation by substituting the known values into the formula for the volume of a rectangular solid. Letter 1d449, 3 letter 1d465, 4 minus 3 letter 1d465, 3 minus 33 letter 1d465, 2 plus 54 letter 1d465 equals letter 1d459, letter 1d464, letter 210e, 3 letter 1d465. Letter 1d465 minus 2 letter 210e to solve for h. First divide both sides by 3x, 3 letter 1d465. Letter 1d465 minus 2 letter 210e, 3 letter 1d465. Letter 1d465 minus 2 letter 210e equals 3 letter 1d465, 4 minus 3 letter 1d465, 3 minus 33 letter 1d465, 2 plus 54 letter 1d465, 3 letter 1d465 letter 1d465, 3 minus letter 1d465, 2 minus 11 letter 1d4s. Now solve for h using synthetic division. The quotient is letter 1d465, 2, plus letter 1d465 minus 9, and the remainder is 0. The height of the solid is letter 1d465, 2, plus letter 1d465 minus 9. Try it 3. The area of a rectangle is given by 3 letter 1d465, 3, plus 14 letter 1d465, 2, minus 23 letter 1d465 plus 6. The width of the rectangle is given by x plus 6. Find an expression for the length of the rectangle. Media access these online resources for additional instruction and practice with polynomial division. Dividing a trinomial by a binomial using long division, dividing a polynomial by a binomial using long division x2. Dividing a polynomial by a binomial using synthetic division x4. Dividing a polynomial by a binomial using synthetic division 5-4 section, exercises verbal 1. If division of a polynomial by a binomial results in a remainder of 0, what can be concluded? 2. If a polynomial of degree n is divided by a binomial of degree 1, what is the degree of the quotient? Algebraic for the following exercises, use long division to divide. Specify the quotient and the remainder. 3. Letter 1d465 2 plus 5 letter 1d465 minus 1 divided by letter 1d465 minus 1, 4. 2 letter 1d465 2 minus 9 letter 1d465 minus 5 divided by letter 1d465 minus 5. 5. 3 letter 1d465 2 plus 23 letter 1d465 plus 14 divided by letter 1d465 plus 7. 6. 4 letter 1d465 2 minus 10 letter 1d465 plus 6 divided by 4 letter 1d465 plus 2. 7. 6 letter 1d465 2 minus 25 letter 1d465 minus 25 divided by 6 letter 1d465 plus 5. 8. Minus letter 1d465 2 minus 1 divided by letter 1d465 plus 1, 9. 2 letter 1d465 2 minus 3 letter 1d465 plus 2 divided by letter 1d465 plus 2, 10. Letter 1d465 3 minus 126 divided by letter 1d465 minus 5, 11. 3 letter 1d465 2 minus 5 letter 1d465 plus 4 divided by 3 letter 1d465 plus 1, 12. Letter 1d465 3 minus 3 letter 1d465 2 plus 5 letter 1d465 minus 6 divided by letter 1d465 minus 2, 13. 2 letter 1 d465 3 plus 3 letter 1 d465 2 minus 4 letter 1 d465 plus 15 divided by letter 1 d465 plus 3. For the following exercises, use synthetic division to find the quotient. Ensure the equation is in the form required by synthetic division. Hint: divide the dividend and divisor by the coefficient of the linear term in the divisor. 14. 3 letter 1 d465 3 minus 2 letter 1 d465 2 plus letter 1 d465 minus 4 divided by letter 1 d465 plus 3, 15. 2 letter 1 d465 3 minus 6 letter 1 d465 2 minus 7 letter 1 d465 plus 6 divided by letter 1 d465 minus 4, 16. 6 letter 1 d465 3 minus 10 letter 1 d465 2 minus 7 letter 1 d465 minus 15 divided by letter 1 d465 plus 1, 17. 4 letter 1 d465 3 minus 12 letter 1 d465 2 minus 5 letter 1 d465 minus 1 divided by 2 letter 1 d465 plus 1, 18. 9 letter 1 d465 3 minus 9 letter 1 d465 2 plus 18 letter 1 d465 plus 5 divided by 3 letter 1 d465 minus 1, 19. 3 letter 1 d465 3 minus 2 letter 1 d465 2 plus letter 1 d465 minus 4 divided by letter 1 d465 plus 3, 20. Minus 6 letter 1 d465 3 plus letter 1 d465 2 minus 4 divided by 2 letter 1 d465 minus 3, 21. 2 letter 1 d465 3 plus 7 letter 1 d465 2 minus 13 letter 1 d465 minus 3 divided by 2 letter 1 d465 minus 3, 22. 3 letter 1 d465 3 minus 5 letter 1 d465 2 plus 2 letter 1 d465 plus 3 divided by letter 1 d465 plus 2, 23. 4 letter 1 d465 3 minus 5 letter 1 d465 2 plus 13 divided by letter 1 d465 plus 4, 24. Letter 1 d465 3 minus 3 letter 1 d465 plus 2 divided by letter 1 d465 plus 2, 25. Letter 1 d465 3 minus 21 letter 1 d465 2 plus 147 letter 1 d465 minus 343 divided by letter 1 d465 minus 7, 26. Letter 1 d465 3 minus 15 letter 1 d465 2 plus 75 letter 1 d465 minus 125 divided by letter 1 d465 minus 5, 27. 9 letter 1 d465 3 minus letter 1 d465 plus 2 divided by 3 letter 1 d465 minus 1, 28. 6 letter 1 d465 3 minus letter 1 d465 2 plus 5 letter 1 d465 plus 2 divided by 3 letter 1 d465 plus 1, 29. Letter 1 d465 4 plus letter 1 d465 3 minus 3 letter 1 d465 2 minus 2 letter 1 d465 plus 1 divided by letter 1 d465 plus 1, 30. Letter 1 d465 4 minus 3 letter 1 d465 2 plus 1 divided by letter 1 d465 minus 1, 31. Letter 1 d465 4 plus 2 letter 1 d465 3 minus 3 letter 1 d465 2 plus 2 letter 1 d465 plus 6 divided by letter 1 d465 plus 3, 32. Letter 1 d465 4 minus 10 letter 1 d465 3 plus 37 letter 1 d465 2 minus 60 letter 1 d465 plus 36 divided by letter 1 d465 minus 2, 33. Letter 1 d465 4 minus 8 letter 1 d465 3 plus 24 letter 1 d465 2 minus 32 letter 1 d465 plus 16 divided by letter 1 d465 minus 2, 34. Letter 1 d465 4 plus 5 letter 1 d465 3 minus 3 letter 1 d465 2 minus 13 letter 1 d465 plus 10 divided by letter 1 d465 plus 5, 35. Letter 1 d465 4 minus 12 letter 1 d465 3 plus 54 letter 1d465, 2 minus 108 letter 1d465, plus 81 divided by letter 1d465 minus 3, 36. 4 letter 1d465, 4 minus 2 letter 1d465, 3 minus 4 letter 1d465 plus 2, divided by 2 letter 1d465 minus 1, 37. 4 letter 1d465, 4 plus 2 letter 1d465, 3 minus 4 letter 1d465, 2, plus 2 letter 1d465, plus 2 divided by 2 letter 1d465 plus 1. For the following exercises, use synthetic division to determine whether the first expression is a factor of the second. If it is, indicate the factorization. 38. Letter 1d465 minus 2, 4 letter 1d465, 3 minus 3, letter 1d465, 2 minus 8, letter 1d465, plus 4, 39. Letter 1d465 minus 2, 3 letter 1d465, 4 minus 6, letter 1d465, 3 minus 5, letter 1d465, plus 1040. Letter 1d465 plus 3, minus 4 letter 1d465 3, plus 5 letter 1d465 2, plus 841. Letter 1d465 minus 2, 4 letter 1d465 4 minus 15, letter 1d465 2 minus 442. Letter 1d465 minus 12, 2 letter 1d465, 4 minus letter 1d465 3, plus 2 letter 1d465 minus 143. Letter 1d465 plus 13, 3 letter 1d465, 4 plus letter 1d465, 3 minus 3 letter 1d465, plus 1 graphical for the following exercises. Use the graph of the degree polynomial and one factor to write the factored form of the polynomial suggested by the graph. The leading coefficient is 1, 44. Factor is letter 1d465 2 minus letter 1d465 plus 3 graph of a polynomial that has a x-intercept at minus 1, 45. Factor is x2 plus 2x plus 4 graph of a polynomial that has a x-intercept at 146. Factor is x2 plus 2x plus 5 graph of a polynomial that has a x-intercept at 2, 47. Factor is x2 plus x plus 1 graph of a polynomial that has a x-intercept at 548. Factor is x2 plus 2x plus 2 graph of a polynomial that has a x-intercept at. For the following exercises, use synthetic division to find the quotient and remainder. 49. 4 letter 1d465 3 minus 33 letter 1d465 minus 250. 2x3 plus 25x plus 351. 3 letter 1d465 3 plus 2 letter 1d465 minus 5 letter 1d465 minus 152. Minus 4 letter 1d465 3 minus letter 1d465 2 minus 12 letter 1d465 plus 453. Letter 1d465 4 minus 22 letter 1d465 plus 2 technology for the following exercises. Use a calculator with CAS to answer the questions. 54. Consider letter 1d465 letter 1d458 minus 1 letter 1d465 minus 1 with letter 1d458 equals 1, 2, 3. What do you expect the result to be if letter 1d458 equals 4? 55. Consider letter 1d465 letter 1d458 plus 1 letter 1d465 plus 1 for letter 1d458 equals 1, 3, 5. What do you expect the result to be if letter 1d458 equals 7? 56. Consider letter 1d465 4 minus letter 1d458 for letter 1d465 minus letter 1d458 for letter 1d458 equals 1, 2, 3. What do you expect the result to be if letter 1d458 equals 4? 57. Consider letter 1d465 letter 1d458 letter 1d465 plus 1 with letter 1d458 equals 1, 2, 3. What do you expect the result to be if letter 1d458 equals 4? 58. Consider letter 1d465 letter 1d458 letter 1d465 minus 1 with letter 1d458 equals 1, 2, 3. What do you expect the result to be if letter 1d458 equals 4? Extensions for the following exercises use synthetic division to determine the quotient involving a complex number. 59. Letter 1d465 plus 1 letter 1d465 minus letter 1d456 60. Letter 1d4652 plus 1 letter 1d465 minus letter 1d456 61. X plus 1x plus I 62. X2 plus 1x plus I 63. Letter 1d4653 plus 1 letter 1d465 minus letter 1d456 real-world applications for the following exercises. Use the given length and area of a rectangle to express the width algebraically. 64. Length is x plus 5. Area is 2 letter 1d4652 plus 9 letter 1d465 minus 5. 65. Length is 2x plus 5. Area is 4x3 plus 10x2 plus 6x plus 1566. Length is 3 letter 1d4654. Area is 6 letter 1d4654 minus 8 letter 1d4653 plus 9 letter 1d4652 minus 9 letter 1d465 minus 4 for the following exercises. Use the given volume of a box and its length and width to express the height of the box algebraically. 67. Volume is 12 letter 1d4653 plus 20 letter 1d4652 minus 21 letter 1d465 minus 36. Length is 2x plus 3. Width is 3 letter 1d465 minus 4. 68. Volume is 18 letter 1d465 3 minus 21 letter 1d465 2 minus 40 letter 1d465 plus 48. Length is 3 letter 1d4654. Width is 3 letter 1d4654. 69. Volume is 10 letter 1d4653 plus 27 letter 1d4652 plus 2 letter 1d465 minus 24. Length is 5 letter 1d4654. Width is 2x plus 3. 70. Volume is 10 letter 1d4653 plus 30 letter 1d4652 minus 8 letter 1d465 minus 24. Length is 2. Width is x plus 3. For the following exercises, use the given volume and radius of a cylinder to express the height of the cylinder algebraically. 71. Volume is letter 1d70b. 25 letter 1d465 3 minus 65 letter 1d465 2 minus 29 letter 1d465 minus 3. Radius is 5x plus 1. 72. Volume is letter 1d70b. 4 letter 1d465 3 plus 12 letter 1d465 2 minus 15 letter 1d465 minus 50. Radius is 2x plus 5. 73. Volume is plus 24 letter 1d465 3 plus 46 letter 1d465 2 minus 16 letter 1d465 minus 32. Radius is x plus 4. Learning objectives in this section, you will evaluate a polynomial using the remainder theorem. Use the factor theorem to solve a polynomial equation. Use the rational zero theorem to find rational zeros. Find zeros of a polynomial function. Use the linear factorization theorem to find polynomials with given zeros. Use Descartes' rule of signs. Solve real-world applications of polynomial equations. A new bakery offers decorated, multi-tiered cakes for display and cutting at quinceañera and wedding celebrations, as well as sheet cakes to serve most of the guests. The bakery wants the volume of a small sheet cake to be 351 cubic inches. The cake is in the shape of a rectangular solid. They want the length of the cake to be 4 inches longer than the width of the cake and the height of the cake to be 1/3 of the width. What should the dimensions of the cake pan be? This problem can be solved by writing a cubic function and solving a cubic equation for the volume of the cake. In this section, we will discuss a variety of tools for writing polynomial functions and solving polynomial equations. Evaluating a polynomial using the remainder theorem in the last section, we learned how to divide polynomials. We can now use polynomial division to evaluate polynomials using the remainder theorem. If the polynomial is divided by letter 1d465, letter 1d458, the remainder may be found quickly by evaluating the polynomial function at k. That is, letter 1d453, letter 1d458, Let's walk through the proof of the theorem. Recall that the division algorithm states that, given a polynomial dividend letter 1d453, letter 1d465, and a non-zero polynomial divisor letter 1d451, letter 1d465, there exist unique polynomials letter 1d45e, letter 1d465, and letter 1d45f, letter 1d465, such that letter 1d453, letter 1d465 equals letter 1d451, letter 1d465, letter 1d45e, letter 1d465 plus letter 1d45f, letter 1d465, and either letter 1d45f, letter 1d465, equals 0 or the degree of letter 1d45f, letter 1d465, is less than the degree of letter 1d451, letter 1d465. In practice divisors, letter 1d451, letter 1d465 will have degrees less than or equal to the degree of letter 1d453, letter 1d465. If the divisor, letter 1d451, letter 1d465, is letter 1d465 minus letter 1d458, this takes the form letter 1d453, letter 1d465 equals letter 1d465 minus letter 1d458, letter 1d45e, letter 1d465, plus letter 1d45f, since the divisor letter 1d465 minus letter 1d458 is linear. The remainder will be a constant, r. And if we evaluate this for letter 1d465 equals letter 1d458, we have letter 1d453, letter 1d458 equals letter 1d458 minus letter 1d458, letter 1d45e, letter 1d458 plus letter 1d45f, 0 letter 1d45e, letter 1d458 plus letter 1d45f, letter 1d45f, in other words, letter 1d453, letter 1d458, is the remainder obtained by dividing letter 1d453, letter 1d465, by letter 1d465 minus letter 1d458. The remainder theorem if a polynomial letter 1d453, letter 1d465, is divided by letter 1d465 minus letter 1d458, then the remainder is the value letter 1d453, letter 1d458. How to given a polynomial function f, evaluate letter 1d453, letter 1d465, at letter 1d465 equals letter 1d458 using the remainder theorem. Use synthetic division to divide the polynomial by letter 1d465 minus letter 1d458. The remainder is the value letter 1d453, letter 1d458. Example 1, using the remainder theorem to evaluate a polynomial. Use the remainder theorem to evaluate letter 1d453. Letter 1d465 equals 6 letter 1d465, 4 minus letter 1d465, 3 minus 15 letter 1d465, 2 plus 2 letter 1d465 minus 7 at letter 1d465 equals 2. Solution to find the remainder using the remainder theorem. Use synthetic division to divide the polynomial by letter 1d465 minus 2. The remainder is 25. Therefore, letter 1d453, 2, equals 25. Analysis: we can check our answer by evaluating letter 1d453, 2. Letter 1d453, letter 1d465, letter 1d453, 2 equals 6 letter 1d465, 4 minus letter 1d465, 3 minus 15 letter 1d465, 2 plus 2 letter 1d465 minus 76, 2, 4 minus 2, 3 minus 15, 2, 2 plus 2, 2, minus 725. Try it 1. Use the remainder theorem to evaluate. Letter 1d453, letter 1d465, equals 2 letter 1d465, 5 minus 3 letter 1d465, 4 minus 9 letter 1d465, 3, plus 8 letter 1d465, 2, plus 2, at letter 1d465 equals minus 3. Using the factor theorem to solve a polynomial equation. The factor theorem is another theorem that helps us analyze polynomial equations. It tells us how the zeros of a polynomial are related to the factors. Recall that the division algorithm, letter 1d453, letter 1d465 equals letter 1d465 minus letter 1d458, letter 1d45e, letter 1d465, plus letter 1d45f if k is a 0. Then the remainder r is letter 1d453. Letter 1d458 equals 0 and letter 1d453. Letter 1d465 equals letter 1d465 minus letter 1d458 letter 1d458, letter 1d465 plus 0 or letter 1d453, letter 1d465 equals letter 1d465 minus letter 1d458, letter 1d458, letter 1d465. Notice, written in this form, letter 1d465 minus letter 1d458 is a factor of letter 1d453, letter 1d465. We can conclude if k is a 0 of letter 1d453, letter 1d465. Then letter 1d465 minus letter 1d458 is a factor of letter 1d453, letter 1d465. Similarly, if letter 1d465 minus letter 1d458 is a factor of letter 1d453, letter 1d465. Then the remainder of the division algorithm letter 1d453, letter 1d465 equals letter 1d465 minus letter 1d458, letter 1d458, letter 1d465, plus letter 1d45f is 0. This tells us that k is a 0. This pair of implications is the factor theorem. As we will soon see, a polynomial of degree n in the complex number system will have n zeros. We can use the factor theorem to completely factor a polynomial into the product of n factors. Once the polynomial has been completely factored, we can easily determine the zeros of the polynomial. The factor theorem, according to the factor theorem, k is a 0 of letter 1d453, letter 1d465. If and only if letter 1d465 minus letter 1d458 is a factor of letter 1d453, letter 1d465. How to given a factor and a degree polynomial, use the factor theorem to factor the polynomial. Use synthetic division to divide the polynomial by letter 1d465 minus letter 1d458. Confirm that the remainder is 0. Write the polynomial as the product of letter 1d465 minus letter 1d458 and the quadratic quotient. If possible, factor the quadratic. Write the polynomial as the product of factors. Example 2, using the factor theorem to find the zeros of a polynomial expression show that x plus 2 is a factor of letter 1d465, 3 minus 6, letter 1d465, 2 minus letter 1d465 plus 30. Find the remaining factors. Use the factors to determine the zeros of the polynomial. Solution, we can use synthetic division to show that x plus 2 is a factor of the polynomial. The remainder is 0, so x plus 2 is a factor of the polynomial. We can use the division algorithm to write the polynomial as the product of the divisor and the quotient. Letter 1d465 plus 2, letter 1d465 2 minus 8, letter 1d465 plus 15. We can factor the quadratic factor to write the polynomial as letter 1d465 plus 2, letter 1d465 minus 3, letter 1d465 minus 5, by the factor theorem. The zeros of letter 1d465, 3 minus 6, letter 1d465, 2 minus letter 1d465 plus 30 are 2, 3, and 5. Try it too, use the factor theorem to find the zeros of letter 1d453. Letter 1d465 equals letter 1d465 3 plus 4 letter 1d465 2 minus 4 letter 1d465 minus 16, given that letter 1d465 minus 2 is a factor of the polynomial. Using the rational zero theorem to find rational zeros, another use for the remainder theorem is to test whether a rational number is a 0 for a given polynomial. But first, we need a pool of rational numbers to test. The rational zero theorem helps us to narrow down the number of possible rational zeros using the ratio of the factors of the constant term and factors of the leading coefficient of the polynomial. Consider a quadratic function with two zeros. Letter 1d465 equals 25 and letter 1d465 equals 34. By the factor theorem, these zeros have factors associated with them. Let us set each factor equal to 0, and then construct the original quadratic function absent its stretching factor. Notice that two of the factors of the constant term, 6, are the two numerators from the original rational roots, 2 and 3. Similarly, two of the factors from the leading coefficient, 20, are the two denominators from the original rational roots, 5 and 4. We can infer that the numerators of the rational roots will always be factors of the constant term, and the denominators will be factors of the leading coefficient. This is the essence of the rational zero theorem. It is a means to give us a pool of possible rational zeros. The rational zero theorem states that if the polynomial letter 1d453, letter 1d465 equals letter 1d44, letter 1d45b, letter 1d465, letter 1d45b, plus letter 1d44, letter 1d45b, minus 1, letter 1d465, letter 1d45b, minus 1 plus a1x plus a0 has integer coefficients letter 1d44, letter 1d45b, not equal to 0. Then every rational zero of letter 1d453, letter 1d465, has the form letter 1d45d, letter 1d45e, where p is a factor of the constant term a0, and q is a factor of the leading coefficient n. When the leading coefficient is 1, the possible rational zeros are the factors of the constant term. How to given a polynomial function letter 1d453, letter 1d465, use the rational zero theorem to find rational zeros. Determine all factors of the constant term and all factors of the leading coefficient. Determine all possible values of letter 1d45d, letter 1d45e, where p is a factor of the constant term and q is a factor of the leading coefficient. Be sure to include both positive and negative candidates. Determine which possible zeros are actual zeros by evaluating each case of letter 1d453, letter 1d45d, letter 1d45e. Example 3, listing all possible rational zeros. List all possible rational zeros of letter 1d453, letter 1d465, equals 2, letter 1d465, 4 minus 5, letter 1d465, 3, plus letter 1d465, 2 minus 4. Solution: the only possible rational zeros of letter 1d453, letter 1d465, are the quotients of the factors of the last term, 4, and the factors of the leading coefficient, 2. The constant term is 4. The factors of 4 are letter 1d45d equals plus 1, plus or minus 2, plus or minus 4. The leading coefficient is 2. The factors of 2 are letter 1d45e equals plus 1, plus or minus 2. If any of the 4 real zeros are rational zeros, then they will be of one of the following factors of 4 divided by one of the factors of 2. Letter 1d45d, letter 1d45e equals plus 11, plus or minus 12, letter 1d45d, letter 1d45e equals plus 21, plus or minus 22, letter 1d45d, letter 1d45e equals plus 41, plus or minus 42. Note that 22 equals 1 and 42 equals 2, which have already been listed. So we can shorten our list. Letter 1d45d, letter 1d45e equals factors of the last factors of the first equals plus 1, plus or minus 2, plus or minus 4, plus or minus 12. Example 4, using the rational zero theorem to find rational zeros. Use the rational zero theorem to find the rational zeros of letter 1d453. Letter 1d465 equals 2, letter 1d465, 3, plus letter 1d465, 2 minus 4, letter 1d465, plus 1. Solution: the rational zero theorem tells us that if letter 1d45d, letter 1d45e is a zero of letter 1d453, letter 1d465, then p is a factor of 1 and q is a factor of 2. Letter 1d45d, letter 1d45e equals factor of constant term factor of leading coefficient factor of 1 factor of 2. The factors of 1 are plus or minus 1, and the factors of 2 are plus or minus 1 and plus or minus 2. The possible values for letter 1d45d, letter 1d45e are plus or minus 1 and plus or minus 12. These are the possible rational zeros for the function. We can determine which of the possible zeros are actual zeros by substituting these values for x in letter 1d453, letter 1d465. Letter 1d453, minus 1, letter 1d453. 1, letter 1d453, minus 12, letter 1d453. 12 equals 2 minus 1, 3 plus, minus 1, 2 minus 4 minus 1, plus 1 equals 42, 1, 3 plus, 1, 2 minus 4, 1, plus 1 equals 0, 2 minus 12, 3 plus minus 12, 2 minus 4, minus 12, plus 1 equals 32, 12, 3 plus, 12, 2 minus 4, 12, plus 1 equals minus 12. Of those, minus 1, minus 12, and 12 are not zeros of letter 1D453, letter 1D465. 1 is the only rational zero of letter 1D453, letter 1D465. Try it 3. Use the rational zero theorem to find the rational zeros of letter 1D453, letter 1D465, equals letter 1D465, 3 minus 5 letter 1D465, 2 plus 2 letter 1D465 plus 1. Finding the zeros of polynomial functions, the rational zero theorem helps us to narrow down the list of possible rational zeros for a polynomial function. Once we have done this, we can use synthetic division repeatedly to determine all of the zeros of a polynomial function. How to given a polynomial function f, use synthetic division to find its zeros. Use the rational zero theorem to list all possible rational zeros of the function. Use synthetic division to evaluate a given possible zero by synthetically dividing the candidate into the polynomial. If the remainder is 0, the candidate is a 0. If the remainder is not 0, discard the candidate. Repeat step 2 using the quotient found with synthetic division. If possible, continue until the quotient is a quadratic. Find the zeros of the quadratic function. 2 possible methods for solving quadratics are factoring and using the quadratic formula. Example 5, finding the zeros of a polynomial function with repeated real zeros. Find the zeros of letter 1D453, letter 1D465, equals 4 letter 1D465, 3 minus 3, letter 1D465 minus 1. Solution: the rational zero theorem tells us that if letter 1D45D letter 1D45E is a zero of letter 1D453, letter 1D465, then P is a factor of 1 and Q is a factor of 4. Letter 1D45D letter 1D45E equals factor of constant term factor of leading coefficient factor. Of one factor of 4, the factors of 1 are plus or minus 1, and the factors of 4 are plus or minus 1, plus or minus 2, and plus or minus 4. The possible values for letter 1D45D letter 1D45E are plus or minus 1, plus or minus 12, and plus or minus 14. These are the possible rational zeros for the function. We will use synthetic division to evaluate each possible zero until we find one that gives a remainder of 0. Let's begin with 1. Dividing by letter 1D465 minus 1 gives a remainder of 0, so 1 is a 0 of the function. The polynomial can be written as letter 1D465 minus 1, 4 letter 1D465 2 plus 4 letter 1D465 plus 1. The quadratic is a perfect square. Letter 1D453, letter 1D465 can be written as letter 1D465 minus 1, 2 letter 1D465 plus 1, 2, we already know that 1 is a 0. The other 0 will have a multiplicity of 2 because the factor is squared. To find the other 0, we can set the factor equal to 0. 2 letter 1D465 plus 1 letter 1D465 equals 0 minus 12. The zeros of the function are 1 and minus 12 with multiplicity 2. Analysis: look at the graph of the function f in figure 1. Notice, at letter 1D465 equals minus 0. 5, the graph bounces off the x-axis, indicating the even multiplicity 246 for the 0 minus 0. 5, at letter 1D465 equals 1, the graph crosses the x-axis, indicating the odd multiplicity 135 for the 0 letter 1D465 equals 1. Graph of a polynomial that have its local maximum at minus 0, 5, 0 labeled as bounce, and its x-intercept at 1, 0 labeled cross. Figure 1 using the fundamental theorem of algebra. Now that we can find rational zeros for a polynomial function, we will look at a theorem that discusses the number of complex zeros of a polynomial function. The fundamental theorem of algebra tells us that every polynomial function has at least one complex zero. This theorem forms the foundation for solving polynomial equations. Suppose f is a polynomial function of degree 4, and letter 1D453, letter 1D465 equals 0. The fundamental theorem of algebra states that there is at least one complex solution, call it C1. By the factor theorem, we can write letter 1D453, letter 1d465, as a product of letter 1d465 minus letter 1d450, 1, and a polynomial quotient. Since letter 1d465 minus letter 1d450, 1 is linear, the polynomial quotient will be of degree 3. Now, we apply the fundamental theorem of algebra to the degree polynomial quotient. It will have at least one complex zero, call it C2. So we can write the polynomial quotient as a product of letter 1d465 minus letter 1d450, 2, and a new polynomial quotient of degree 2. Continue to apply the fundamental theorem of algebra until all of the zeros are found. There will be 4 of them, and each one will yield a factor of letter 1d453, letter 1d465. The fundamental theorem of algebra states that if letter 1d453, letter 1d465 is a polynomial of degree n0, then letter 1d453, letter 1d465 has at least one complex zero. We can use this theorem to argue that if letter 1d453, letter 1d465 is a polynomial of degree letter 1d45b0, and a is a non-zero real number, then letter 1d453, letter 1d465 has exactly n linear factors letter 1d453, letter 1d465 equals letter 1d440, letter 1d465 minus letter 1d450, 1, letter 1d465 minus letter 1d450, 2, letter 1d465 minus letter 1d450, letter 1d45b, where C1, C2, letter 1d450, letter 1d45b are complex numbers. Therefore, letter 1d453, letter 1d465 has n roots if we allow for multiplicities. Q and A. Does every polynomial have at least one imaginary zero? No. Real numbers are a subset of complex numbers, but not the other way around. A complex number is not necessarily imaginary. Real numbers are also complex numbers. Example 6. Finding the zeros of a polynomial function with complex zeros. Find the zeros of letter 1d453. Letter 1d465 equals 3 letter 1d465 3 plus 9 letter 1d465 2 plus letter 1d465 plus 3. Solution. The rational zero theorem tells us that if letter 1d45d letter 1d45e is a zero of letter 1d453, letter 1d465, then p is a factor of 3 and q is a factor of 3. Letter 1d45d letter 1d45e equals factor of constant term factor of leading coefficient factor of 3 factor of 3. The factors of 3 are plus or minus 1 and plus or minus 3. The possible values for letter 1d45d letter 1d45e, and therefore the possible rational zeros for the function are plus or minus 3, plus or minus 1, and plus or minus 13. We will use synthetic division to evaluate each possible zero until we find one that gives a remainder of 0. Let's begin with 3. Dividing by x plus 3 gives a remainder of 0, so 3 is a zero of the function. The polynomial can be written as letter 1d465 plus 3, 3 letter 1d465 2 plus 1. We can then set the quadratic equal to 0 and solve to find the other zeros of the function. 3x2 plus 1x to letter 1d465 equals 0 minus 13 plus minus 13 square equals plus letter 1d456, 3 square root 3. The zeros of letter 1d453, letter 1d465, are 3 and plus or minus letter 1d456, 3 square root 3. Analysis. Look at the graph of the function f in figure 2. Notice that, at letter 1d465 equals minus 3, the graph crosses the x-axis, indicating an odd multiplicity, 1, for the zero letter 1d465 equals 3. Also note the presence of the 2 turning points. This means that, since there is a third-degree polynomial, we are looking at the maximum number of turning points. So, the end behavior of increasing without bound to the right and decreasing without bound to the left will continue. Thus, all the x-intercepts for the function are shown. So either the multiplicity of letter 1d465 equals minus 3 is 1, and there are 2 complex solutions, which is what we found, or the multiplicity at letter 1d465 equals minus 3 is 3. Either way, our result is correct. Graph of a polynomial with its x-intercept at -3, 0, labeled as cross. Figure 2, try at 4, find the zeros of letter 1d453, letter 1d465, equals 2 letter 1d4653 plus 5 letter 1d465, 2 minus 11 letter 1d465 plus 4. Using the linear factorization theorem to find polynomials with given zeros, a vital implication of the fundamental theorem of algebra, as we stated above, is that a polynomial function of degree n will have n zeros in the set of complex numbers, if we allow for multiplicities. This means that we can factor the polynomial function into n factors. The linear factorization theorem tells us that a polynomial function will have the same number of factors as its degree, and that each factor will be in the form letter 1d465 minus letter 1d450, where c is a complex number. Let f be a polynomial function with real coefficients, and suppose a plus by letter 1d44f not equal to 0 is a 0 of letter 1d453, letter 1d465. Then, by the factor theorem, letter 1d465 minus letter 1d44e plus letter 1d44f letter 1d456 is a factor of letter 1d453, letter 1d465. For f to have real coefficients, letter 1d465 minus letter 1d44e minus letter 1d44f letter 1d456 must also be a factor of letter 1d453, letter 1d465. This is true because any factor other than letter 1d465 minus letter 1d44e minus letter 1d44f letter 1d456, when multiplied by letter 1d465 minus letter 1d44e plus letter 1d44f letter 1d456, will leave imaginary components in the product. Only multiplication with conjugate pairs will eliminate the imaginary parts and result in real coefficients. In other words, if a polynomial function, f with real coefficients, has a complex 0 a plus by, then the complex conjugate letter 1d44e minus letter 1d44f letter 1d456 must also be a 0 of letter 1d453, letter 1d465. This is called the complex conjugate theorem. Complex conjugate theorem, according to the linear factorization theorem, a polynomial function will have the same number of factors as its degree, and each factor will be in the form letter 1d465 minus letter 1d450, where c is a complex number. If the polynomial function f has real coefficients and a complex 0 in the form a plus by, then the complex conjugate of the 0, letter 1d44e minus letter 1d44f letter 1d456, is also a 0. How to given the zeros of a polynomial function f and a point c, f, c. On the graph of f, use the linear factorization theorem to find the polynomial function. Use the zeros to construct the linear factors of the polynomial. Multiply the linear factors to expand the polynomial. Substitute letter 1d450, letter 1d453, letter 1d450 into the function to determine the leading coefficient. Simplify. Example 7, using the linear factorization theorem to find a polynomial with given zeros. Find a fourth-degree polynomial with real coefficients that has zeros of 3, 2, I, such that letter 1d453 minus 2 equals 100. Solution, because letter 1d465 equals letter 1d456, is a 0. By the complex conjugate theorem, letter 1d465 equals letter 1d456 is also a 0. The polynomial must have factors of letter 1d465 plus 3, letter 1d465 minus 2, letter 1d465 minus letter 1d456, and x plus I. Since we are looking for a degree 4 polynomial and now have 4 zeros, we have all 4 factors. Let's begin by multiplying these factors. Letter 1d453, letter 1d465, letter 1d453, letter 1d465, letter 1d453, letter 1d465 equals letter 1d44e, letter 1d465 plus 3, letter 1d465 minus 2, letter 1d465 minus letter 1d456, letter 1d465 plus letter 1d456, letter 1d44e, letter 1d465 2 plus letter 1d465 minus 6. We need to find it to ensure letter 1d453, 2, equals 100. Substitute letter 1d465 equals 2 and letter 1d453. 2 equals 100 into letter 1d453, letter 1d465. 100,100 minus 5 equals letter 1d440. Minus 2, 4 plus minus 2, 3 minus 5, minus 2 2 plus, minus 2 minus 6, letter 1d440, minus 20, letter 1d440, so the polynomial function is letter 1d453, letter 1d465, equals minus 5, letter 1d465, 4 plus letter 1d465, 3 minus 5, letter 1d465, 2 plus letter 1d465 minus 6, or letter 1d453, letter 1d465, equals minus 5, letter 1d465, 4 minus 5, letter 1d465, 3, plus 25, letter 1d465, 2 minus 5, letter 1d465, plus 30 analysis, we found that both I and minus letter 1d456 were zeros, but only one of these zeros needed to be given. If I is a zero of a polynomial with real coefficients, then minus letter 1d456 must also be a zero of the polynomial, because minus letter 1d456 is the complex conjugate of I. Q and A, if 2 plus 3i were given as a zero of a polynomial with real coefficients, would 2 minus 3 letter 1d456 also need to be a zero? Yes, when any complex number with an imaginary component is given as a zero of a polynomial with real coefficients, the conjugate must also be a zero of the polynomial. Try at 5 find a third-degree polynomial with real coefficients that has zeros of 5 and minus 2 letter 1d456, such that letter 1d453, 1 equals 10. Using Descartes' rule of signs, there is a straightforward way to determine the possible numbers of positive and negative real zeros for any polynomial function. If the polynomial is written in descending order, Descartes' rule of signs tells us of a relationship between the number of sign changes in letter 1d453, letter 1d465, and the number of positive real zeros. For example, the polynomial function below has one sign change. The function f x equals x4 plus x3 plus x2 plus x1 has one sign change between x and minus 1. This tells us that the function must have one positive real zero. There is a similar relationship between the number of sign changes in letter 1d453 minus letter 1d465 and the number of negative real zeros. The function f x equals x4 plus, x3 plus, x2 plus, x minus 1 equals plus x4 x3 plus x2 x1 has three sign changes between x4 and x3, x3 and x2 and x. In this case, letter 1d453 minus letter 1d465 has three sign changes. This tells us that letter 1d453, letter 1d465 could have 3 or 1 negative real zeros. Descartes' rule of signs, according to Descartes' rule of signs, if we let letter 1d453, letter 1d465 equals letter 1d44, letter 1d45b, letter 1d465, letter 1d45b, plus letter 1d44, letter 1d45b, minus 1, letter 1d465, letter 1d45b, minus 1 plus a1x plus a0 be a polynomial function with real coefficients. The number of positive real zeros is either equal to the number of sign changes of letter 1d453, letter 1d465, or is less than the number of sign changes by an even integer. The number of negative real zeros is either equal to the number of sign changes of letter 1d453 minus letter 1d465, or is less than the number of sign changes by an even integer. Example 8 using Descartes' rule of signs, use Descartes' rule of signs to determine the possible numbers of positive and negative real zeros for letter 1d453. Letter 1d465 equals minus letter 1d465, 4 minus 3 letter 1d465, 3, plus 6 letter 1d465, 2 minus 4 letter 1d465 minus 12. Solution begin by determining the number of sign changes. The function f x equals x4-3x3 plus 6x2-4x12 has two sign change between x and 6x2 and 6x2 and minus 4x. Figure 3, there are two sign changes, so there are either 2 or 0 positive real roots. Next, we examine letter 1d453 minus letter 1d465 to determine the number of negative real roots. Letter 1d453 minus letter 1d465, letter 1d453, minus letter 1d465 equals minus letter 1d465, 4 minus 3, minus letter 1d465, 3 plus 6, minus letter 1d465, 2 minus 4, minus letter 1d465, minus 12 minus letter 1d465, 4 plus 3 letter 1d465, 3 plus 6 letter 1d465, 2 plus 4 letter 1d465 minus. The function f(x) equals x4 plus 3x3 plus 6x2 plus 4x12 has two sign change between x4 and 3x3 and 4x and. Figure 4 again, there are two sign changes, so there are either 2 or 0 negative real roots. There are 4 possibilities, as we can see in Table 1. Positive real zeros, negative real zeros, complex zeros, total zeros, 2, 2, 0, 4, 2, 0, 2, 4, 0, 2, 2, 4, 0, 0, 4, 4. Table 1 analysis. We can confirm the numbers of positive and negative real roots by examining a graph of the function. See Figure 5. We can see from the graph that the function has 0 positive real roots and 2 negative real roots. Graph of f, x, equals x4-3x3 plus 6x2-4x12 with x-intercepts at minus 4, 42 and minus 1. Figure 5 try, it 6 use Descartes' rule of signs to determine the maximum possible numbers of positive and negative real zeros for letter 1d453. Letter 1d465 equals 2 letter 1d465, 4 minus 10, letter 1d465, 3 plus 11 letter 1d465, 2 minus 15 letter 1d465 plus 12. Use a graph to verify the numbers of positive and negative real zeros for the function. Solving real-world applications, we have now introduced a variety of tools for solving polynomial equations. Let's use these tools to solve the bakery problem from the beginning of the section. Example 9, solving polynomial equations. A new bakery offers decorated, multi-tiered cakes for display and cutting at quinceañera and wedding celebrations, as well as sheet cakes to serve most of the guests. The bakery wants the volume of a small sheet cake to be 351 cubic inches. The cake is in the shape of a rectangular solid. They want the length of the cake to be 4 inches longer than the width of the cake and the height of the cake to be 1/3 of the width. What should the dimensions of the cake pan be? Solution: begin by writing an equation for the volume of the cake. The volume of a rectangular solid is given by letter 1d449 equals letter 1d459 letter 1d464 letter 210e. We were given that the length must be 4 inches longer than the width, so we can express the length of the cake as letter 1d459 equals letter 1d464 plus 4. We were given that the height of the cake is 1/3 of the width, so we can express the height of the cake as letter 210a equals 13 letter 1d464. Let's write the volume of the cake in terms of width of the cake. Letter 1d449 letter 1d449 equals letter 1d464 plus 4, letter 1d464. 13 letter 1d464, 13 letter 1d464, 3 plus 43 letter 1d464, 2. Substitute the given volume into this equation. 35,110,530 equals 13 letter 1d464, 3 plus 43 letter 1d464 to W3 plus 4W to letter 1d464, 3 plus 4 letter 1d464, 2 minus 1053, substitute 351 for V. Multiply both sides by 3. Subtract 1053 from both sides. Descartes' rule of signs tells us there is one positive solution. The rational zero theorem tells us that the possible rational zeros are plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 13, plus or minus 27, plus or minus 39, plus or minus 81, plus or minus 117, plus or minus 351, and plus or minus 1053. We can use synthetic division to test these possible zeros. Only positive numbers make sense as dimensions for a cake, so we need not test any negative values. Let's begin by testing values that make the most sense as dimensions for a small sheet cake. Use synthetic division to check letter 1d465 equals 1. Since 1 is not a solution, we will check letter 1d465 equals 3. Since 3 is not a solution either, we will test letter 1d465 equals 9. Synthetic division gives a remainder of 0, so 9 is a solution to the equation. We can use the relationships between the width and the other dimensions to determine the length and height of the sheet cake pan. Letter 1d459 equals letter 1d464 plus 4 equals 9 plus 4 equals 13, and letter 210e equals 13 letter 1d464 equals 13. 9 equals 3, the sheet cake pan should have dimensions 13 inches by 9 inches by 3 inches. Try it 7. A shipping container in the shape of a rectangular solid must have a volume of 84 cubic meters. The client tells the manufacturer that, because of the contents, the length of the container must be 1 meter longer than the width, and the height must be 1 meter greater than twice the width. What should the dimensions of the container be? Media access these online resources for additional instruction and practice with zeros of polynomial functions. Real zeros, factors, and graphs of polynomial functions, complex factorization theorem. Find the zeros of a polynomial function. Find the zeros of a polynomial function 2. Find the zeros of a polynomial function 3. 5 section exercises verbal 1. Describe a use for the remainder theorem. 2. Explain why the rational zero theorem does not guarantee finding zeros of a polynomial function. 3. What is the difference between rational and real zeros? 4. If Descartes' rule of signs reveals a no change of signs or one sign of changes, what specific conclusion can be drawn? 5. If synthetic division reveals a 0, why should we try that value again as a possible solution? Algebraic for the following exercises, use the remainder theorem to find the remainder. 6. Letter 1d465 4 minus 9 letter 1d465 2 plus 14 divided by letter 1d465 minus 2. 7. 3 letter 1d465 3 minus 2 letter 1d465 2 plus letter 1d465 minus 4 divided by letter 1d465 plus 3. 8. Letter 1d465 4 plus 5 letter 1d465 3 minus 4 letter 1d465 minus 17 divided by letter 1d465 plus 1, 9. Minus 3 letter 1d465 2 plus 6 letter 1d465 plus 24 divided by letter 1d465 minus 4, 10. 5 letter 1d465 5 minus 4 letter 1d465 4 plus 3 letter 1d465 3 minus 2 letter 1d465 2 plus letter 1d465 minus 1 divided by letter 1d465 plus 6, 11. Letter 1d465 4 minus 1 divided by letter 1d465 minus 4, 12. 3 letter 1d465 3 plus 4 letter 1d465 2 minus 8 letter 1d465 plus 2 divided by letter 1d465 minus 3, 13. 4 letter 1d465 3 plus 5 letter 1d465 2 minus 2 letter 1d465 plus 7 divided by letter 1d465 plus 2. For the following exercises, use the given factor and the factor theorem to find all real zeros for the given polynomial function. 14. Letter 1d453, letter 1d465 equals 2 letter 1d465 3 minus 9 letter 1d465 2 plus 13 letter 1d465 minus 6. Letter 1d465 minus 115. Letter 1d453. Letter 1d465 equals 2 letter 1d465 3 plus letter 1d465 2 minus 5 letter 1d465 plus 2. X plus 2 16. Letter 1d453, letter 1d465 equals 3 letter 1d465 3 plus letter 1d465 2 minus 20 letter 1d465 plus 12. X plus 3 17. Letter 1d453, letter 1d465 equals 2 letter 1d465 3 plus 3 letter 1d465 2 plus letter 1d465 plus 6. X plus 2 18. Letter 1d453, letter 1d465 equals minus 5 letter 1d465 3 plus 16 letter 1d465 2 minus 9. Letter 1d465 minus 319. X3 plus 3x2 plus 4x plus 12, 20. 4 letter 1d465, 3 minus 7, letter 1d465 plus 3. Letter 1d465 minus 121. 2 letter 1d465, 3 plus 5 letter 1d465, 2 minus 12 letter 1d465 minus 30. 2 letter 1d465 plus 5 for the following exercises. Use the rational zero theorem to find the real solution, S, to each equation. 22. Letter 1d465, 3 minus 3, letter 1d465, 2 minus 10, letter 1d465, plus 24 equals 0, 23. 2 letter 1d465, 3 plus 7, letter 1d465, 2 minus 10, letter 1d465, minus 24 equals 0, 24. Letter 1d465, 3 plus 2, letter 1d465, 2 minus 9, letter 1d465 minus 18 equals 0, 25. Letter 1d465, 3 plus 5, letter 1d465, 2 minus 16, letter 1d465 minus 80 equals 0, 26. Letter 1d465, 3 minus 3, letter 1d465, 2 minus 25, letter 1d465, plus 75 equals 0, 27. 2 letter 1d465, 3 minus 3, letter 1d465, 2 minus 32, letter 1d465, minus 15 equals 0, 28. 2 letter 1d465, 3 plus letter 1d465, 2 minus 7, letter 1d465, minus 6 equals 0, 29. 2 letter 1d465, 3 minus 3, letter 1d465, 2 minus letter 1d465, plus 1 equals 0, 30. 3 letter 1d465, 3 minus letter 1d465, 2 minus 11 letter 1d465 minus 6 equals 0, 31. 2 letter 1d465, 3 minus 5 letter 1d465, 2 plus 9 letter 1d465 minus 9 equals 0, 32. 2 letter 1d465, 3 minus 3 letter 1d465, 2 plus 4 letter 1d465 plus 3 equals 0, 33. Letter 1d465, 4 minus 2 letter 1d465, 3 minus 7 letter 1d465, 2 plus 8 letter 1d465 plus 12 equals 0, 34. Letter 1d465, 4 plus 2 letter 1d465, 3 minus 9 letter 1d465, 2 minus 2 letter 1d465, plus 8 equals 0, 35. 4 letter 1d465, 4 plus 4 letter 1d465, 3 minus 25 letter 1d465, 2 minus letter 1d465, plus 6 equals 0, 36. 2 letter 1d465, 4 minus 3 letter 1d465, 3 minus 15 letter 1d465, 2 plus 32 letter 1d465 minus 12 equals 0, 37. Letter 1d465, 4 plus 2 letter 1d465, 3 minus 4 letter 1d465, 2 minus 10 letter 1d465 minus 5 equals 0, 38. 4 letter 1d465, 3 minus 3 letter 1d465 plus 1 equals 0, 39. 8x4 plus 26x3 plus 39x2 plus 26x plus 6 for the following exercises. Find all complex solutions, real and non-real. 40. Letter 1d465, 3 plus letter 1d465, 2 plus letter 1d465 plus 1 equals 0, 41. Letter 1d465, 3 minus 8 letter 1d465, 2 plus 25 letter 1d465 minus 26 equals 0, 42. Letter 1d465, 3 plus 13 letter 1d465, 2 plus 57 letter 1d465 plus 85 equals 0, 43. 3 letter 1d465, 3 minus 4 letter 1d465, 2 plus 11 letter 1d465 plus 10 equals 0, 44. Letter 1d465, 4 plus 2 letter 1d465, 3 plus 22 letter 1d465, 2 plus 50 letter 1d465 minus 75 equals 0, 45. 2 letter 1d465, 3 minus 3 letter 1d465, 2 plus 32 letter 1d465 plus 17 equals 0. Graphical for the following exercises. Use Descartes' rule to determine the possible number of positive and negative solutions. Confirm with the given graph. 46. Letter 1d453, letter 1d465 equals letter 1d465 3 minus 147. Letter 1d453, letter 1d465 equals letter 1d465 4 minus letter 1d465 2 minus 148. Letter 1d453, letter 1d465 equals letter 1d465 3 minus 2 letter 1d465 2 minus 5 letter 1d465 plus 649. Letter 1d453, letter 1d465 equals letter 1d465 3 minus 2 letter 1d465 2 plus letter 1d465 minus 150. Letter 1d453, letter 1d465 equals letter 1d465 4 plus 2 letter 1d465 3 minus 12 letter 1d465 2 plus 14 letter 1d465 minus 551. Letter 1d453, letter 1d465 equals 2 letter 1d465 3 plus 37 letter 1d465 2 plus 200 letter 1d465 plus 352. Letter 1d453, letter 1d465 equals letter 1d465 3 minus 2 letter 1d465 2 minus 16 letter 1d465 plus 3253. Letter 1d453, letter 1d465 equals 2 letter 1d465 4 minus 5 letter 1d465 3 minus 5 letter 1d465 2 plus 5 letter 1d465 plus 354. Letter 1d453, letter 1d465 equals 2 letter 1d465 4 minus 5 letter 1d465 3 minus 14 letter 1d465 2 plus 20 letter 1d465 plus 855. Letter 1d453, letter 1d465 equals 10 letter 1d465 4 minus 21 letter 1d465 2 plus 11 numeric for the following exercises. List all possible rational zeros for the functions. 56. Letter 1d453, letter 1d465 equals letter 1d465 4 plus 3 letter 1d465 3 minus 4 letter 1d465 plus 457. Letter 1d453, letter 1d465 equals 2 letter 1d465 3 plus 3 letter 1d465 2 minus 8 letter 1d465 plus 558. Letter 1d453, letter 1d465 equals 3 letter 1d465 3 plus 5 letter 1d465 2 minus 5 letter 1d465 plus 459. Letter 1d453, letter 1d465 equals 6 letter 1d465 4 minus 10 letter 1d465 2 plus 13 letter 1d465 plus 160. Letter 1d453, letter 1d465 equals 4 letter 1d465 5 minus 10 letter 1d465 4 plus 8 letter 1d465 3 plus letter 1d465 2 minus 8 technology for the following exercises. Use your calculator to graph the polynomial function. Based on the graph, find the rational zeros. All real solutions are rational. 61 letter 1d453, letter 1d465 equals 6 letter 1d465 3 minus 7 letter 1d465 2 plus 162. Letter 1d453, letter 1d465 equals 4 letter 1d465 3 minus 4 letter 1d465 2 minus 13 letter 1d465 minus 563. Letter 1d453, letter 1d465 equals 8 letter 1d465 3 minus 6 letter 1d465 2 minus 23 letter 1d465 plus 664. Letter 1d453, letter 1d465 equals 12 letter 1d465 4 plus 55 letter 1d465 3 plus 12 letter 1d465 2 minus 117 letter 1d465 plus 5465. Letter 1d453, letter 1d465 equals 16 letter 1d465 4 minus 24 letter 1d465 3 plus letter 1d465 2 minus 15 letter 1d465 plus 25 extensions for the following exercises. Construct a polynomial function of least degree possible using the given information. 66. Real roots. 1, 1, 3, and 2 letter 1d4532 equals 2, 4, 67. Real roots: 1 with multiplicity 2 and 1 and 2, letter 1d4532, equals 2, 4, 68. Real roots: 2, 12 with multiplicity 2 and minus 3, letter 1d453 minus 3, equals minus 3, 5, 69. Real roots: minus 12, 0, 12 and minus 2, letter 1d453 minus 2, equals minus 2, 6, 70. Real roots: 4, 1, 1, 4 and minus 2, letter 1d453, minus 2, equals minus 2, 10. Real-world applications for the following exercises: find the dimensions of the box described. 71. The length is twice as long as the width. The height is 2 inches greater than the width. The volume is 192 cubic inches. 72. The length, width, and height are consecutive whole numbers. The volume is 120 cubic inches. 73. The length is 1 inch more than the width, which is 1 inch more than the height. The volume is 86, 625 cubic inches. 74. The length is 3 times the height, and the height is 1 inch less than the width. The volume is 108 cubic inches. 75. The length is 3 inches more than the width. The width is 2 inches more than the height. The volume is 120 cubic inches. For the following exercises, find the dimensions of the right circular cylinder described. 76. The radius is 3 inches more than the height. The volume is 16 letter 1d70b cubic meters. 77. The height is 1 less than 1/2 the radius. The volume is 72 letter 1d70b cubic meters. 78. The radius and height differ by 1 meter. The radius is larger, and the volume is 48 letter 1d70b cubic meters. 79. The radius and height differ by 2 meters. The height is greater, and the volume is 28. 125 letter 1d70b cubic meters. 80. The radius is 13 meter greater than the height. The volume is 989 letter 1d70b cubic meters. Learning objectives. In this section, you will use arrow notation, solve applied problems involving rational functions, find the domains of rational functions, identify vertical asymptotes, identify horizontal asymptotes, graph rational functions. Suppose we know that the cost of making a product is dependent on the number of items, x, produced. This is given by the equation letter 1d436, letter 1d465, equals 15, 0, 0, 0, letter 1d465 minus 0. 1x2 plus 1,000. If we want to know the average cost for producing x items, we would divide the cost function by the number of items, x, the average cost function, which yields the average cost per item for x items produced is letter 1d453, letter 1d465 equals 15, 0, 0, 0, letter 1d465 minus 0. 1x2 plus 1000x. Many other application problems require finding an average value in a similar way, giving us variables in the denominator. Written without a variable in the denominator, this function will contain a negative integer power. In the last few sections, we have worked with polynomial functions, which are functions with non-negative integers for exponents. In this section, we explore rational functions, which have variables in the denominator. Using arrow notation, we have seen the graphs of the basic reciprocal function and the squared reciprocal function from our study of toolkit functions. Examine these graphs, as shown in Figure 1, and notice some of their features. Graphs of f x equals 1/x and f x equals 1/x2. Figure 1. Several things are apparent if we examine the graph of letter 1d453, letter 1d465, equals 1 letter 1d465. On the left branch of the graph, the curve approaches the x-axis, letter 1d466 equals 0, as letter 1d465 right infinity. As the graph approaches, from the left the curve drops, but as we approach 0 from the right, the curve rises. Finally, on the right branch of the graph, the curve approaches the x-axis, letter 1d466 equals 0, as, to summarize, we use arrow notation to show that x, or letter 1d453, letter 1d465, is approaching a particular value. See Table 1. Symbol meaning, letter 1d465, right arrow, letter 1d44e minus. X approaches A. From the left, letter 1d465, letter 1d44e. but close to A. The x approaches A. From the right, letter 1d465, letter 1d44e. But close to A. Letter 1d465, right infinity. X approaches infinity, x increases without bound. Letter 1d465, right minus infinity. X approaches negative infinity, x decreases without bound. Letter 1d453, letter 1d465, right infinity. The output approaches infinity. The output increases without bound. Letter 1d453, letter 1d465, right minus infinity. The output approaches negative infinity. The output decreases without bound. Letter 1d453, letter 1d465, right, arrow letter 1d44e. The output approaches A. Table 1. Local behavior of letter 1d453, letter 1d465, equals 1 letter 1d465. Let's begin by looking at the reciprocal function. Letter 1d453, letter 1d465, equals 1 letter 1d465. We cannot divide by 0, which means the function is undefined at letter 1d465 equals 0, so 0 is not in the domain. As the input values approach 0 from the left side, becoming very small negative values, the function values decrease without bound. In other words, they approach negative infinity. We can see this behavior in Table 2. X, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 10, 100, 1010, 0. Table 2. We write an arrow notation. As letter 1d465, right arrow 0 minus. Letter 1d453, letter 1d465, right minus infinity. As the input values approach 0 from the right side, becoming very small positive values, the function values increase without bound, approaching infinity. We can see this behavior in Table 3. X, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 10, 100, 1010, 0, 0, 0. Table 3. We write an arrow notation. As letter 1d465, right arrow 0 plus, letter 1d453, letter 1d465, right infinity. See Figure 2. Graph of f x equals 1/x, which denotes the end behavior. As x goes to negative infinity, fx goes to 0, and as x goes to 0, fx goes to negative infinity. As x goes to positive infinity, fx goes to 0, and as x goes to 0 plus, fx goes to positive infinity. Figure 2. This behavior creates a vertical asymptote, which is a vertical line that the graph approaches but never crosses. In this case, the graph is approaching the vertical line. As the input becomes close to 0, see Figure 3. Graph of fx equals 1/x with its vertical asymptote at x equals 0. Figure 3. Vertical asymptote. A vertical asymptote of a graph is a vertical line letter 1d465 equals letter 1d44e, where the graph tends toward positive or negative infinity as the input approaches A, from either the left or the right. We write, as letter 1d465, right arrow letter 1d44e, letter 1d453, letter 1d465, right plus infinity, or letter 1d465, right arrow letter 1d44e plus, letter 1d453, letter 1d465, right plus infinity. End behavior of letter 1d453, letter 1d465, equals 1 letter 1d465. As the values of x approach infinity, the function values approach 0. As the values of x approach negative infinity, the function values approach 0. See Figure 4. Symbolically, using arrow notation. As and as letter 1d465 right minus infinity, letter 1d453, letter 1d465, right arrow 0. Graph of f, x, equals 1/x, which highlights the segments of the turning points to denote their end behavior. Figure 4. Based on this overall behavior and the graph, we can see that the function approaches, but never actually reaches 0. It seems to level off as the inputs become large. This behavior creates a horizontal asymptote, a horizontal line that the graph approaches as the input increases or decreases without bound. In this case, the graph is approaching the horizontal line letter 1d466 equals 0. See Figure 5. Graph of f, x equals 1/x with its vertical asymptote at x equals 0 and its horizontal asymptote at y equals 0. Figure 5. Horizontal asymptote. A horizontal asymptote of a graph is a horizontal line, letter 1D466 equals letter 1D44F, where the graph approaches the line as the inputs increase or decrease without bound. We write as letter 1D465 right infinity or letter 1D465 right minus infinity, letter 1D453, letter 1D465 right arrow letter 1D44F. Example 1. Using arrow notation. Use arrow notation to describe the end behavior and local behavior of the function graphed in Figure 6. Graph of f(x) equals 1 slash x2 plus 4 with its vertical asymptote at x equals 2 and its horizontal asymptote at y equals 4. Figure 6. Solution. Notice that the graph is showing a vertical asymptote at letter 1D465 equals 2, which tells us that the function is undefined at letter 1D465 equals 2. As letter 1D465 right arrow 2 minus, letter 1D453, letter 1D465 right minus infinity, and as letter 1D465 right arrow 2 plus, letter 1D453, letter 1D465 right infinity. And as the inputs decrease without bound, the graph appears to be leveling off at output values of 4, indicating a horizontal asymptote at letter 1D466 equals 4. As the inputs increase without bound, the graph levels off at 4. As letter 1D465 right infinity, letter 1D453, letter 1D465, right arrow 4, and as letter 1D465 right minus infinity, letter 1D453, letter 1D465, right arrow 4. Try it 1. Use arrow notation to describe the end behavior and local behavior for the reciprocal squared function. Example 2. Using transformations to graph a rational function. Sketch a graph of the reciprocal function, shifted 2 units to the left and up 3 units. Identify the horizontal and vertical asymptotes of the graph, if any. Solution. Shifting the graph left 2 and up 3 would result in the function letter 1D453, letter 1D465, equals 1 letter 1D465 plus 2 plus 3. Or equivalently, by giving the terms a common denominator, letter 1D453, letter 1D465, equals 3 letter 1D465 plus 7 letter 1D465 plus 2. The graph of the shifted function is displayed in Figure 7. Graph of f(x) equals 1 slash x plus 2 plus 3 with its vertical asymptote at x equals 2 and its horizontal asymptote at y equals 3. Figure 7. Notice that this function is undefined at letter 1D465 equals minus 2. And the graph also is showing a vertical asymptote at letter 1D465 equals minus 2. As letter 1D465 right minus 2 minus letter 1D453, letter 1D465, right minus infinity. And as letter 1D465 right minus 2 plus letter 1D453, letter 1D465 right infinity. As the inputs increase and decrease without bound, the graph appears to be leveling off at output values of 3, indicating a horizontal asymptote at letter 1D466 equals 3. As letter 1D465 right plus infinity, letter 1D453, letter 1D465 right arrow 3. Analysis. Notice that horizontal and vertical asymptotes are shifted left 2 and up 3 along with the function. Try it 2. Sketch the graph and find the horizontal and vertical asymptotes of the reciprocal squared function that has been shifted right 3 units and down 4 units. Solving applied problems involving rational functions. In example 2, we shifted a toolkit function in a way that resulted in the function letter 1D453, letter 1D465, equals 3 letter 1D465 plus 7 letter 1D465 plus 2. This is an example of a rational function. A rational function is a function that can be written as the quotient of 2 polynomial functions. Many real-world problems require us to find the ratio of 2 polynomial functions. Problems involving rates and concentrations often involve rational functions. Rational function. A rational function is a function that can be written as the quotient of 2 polynomial functions letter 1D443, letter 1D465, and letter 1D444, letter 1D465, letter 1D453, letter 1D465 equals letter 1D443, letter 1D465, letter 1D444. Letter 1D465 equals letter 1d44, letter 1d45d, letter 1d465, letter 1d45d, plus letter 1d44, letter 1d45d, minus 1, letter 1d465, letter 1d45d, minus 1 plus letter 1d44e, 1 letter 1d465, plus letter 1d44e, 0, letter 1d44f, letter 1d45e, letter 1d465, letter 1d45e, plus letter 1d44f, letter 1d45e, minus 1, letter 1d465, letter 1d45e, minus 1 plus letter 1d44f, 1 letter 1d465, plus letter 1d44f, 0, letter 1d444, letter 1d465, not equal to 0. Example 3. Solving an applied problem involving a rational function. After running out of prepackaged supplies, a nurse in a refugee camp is preparing an intravenous sugar solution for patients in the camp hospital. A large mixing tank currently contains 100 gallons of distilled water into which 5 pounds of sugar have been mixed. A tap will open, pouring 10 gallons per minute of distilled water into the tank. At the same time, sugar is poured into the tank at a rate of 1 pound per minute. Find the ratio of sugar to water in pounds per gallon in the tank after 12 minutes. Is that a greater ratio of sugar to water in pounds per gallon than at the beginning? Solution. Let T be the number of minutes since the tap opened. Since the water increases at 10 gallons per minute and the sugar increases at 1 pound per minute, these are constant rates of change. This tells us the amount of water in the tank is changing linearly, as is the amount of sugar in the tank. We can write an equation independently for each: water, letter 1d44a, letter 1d461, sugar, letter 1d446, letter 1d461, equals 100 plus 10 letter 1d461, in gallons 5 plus 1 tin pounds. The ratio of sugar to water in pounds per gallon, C, will be the ratio of pounds of sugar to gallons of water. Letter 1d436, letter 1d461 equals 5 plus letter 1d461, 100 plus 10 letter 1d461. The ratio of sugar to water in pounds per gallon after 12 minutes is given by evaluating letter 1d436, letter 1d461. At letter 1d461 equals 12. Letter 1d436, 12 equals 5 plus 12,100 plus 10, 12, 17,220. This means the ratio of sugar to water in pounds per gallon is 17 pounds of sugar to 220 gallons of water. At the beginning, the ratio of sugar to water in pounds per gallon is letter 1d436, 0, equals 5 plus 0, 100 plus 10, 0, 120. Since 17,220, approximately 0, 0, 8, 120 equals 0, 5. The ratio of sugar to water in pounds per gallon is greater after 12 minutes than at the beginning. Try it 3. There are 1,200 first-year and 1,500 second-year students at a rally at noon. After 12 p.m., 20 first-year students arrive at the rally every 5 minutes, while 15 second-year students leave the rally. Find the ratio of first-year to second-year students at 1 p.m. Finding the domains of rational functions. A vertical asymptote represents a value at which a rational function is undefined, so that value is not in the domain of the function. A reciprocal function cannot have values in its domain that cause the denominator to equal 0. In general, to find the domain of a rational function, we need to determine which inputs would cause division by 0. Domain of a rational function. The domain of a rational function includes all real numbers except those that cause the denominator to equal 0. How to? Given a rational function, find the domain. Set the denominator equal to 0. Solve to find the x values that cause the denominator to equal 0. The domain is all real numbers except those found in step 2. Example 4. Finding the domain of a rational function. Find the domain of letter 1d453, letter 1d465, equals letter 1d465 plus 3 letter 1d465, 2 minus 9. Solution. Begin by setting the denominator equal to 0 and solving. Letter 1d465, 2 minus 9, letter 1d465 to letter 1d465 equals 0, 9 plus or minus 3. The denominator is equal to 0 when letter 1d465 equals plus 3. The domain of the function is all real numbers except letter 1d465 equals plus 3. Analysis. A graph of this function, as shown in Figure 8, confirms that the function is not defined when letter 1d465 equals plus 3. Graph of f x equals 1/x3 with its vertical asymptote at x equals 3 and its horizontal asymptote at y equals 0. Figure 8. There is a vertical asymptote at letter 1d465 equals 3, and a hole in the graph at letter 1d465 equals minus 3. We will discuss these types of holes in greater detail later in this section. Try it 4. Find the domain of letter 1d453, letter 1d465 equals 4 letter 1d465 5, letter 1d465 minus 1, letter 1d465 minus 5. Identifying vertical asymptotes of rational functions. By looking at the graph of a rational function, we can investigate its local behavior and easily see whether there are asymptotes. We may even be able to approximate their location. Even without the graph, however, we can still determine whether a given rational function has any asymptotes and calculate their location. Vertical asymptotes. The vertical asymptotes of a rational function may be found by examining the factors of the denominator that are not common to the factors in the numerator. Vertical asymptotes occur at the zeros of such factors. How to, given a rational function, identify any vertical asymptotes of its graph. Factor the numerator and denominator. Note any restrictions in the domain of the function. Reduce the expression by canceling common factors in the numerator and the denominator. Note any values that cause the denominator to be 0 in this simplified version. These are where the vertical asymptotes occur. Note any restrictions in the domain where asymptotes do not occur. These are removable discontinuities or holes. Example 5. Identifying vertical asymptotes. Find the vertical asymptotes of the graph of letter 1d458, letter 1d465, equals 5 plus 2 letter 1d465, 22, minus letter 1d465, minus letter 1d465, 2. Solution. First, factor the numerator and denominator. Letter 1d458, letter 1d465, equals 5 plus 2 letter 1d465, 22, minus letter 1d465, minus letter 1d465, 25, plus 2 letter 1d465, 2, 2 plus letter 1d465. 1 minus letter 1d465. To find the vertical asymptotes, we determine where this function will be undefined by setting the denominator equal to 0. 2 plus letter 1d465. 1 minus letter 1d465. Letter 1d465 equals 0 minus 2, 1. Neither letter 1d465 equals 2, nor are zeros of the numerator, so the two values indicate two vertical asymptotes. The graph in Figure 9 confirms the location of the two vertical asymptotes. Graph of k, x equals 5 plus 2x2 slash 2xx2 with its vertical asymptotes at x equals 2 and x equals 1 and its horizontal asymptote at y equals 2. Figure 9. Removable discontinuities. Occasionally, a graph will contain a hole, a single point where the graph is not defined, indicated by an open circle. We call such a hole a removable discontinuity. For example, the function letter 1d453, letter 1d465, equals letter 1d465 2 minus 1 letter 1d465 2 minus 2 letter 1d465 minus 3. May be rewritten by factoring the numerator and the denominator. Letter 1d453, letter 1d465 equals letter 1d465 plus 1 letter 1d465 minus 1, letter 1d465 plus 1, letter 1d465 minus 3. Notice that letter 1d465 plus 1 is a common factor to the numerator and the denominator. The 0 of this factor, letter 1d465 equals minus 1, is the location of the removable discontinuity. Notice also that letter 1d465 3 is not a factor in both the numerator and denominator. The 0 of this factor is the vertical asymptote. See Figure 10. Note that removable discontinuities may not be visible when we use a graphing calculator, depending upon the window selected. Graph of f x equals x2-1 slash x2-2x3 with its vertical asymptote at x equals 3 and a removable discontinuity at x equals 1. Figure 10. Removable discontinuities of rational functions. A removable discontinuity occurs in the graph of a rational function at letter 1d465 equals letter 1d44e. If letter 1d44e is a 0 for a factor in the denominator that is common with a factor in the numerator, we factor the numerator and denominator and check for common factors. If we find any, we set the common factor equal to 0 and solve. This is the location of the removable discontinuity. This is true if the multiplicity of this factor is greater than or equal to that in the denominator. If the multiplicity of this factor is greater in the denominator, then there is still an asymptote at that value. Example 6. Identifying vertical asymptotes and removable discontinuities for a graph. Find the vertical asymptotes and removable discontinuities of the graph of letter 1d458, letter 1d465, equals letter 1d465 minus 2, letter 1d465, 2 minus 4. Solution. Factor the numerator and the denominator. Letter 1d458, letter 1d465 equals letter 1d465 minus 2, letter 1d465 minus 2, letter 1d465 plus 2. Notice that there is a common factor in the numerator, and the denominator, letter 1d465 2. The 0 for this factor is letter 1d465 equals 2. This is the location of the removable discontinuity. Notice that there is a factor in the denominator that is not in the numerator, letter 1d465 plus 2. The 0 for this factor is letter 1d465 equals minus 2. The vertical asymptote is letter 1d465 equals minus 2. See figure 11. Graph of k, x equals x2 slash x2. X plus 2 with its vertical asymptote at x equals 2 and a removable discontinuity at x equals 2. Figure 11. The graph of this function will have the vertical asymptote at letter 1d465 equals minus 2, but at letter 1d465 equals 2. The graph will have a hole. Try at 5. Find the vertical asymptotes and removable discontinuities of the graph of letter 1d453, letter 1d465, equals letter 1d465 2 minus 25, letter 1d465 3 minus 6, letter 1d465 2, plus 5 letter 1d465. Identifying horizontal asymptotes of rational functions, while vertical asymptotes describe the behavior of a graph as the output gets very large or very small. Horizontal asymptotes help describe the behavior of a graph as the input gets very large or very small. Recall that a polynomial's end behavior will mirror that of the leading term. Likewise, a rational function's end behavior will mirror that of the ratio of the function, that is, the ratio of the leading terms. There are 3 distinct outcomes when checking for horizontal asymptotes. Case 1. If the degree of the denominator degree of the numerator, there is a horizontal asymptote at letter 1d466 equals 0. Example. Letter 1d453, letter 1d465, equals 4 letter 1d465 plus 2 letter 1d465 2 plus 4 letter 1d465 minus 5. In this case, the end behavior is letter 1d453, letter 1d465, approximately 4 letter 1d465 letter 1d465 2 equals 4 letter 1d465. This tells us that, as the inputs increase or decrease without bound, this function will behave similarly to the function letter 1d454, letter 1d465 equals 4 letter 1d465, and the outputs will approach 0, resulting in a horizontal asymptote at letter 1d466 equals 0. See figure 12. Note that this graph crosses the horizontal asymptote. Graph of f x equals 4x plus 2 slash x2 plus 4x5 with its vertical asymptotes at x equals 5 and x equals 1 and its horizontal asymptote at y equals 0. Figure 12, horizontal asymptote letter 1d466 equals 0. When letter 1d453, letter 1d465 equals letter 1d45d, letter 1d465, letter 1d45e, letter 1d465. Letter 1d45e, letter 1d465, not equal to 0 where degree O f letter 1d45d degree of q. Case 2, if the degree of the denominator degree of the numerator by 1, we get a slant asymptote. Example, letter 1d453, letter 1d465, equals 3 letter 1 d465 2 minus 2 letter 1 d465 plus 1 letter 1 d465 minus 1. In this case, the end behavior is. This tells us that as the inputs increase or decrease without bound, this function will behave similarly to the function letter 1 d454. Letter 1 d465 equals 3 letter 1 d465. As the inputs grow large, the outputs will grow and not level off, so this graph has no horizontal asymptote. However, the graph of letter 1 d454, letter 1 d465, equals 3 letter 1 d465, looks like a diagonal line, and since letter 1 d453 will behave similarly to letter 1 d454, it will approach a line close to letter 1 d466 equals 3 letter 1 d465. This line is a slant asymptote. To find the equation of the slant asymptote, divide 3 letter 1 d465 2 minus 2 letter 1 d465 plus 1 letter 1 d465 minus 1. The quotient is 3 letter 1 d465 plus 1, and the remainder is 2. The slant asymptote is the graph of the line letter 1 d454, letter 1 d465, equals 3 letter 1 d465 plus 1. See Figure 13. Graph of f, x equals 3x2-2x plus 1/x1 with its vertical asymptote at x equals 1 and a slant asymptote 80 equals 3x plus 1. Figure 13 slant asymptote when letter 1 d453, letter 1 d465 equals letter 1 d45d, letter 1 d465, letter 1 d45e, letter 1 d465. Letter 1 d45e, letter 1 d465 not equal to 0. Where degree of letter 1 d45d degree of letter 1 d45e by 1. Case 3. If the degree of the denominator equals degree of the numerator, there is a horizontal asymptote at letter 1 d466 equals letter 1 d44e, letter 1 d45b, letter 1 d44f, letter 1 d45b, where letter 1 d44e, letter 1 d45b, and letter 1 d44f, letter 1 d45b are the leading coefficients of letter 1 d45d, letter 1 d465, and letter 1 d45e, letter 1 d465. For letter 1 d453, letter 1 d465 equals letter 1 d45d, letter 1 d465, letter 1 d45e, letter 1 d465. Letter 1 d45e, letter 1 d465 not equal to 0. Example, letter 1 d453, letter 1 d465 equals 3 letter 1 d465 2 plus 2 letter 1 d465 2 plus 4 letter 1 d465 minus 5. In this case, the end behavior is letter 1 d453, letter 1 d465, approximately 3 letter 1 d465 to letter 1 d465, 2 equals 3. This tells us that as the inputs grow large, this function will behave like the function letter 1 d454, letter 1 d465 equals 3, which is a horizontal line. As letter 1 d465 right plus infinity, letter 1 d453, letter 1 d465 right arrow 3, resulting in a horizontal asymptote at letter 1 d466 equals 3. See Figure 14. Note that this graph crosses the horizontal asymptote. Graph of f, x equals 3x2 plus 2 slash x2 plus 4x5, with its vertical asymptotes at x equals 5 and x equals 1, and its horizontal asymptote at y equals 3. Figure 14 horizontal asymptote when letter 1 d453, letter 1 d465 equals letter 1 d45d, letter 1 d465, letter 1 d45e, letter 1 d465, letter 1 d45e, letter 1 d465 not equal to 0 where degree of letter 1 d45d equals degree of q. Notice that, while the graph of a rational function will never cross a vertical asymptote, the graph may or may not cross a horizontal or slant asymptote. Also, although the graph of a rational function may have many vertical asymptotes, the graph will have at most one horizontal or slant asymptote. It should be noted that, if the degree of the numerator is larger than the degree of the denominator by more than 1, the end behavior of the graph will mimic the behavior of the reduced end behavior fraction. For instance, if we had the function letter 1 d453, letter 1 d465 equals 3 letter 1 d465, 5 minus letter 1 d465 to x plus 3, with end behavior letter 1 d453, letter 1 d465 approximately 3 letter 1 d465, 5 letter 1 d465 equals 3 letter 1 d465, 4. The end behavior of the graph would look similar to that of an even polynomial with a positive leading coefficient. Letter 1 d465 right plus infinity, letter 1 d453, letter 1 d465 right infinity. Horizontal asymptotes of rational functions. The horizontal asymptote of a rational function can be determined by looking at the degrees of the numerator and denominator. Degree of numerator is less than degree of denominator. Horizontal asymptote at letter 1 d466 equals 0. Degree of numerator is greater than degree of denominator by 1. No horizontal asymptote. Slant asymptote. Degree of numerator is equal to degree of denominator. Horizontal asymptote at ratio of leading coefficients. Example 7. Identifying horizontal and slant asymptotes. For the functions listed, identify the horizontal or slant asymptote. A letter 1 d454, letter 1 d465, equals 6 letter 1 d465, 3 minus 10, letter 1 d465 to x, 3 plus 5 x2. B letter 210e, letter 1 d465, equals letter 1 d465, 2 minus 4 letter 1 d465, plus 1 letter 1 d465 plus 2. See letter 1 d458. Letter 1 d465 equals letter 1 d465, 2 plus 4 letter 1 d465 letter 1 d465, 3 minus 8. Solution. For these solutions, we will use letter 1 d453. Letter 1 d465 equals letter 1 d45d letter 1 d465 letter 1 d45e letter 1 d465. Letter 1 d45e, letter 1 d465, not equal to 0. A letter 1 d454, letter 1 d465, equals 6 letter 1 d465, 3 minus 10, letter 1 d465 to x, 3 plus 5 x2. The degree of letter 1 d45d equals degree of letter 1 d45e equals 3. So we can find the horizontal asymptote by taking the ratio of the leading terms. There is a horizontal asymptote at letter 1 d466 equals 62, or letter 1 d466 equals 3. B letter 210e, letter 1 d465 equals letter 1 d465, 2 minus 4 letter 1 d465, plus 1 letter 1 d465 plus 2. The degree of letter 1 d45d equals 2, and degree of letter 1 d45e equals 1. Since letter 1 d45d, letter 1 d45e. By 1, there is a slant asymptote found at letter 1 d465, 2 minus 4 letter 1 d465, plus 1 letter 1 d465 plus 2. The quotient is letter 1 d465, 6, and the remainder is 13. There is a slant asymptote at letter 1 d466 equals letter 1 d465, 6. See letter 1 d458. Letter 1 d465 equals letter 1 d465, 2, plus 4 letter 1 d465 letter 1 d465, 3 minus 8. The degree of letter 1 d45d equals 2. Degree of letter 1 d45e equals 3. So there is a horizontal asymptote, letter 1 d466 equals 0. Example 8. Identifying horizontal asymptotes. In the sugar concentration problem earlier, we created the equation letter 1 d436, letter 1 d461, equals 5 plus letter 1 d461, 100 plus 10 letter 1 d461. Find the horizontal asymptote and interpret it in context of the problem. Solution. Both the numerator and denominator are linear, degree 1. Because the degrees are equal, there will be a horizontal asymptote at the ratio of the leading coefficients. In the numerator, the leading term is letter 1 d461, with coefficient 1. In the denominator, the leading term is 10 letter 1 d461, with coefficient 10. The horizontal asymptote will be at the ratio of these values. Letter 1 d461 right infinity, letter 1 d436, letter 1 d461, right arrow 110. This function will have a horizontal asymptote at letter 1 d466 equals 110. This tells us that as the values of t increase, the values of letter 1 d436 will approach 110. In context, this means that as more time goes by, the concentration of sugar in the tank will approach 1/10 of a pound of sugar per gallon of water, or 110 pounds per gallon. Example 9. Identifying horizontal and vertical asymptotes. Find the horizontal and vertical asymptotes of the function. letter 1d453, letter 1d465 equals, letter 1d465 minus 2, letter 1d465 plus 3, letter 1d465 minus 1, letter 1d465 plus 2, letter 1d465 minus 5. Solution. First, note that this function has no common factors, so there are no potential removable discontinuities. The function will have vertical asymptotes when the denominator is 0, causing the function to be undefined. The denominator will be 0 at letter 1d465 equals 1, 2, and 5, indicating vertical asymptotes at these values. The numerator has degree 2, while the denominator has degree 3. Since the degree of the denominator is greater than the degree of the numerator, the denominator will grow faster than the numerator, causing the outputs to tend towards 0 as the inputs get large. And so, as letter 1d465 right plus infinity, letter 1d453, letter 1d465, right arrow 0. This function will have a horizontal asymptote at letter 1d466 equals 0. See figure 15. Graph of f(x) equals x2, x plus 3 slash x1, x plus 2, x5, with its vertical asymptotes at x equals 2, x equals 1, and x equals 5, and its horizontal asymptote at y equals 0. Figure 15. Try at 6. Find the vertical and horizontal asymptotes of the function. Letter 1d453, letter 1d465 equals 2 letter 1d465 minus 1, 2 letter 1d465 plus 1, letter 1d465 minus 2, letter 1d465 plus 3. Intercepts of rational functions. A rational function will have a y-intercept at letter 1d453, 0, if the function is defined at 0. A rational function will not have a y-intercept if the function is not defined at 0. Likewise, a rational function will have x-intercepts at the inputs that cause the output to be 0. Since a fraction is only equal to 0 when the numerator is 0, x-intercepts can only occur when the numerator of the rational function is equal to 0. Example 10. Finding the intercepts of a rational function. Find the intercepts of letter 1d453, letter 1d465 equals, letter 1d465 minus 2, letter 1d465 plus 3, letter 1d465 minus 1, letter 1d465 plus 2, letter 1d465 minus 5. Solution. We can find the y-intercept by evaluating the function at 0. Letter 1d453, 0 equals 0 minus 2, 0 plus 3, 0 minus 1, 0 plus 2, 0 minus 5, minus 610 minus 35 minus 0. 6. The x-intercepts will occur when the function is equal to 0. 0, 0, letter 1d465 equals, letter 1d465 minus 2, letter 1d465 plus 3, letter 1d465 minus 1, letter 1d465 plus 2, letter 1d465 minus 5, letter 1d465 minus 2, letter 1d465 plus 3, 2, minus 3. This is 0 when the numerator is 0. The y-intercept is 0, 0, 6. The x-intercepts are 20 and 30. See figure 16. Graph of f(x) equals x2, x plus 3 slash x1, x plus 2, x5, with its vertical asymptotes at x equals 2, x equals 1, and x equals 5, its horizontal asymptote at y equals 0, and its intercepts at minus 3, 0, 0, 6, and 2, 0, figure 16. Try at 7. Given the reciprocal squared function that is shifted right 3 units and down 4 units, write this as a rational function. Then find the x and y-intercepts and the horizontal and vertical asymptotes. Graphing rational functions. In example 9, we see that the numerator of a rational function reveals the x-intercepts of the graph, whereas the denominator reveals the vertical asymptotes of the graph. As with polynomials, factors of the numerator may have integer powers greater than 1. Fortunately, the effect on the shape of the graph at those intercepts is the same as we saw with polynomials. The vertical asymptotes associated with the factors of the denominator will mirror one of the two toolkit reciprocal functions. When the degree of the factor in the denominator is odd, the distinguishing characteristic is that on one side of the vertical asymptote, the graph heads towards positive infinity, and on the other side, the graph heads towards negative infinity. See figure 17. Graph of y, x with its vertical asymptote at x equals 0. Figure 17. When the degree of the factor in the denominator is even, the distinguishing characteristic is that the graph either heads toward positive infinity on both sides of the vertical asymptote or heads toward negative infinity on both sides. See Figure 18. Graph of y/x2 with its vertical asymptote at x equals 0. Figure 18, for example, the graph of letter 1d453, letter 1d465 equals letter 1d465 plus 1, 2, letter 1d465 minus 3, letter 1d465 plus 3, 2, letter 1d465 minus 2 is shown in Figure 19. Graph of f(x) equals x plus 1, 2, x3 slash x plus 3, 2x2 with its vertical asymptotes at x equals 3 and x equals 2, its horizontal asymptote at y equals 1, and its intercepts at minus 1, 0, 0, 1, 6, and 3, 0. Figure 19, at the x-intercept letter 1d465 equals minus 1 corresponding to the letter 1d465 plus 1, 2 factor of the numerator. The graph bounces, consistent with the quadratic nature of the factor. At the x-intercept, corresponding to the letter 1d465 minus 3 factor of the numerator, the graph passes through the axis as we would expect from a linear factor. At the vertical asymptote letter 1d465 equals minus 3 corresponding to the letter 1d465 plus 3, 2 factor of the denominator, the graph heads towards positive infinity on both sides of the asymptote, consistent with the behavior of the function letter 1d453. Letter 1d465 equals 1 letter 1d465 At the vertical asymptote letter 1d465 equals 2, corresponding to the letter 1d465 minus 2 factor of the denominator. The graph heads towards positive infinity on the left side of the asymptote and towards negative infinity on the right side. How to give an irrational function, sketch a graph. Evaluate the function at 0 to find the y-intercept. Factor the numerator and denominator. For factors in the numerator not common to the denominator, determine where each factor of the numerator is 0 to find the x-intercepts. Find the multiplicities of the x-intercepts to determine the behavior of the graph at those points. For factors in the denominator, note the multiplicities of the zeros to determine the local behavior. For those factors not common to the numerator, find the vertical asymptotes by setting those factors equal to 0 and then solve. For factors in the denominator common to factors in the numerator, find the removable discontinuities by setting those factors equal to 0 and then solve. Compare the degrees of the numerator and the denominator to determine the horizontal or slant asymptotes. Sketch the graph. Example 11. Graphing a rational function. Sketch a graph of letter 1d453, letter 1d465 equals letter 1d465 plus 2, letter 1d465 minus 3, letter 1d465 plus 1, 2, letter 1d465 minus 2. Try at 8 given the function letter 1d453. Letter 1d465 equals letter 1d465 plus 2, 2, letter 1d465 minus 2, 2, letter 1d465 minus 1, 2, letter 1d465 minus 3. Use the characteristics of polynomials and rational functions to describe its behavior and sketch the function. Writing rational functions. Now that we have analyzed the equations for rational functions and how they relate to a graph of the function, we can use information given by a graph to write the function. A rational function written in factored form will have an x-intercept where each factor of the numerator is equal to 0. An exception occurs in the case of a removable discontinuity. As a result, we can form a numerator of a function whose graph will pass through a set of x-intercepts by introducing a corresponding set of factors. Likewise, because the function will have a vertical asymptote where each factor of the denominator is equal to 0, we can form a denominator that will produce the vertical asymptotes by introducing a corresponding set of factors. Writing rational functions from intercepts and asymptotes. If a rational function has x-intercepts at letter 1d465 equals letter 1d465 1, letter 1d465 2, letter 1d465 letter 1d45b, vertical asymptotes at letter 1d465 equals letter 1d463 1, letter 1d463 2, letter 1d463 letter 1d45a, and no letter 1d465 letter 1d456 equals any letter 1d463 letter 1d457, then the function can be written in the form letter 1d453, letter 1d465 equals letter 1d440, letter 1d465 minus letter 1d465 1, letter 1d45d1, letter 1d465 minus letter 1d465 2, letter 1d45d2, letter 1d465 minus letter 1d465 letter 1d45b, letter 1d45d letter 1d45b, letter 1d465 minus letter 1d463, 1 letter 1d45e1, where the powers pi or chi on each factor can be determined by the behavior of the graph at the corresponding intercept or asymptote, and the stretch factor a can be determined given a value of the function other than the x-intercept, or by the horizontal asymptote if it is non-zero. How to given a graph of a rational function, write the function. Determine the factors of the numerator. Examine the behavior of the graph at the x-intercepts to determine the zeros and their multiplicities. This is easy to do when finding the simplest function with small multiplicities, such as 1 or 3, but may be difficult for larger multiplicities, such as 5 or 7, for example. Determine the factors of the denominator. Examine the behavior on both sides of each vertical asymptote to determine the factors and their powers. Use any clear point on the graph to find the stretch factor. Example 12, writing a rational function from intercepts and asymptotes, write an equation for the rational function shown in Figure 22. Graph of a rational function. Figure 22 media access, these online resources for additional instruction and practice with rational functions. Graphing rational functions, find the equation of a rational function, determining vertical and horizontal asymptotes, find the intercepts, asymptotes, and whole of a rational function 5. 6th section, Exercises Verbal 1. What is the fundamental difference in the algebraic representation of a polynomial function and a rational function? 2. What is the fundamental difference in the graphs of polynomial functions and rational functions? 3. If the graph of a rational function has a removable discontinuity, what must be true of the functional rule? 4. Can a graph of a rational function have no vertical asymptote? If so, how? 5. Can a graph of a rational function have no x-intercepts? If so, how? Algebraic for the following exercises, find the domain of the rational functions. 6. Letter 1d453, letter 1d465 equals letter 1d465 minus 1 letter 1d465 plus 2 7. Letter 1d453, letter 1d465 equals letter 1d465 plus 1 letter 1d465 2 minus 1 8. Letter 1d453, letter 1d465 equals letter 1d465 2 plus 4 letter 1d465 2 minus 2 letter 1d465 minus 8 9. Letter 1d453, letter 1d465 equals letter 1d465 2 plus 4 letter 1d465 minus 3 letter 1d465 4 minus 5 letter 1d465 2 plus 4 for the following exercises. Find the domain, vertical asymptotes, and horizontal asymptotes of the functions. 10. Letter 1d453, letter 1d465 equals 4 letter 1d465 minus 1 11. Letter 1d453, letter 1d465 equals 25 letter 1d465 plus 2 12. Letter 1d453, letter 1d465 equals letter 1d465 letter 1d465 2 minus 9 13. Letter 1d453, letter 1d465 equals letter 1d465 letter 1d465 2 plus 5 letter 1d465 minus 36 14. Letter 1d453, letter 1d465 equals 3 plus letter 1d465 letter 1d465 3 minus 27 15. Letter 1d453, letter 1d465 equals 3 letter 1d465 minus 4 letter 1d465 3 minus 16 letter 1d465 16. Letter 1d453, letter 1d465 equals letter 1d465 2 minus 1 letter 1d465 3 plus 9 letter 1d465 2 plus 14 letter 1d465 17. Letter 1d453, letter 1d465 equals letter 1d465 plus 5 letter 1d465 2 minus 25 18. Letter 1 D453, letter 1 D465 equals letter 1 D465 minus 4 letter 1 D465 minus 619. Letter 1 D453, letter 1 D465 equals 4 minus 2 letter 1 D465 3 letter 1 D465 minus 1 for the following exercises. Find the x and y intercepts for the functions. 20. Letter 1 D453. Letter 1 D465 equals letter 1 D465 plus 5 letter 1 D465 2 plus 421. Letter 1 D453, letter 1 D465 equals letter 1 D465 letter 1 D465 2 minus letter 1 D465 22. Letter 1 D453, letter 1 D465 equals letter 1 D465 2 plus 8 letter 1 D465 plus 7 letter 1 D465 2 plus 11 letter 1 D465 plus 3023. Letter 1 D453, letter 1 D465 equals letter 1 D465 2 plus letter 1 D465 plus 6 letter 1 D465 2 minus 10 letter 1 D465 plus 2424. Letter 1 D453, letter 1 D465 equals 94 minus 2 letter 1 D465 23 letter 1 D465 2 minus 12. For the following exercises, describe the local and end behavior of the functions. 25. Letter 1 D453, letter 1 D465 equals letter 1 D465 to x plus 126. Letter 1 D453, letter 1 D465 equals 2 letter 1 D465 letter 1 D465 minus 627. Letter 1 D453, letter 1 D465 equals minus 2 letter 1 D465 letter 1 D465 minus 628. Letter 1 D453, letter 1 D465 equals letter 1 D465 2 minus 4 letter 1 D465 plus 3 letter 1 D465 2 minus 4 letter 1 D465 minus 529. Letter 1 D453, letter 1 D465 equals 2 letter 1 D465 2 minus 326 letter 1 D465 2 plus 13 letter 1 D465 minus 5. For the following exercises, find the slant asymptote of the functions. 30. Letter 1 D453, letter 1 D465 equals 24 letter 1 D465 2 plus 6 letter 1 D465 to x plus 131. Letter 1 D453, letter 1 D465 equals 4 letter 1 D465 2 minus 102 letter 1 D465 minus 432. Letter 1 D453, letter 1 D465 equals 81 letter 1 D465 2 minus 183 letter 1 D465 minus 233. Letter 1 D453, letter 1 D465 equals 6 letter 1 D465 3 minus 5 letter 1 D465 3 letter 1 D465 2 plus 434. Letter 1 D453, letter 1 D465 equals letter 1 D465 2 plus 5 letter 1 D465 plus 4 letter 1 D465 minus 1 graphical for the following exercises. Use the given transformation to graph the function. Note the vertical and horizontal asymptotes. 35. The reciprocal function shifted up 2 units. 36. The reciprocal function shifted down 1 unit and left 3 units. 37. The reciprocal squared function shifted to the right 2 units. 38. The reciprocal squared function shifted down 2 units and right 1 unit. For the following exercises, find the horizontal intercepts, the vertical intercept, the vertical asymptotes, and the horizontal or slant asymptote of the functions. Use that information to sketch a graph. 39. Letter 1 D45D, letter 1 D465 equals 2 letter 1 D465 minus 3 letter 1 D465 plus 440. Letter 1 D45E, letter 1 D465 equals letter 1 D465 minus 53 letter 1 D465 minus 141. Letter 1 D460, letter 1 D465 equals 4, letter 1 D465 minus 2242. Letter 1 D45F, letter 1 D465 equals 5, letter 1 D465 plus 1243. Letter 1 D453, letter 1 D465 equals 3 letter 1 D465 2 minus 14 letter 1 D465 minus 53 letter 1 D465 2 plus 8 letter 1 d465 minus 1644. Letter 1 d454. Letter 1 d465 equals 2 letter 1 d465 2 plus 7 letter 1 d465 minus 153 letter 1 d465 2 minus 14 letter 1 d465 plus 1545. Letter 1 d440. Letter 1 d465 equals letter 1 d465 2 plus 2 letter 1 d465 minus 3 letter 1 d465 2 minus 146. Letter 1 d44f. Letter 1 d465 equals letter 1 d465 2 minus letter 1 d465 minus 6, letter 1 d465 2 minus 447. Letter 210e. Letter 1 d465 equals 2 letter 1 d465 2 plus letter 1 d465 minus 1 letter 1 d465 minus 448. Letter 1 d458. Letter 1 d465 equals 2 letter 1 d465 2 minus 3 letter 1 d465 minus 20 letter 1 d465 minus 549. Letter 1 d464. Letter 1 d465 equals letter 1 d465 minus 1, letter 1 d465 plus 3, letter 1 d465 minus 5. Letter 1 d465 plus 2 2 letter 1 d465 minus 4, 50. Letter 1 d467. Letter 1 d465 equals letter 1 d465 plus 2 2 letter 1 d465 minus 5. Letter 1 d465 minus 3, letter 1 d465 plus 1, letter 1 d465 plus 4 for the following exercises. Write an equation for a rational function with the given characteristics. 51. Vertical asymptotes at letter 1 d465 equals 5 and letter 1 d465 equals minus 5. X-intercepts at 20 and minus 1, 0, y-intercept at 4, 52. Vertical asymptotes at letter 1 d465 equals minus 4 and letter 1 d465 equals minus 1. X-intercepts at 10 and 50. Y-intercept at 7, 53. Vertical asymptotes at letter 1 d465 equals minus 4 and letter 1 d465 equals minus 5. X-intercepts at 40 and minus 6, 0. Horizontal asymptote at letter 1 d466 equals 754. Vertical asymptotes at letter 1 d465 equals minus 3 and letter 1 d465 equals 6. X-intercepts at minus 2, 0, and 10. Horizontal asymptote at letter 1 d466 equals minus 255. Vertical asymptote at letter 1 d465 equals minus 1. 00 at letter 1 d465 equals 2. Y-intercept at 2, 56. Vertical asymptote at letter 1 d465 equals 3. 00 at letter 1 d465 equals 1. Y-intercept at 4. For the following exercises, use the graphs to write an equation for the function. 57. Graph of a rational function with vertical asymptotes at x equals 3 and x equals 4. 58. Graph of a rational function with vertical asymptotes at x equals 3 and x equals 4. 59. Graph of a rational function with vertical asymptotes at x equals 3 and x equals 3. 60. Graph of a rational function with vertical asymptotes at x equals 3 and x equals 4. 61. Graph of a rational function with vertical asymptote at x equals 1. 62. Graph of a rational function with vertical asymptote at x equals 2. 63. Graph of a rational function with vertical asymptotes at x equals 3 and x equals 2. 64. Graph of a rational function with vertical asymptotes at x equals 2 and x equals 4. Numeric for the following exercises. Make tables to show the behavior of the function near the vertical asymptote and reflecting the horizontal asymptote 65. Letter 1 d453, letter 1 d465 equals 1 letter 1 d465 minus 266. Letter 1 d453, letter 1 d465 equals letter 1 d465 letter 1 d465 minus 367. Letter 1 d453, letter 1 d465 equals 2 letter 1 d465 letter 1 d465 plus 468. Letter 1 d453, letter 1 d465 equals 2 letter 1 d465 letter 1 d465 minus 3269. Letter 1 d453, letter 1 d465 equals letter 1 d465 to x2 plus 2x plus 1 technology for the following exercises. Use a calculator to graph letter 1D453, letter 1D465. Use the graph to solve letter 1D453, letter 1D4650. 70. Letter 1D453, letter 1D465 equals 2 letter 1D465 plus 171. Letter 1D453, letter 1D465 equals 42 letter 1D465 minus 372. Letter 1D453, letter 1D465 equals 2 letter 1D465 minus 1, letter 1D465 plus 2, 73. Letter 1D453, letter 1D465 equals letter 1D465 plus 2, letter 1D465 minus 1, letter 1D465 minus 4, 74. Letter 1D453, letter 1D465 equals letter 1D465 plus 3 2 letter 1D465 minus 1 2, letter 1D465 plus 1 extensions for the following exercises. Identify the removable discontinuity. 75. Letter 1D453, letter 1D465 equals letter 1D465 2 minus 4, letter 1D465 minus 276. Letter 1D453, letter 1D465 equals letter 1D465 3 plus 1 letter 1D465 plus 177. Letter 1D453, letter 1D465 equals letter 1D465 2 plus letter 1D465 minus 6 letter 1D465 minus 278. Letter 1D453, letter 1D465 equals 2 letter 1D465 2 plus 5 letter 1D465 minus 3 letter 1D465 plus 379. Letter 1D453, letter 1D465 equals letter 1D465 3 plus letter 1D465 2x plus 1 real-world applications for the following exercises. Express a rational function that describes the situation. 80. In the refugee camp hospital, a large mixing tank currently contains 200 gallons of water, into which 10 pounds of sugar have been mixed. A tap will open, pouring 10 gallons of water per minute into the tank at the same time. Sugar is poured into the tank at a rate of 3 pounds per minute. Find the concentration, pounds per gallon of sugar in the tank after t minutes. 81. In the refugee camp hospital, a large mixing tank currently contains 300 gallons of water, into which 8 pounds of sugar have been mixed. A tap will open, pouring 20 gallons of water per minute into the tank at the same time. Sugar is poured into the tank at a rate of 2 pounds per minute. Find the concentration, pounds per gallon of sugar in the tank after t minutes. For the following exercises, use the given rational function to answer the question. 82. The concentration C of a drug in a patient's bloodstream t hours after injection is given by letter 1D436, letter 1D461, equals 2 letter 1D4613 plus letter 1D4612. What happens to the concentration of the drug as t increases? 83. The concentration C of a drug in a patient's bloodstream t hours after injection is given by letter 1D436, letter 1D461, equals 100 letter 1D461 to t, 2 plus 75. Use a calculator to approximate the time when the concentration is highest. For the following exercises, construct a rational function that will help solve the problem. Then, use a calculator to answer the question. 84. An open box with a square base is to have a volume of 108 cubic inches. Find the dimensions of the box that will have minimum surface area. Let x equals length of the side of the base. 85. A rectangular box with a square base is to have a volume of 20 cubic feet. The material for the base costs 30 cents square foot. The material for the sides costs 10 cents square foot. The material for the top costs 20 cents square foot. Determine the dimensions that will yield minimum cost. Let x equals length of the side of the base. 86. A right circular cylinder has volume of 100 cubic inches. Find the radius and height that will yield minimum surface area. Let x, radius. 87. A right circular cylinder with no top has a volume of 50 cubic meters. Find the radius that will yield minimum surface area. Let x, radius. 88. A right circular cylinder is to have a volume of 40 cubic inches. It costs 4 cents square inch to construct the top and bottom and 1 cent square inch to construct the rest of the cylinder. Find the radius to yield minimum cost. Let x equals radius. Learning objectives in this section, you will find the inverse of an invertible polynomial function. Restrict the domain to find the inverse of a polynomial function. Park rangers and other trail managers may construct rock piles, stacks, or other arrangements, usually called cairns, to mark trails or other landmarks. Rangers and environmental scientists discourage hikers from doing the same in order to avoid confusion and preserve the habitats of plants and animals. A cairn in the form of a mound of gravel is in the shape of a cone with the height equal to twice the radius. Gravel in the shape of a cone. Figure 1, the volume is found using a formula from elementary geometry. Letter 1 D449 equals 13 letter 1 D70 B letter 1 D45F to letter 210 E. 13 letter 1 D70 B letter 1 D45F. 2 letter 1 D45F 23 letter 1 D70 B letter 1 D45F. 3. We have written the volume V in terms of the radius r. However, in some cases, we may start out with the volume and want to find the radius. For example, a customer purchases 100 cubic feet of gravel to construct a cone-shaped mound with a height twice the radius. What are the radius and height of the new cone? To answer this question, we use the formula. This function is the inverse of the formula for v in terms of r. In this section, we will explore the inverses of polynomial and rational functions, and in particular the radical functions we encounter in the process. Finding the inverse of a polynomial function, two functions f and g are inverse functions if for every coordinate pair in letter 1 D453, letter 1 D44E, letter 1 D44F. There exists a corresponding coordinate pair in the inverse function, letter 1 D454, letter 1 D44F, letter 1 D44E. In other words, the coordinate pairs of the inverse functions have the input and output interchanged. Only one-to-one functions have inverses. Recall that a one-to-one function has a unique output value for each input value and passes the horizontal line test. For example, suppose the Sustainability Club builds a water runoff collector in the shape of a parabolic trough, as shown in Figure 2. We can use the information in the figure to find the surface area of the water in the trough as a function of the depth of the water. Diagram of a parabolic trough that is 18 in height, 3 in length, and 12 in width. Figure 2, because it will be helpful to have an equation for the parabolic cross-sectional shape, we will impose a coordinate system at the cross-section, with x measured horizontally and y measured vertically, with the origin at the vertex of the parabola. See Figure 3. Graph of a parabola. Figure 3, from this, we find an equation for the parabolic shape. We place the origin at the vertex of the parabola, so we know the equation will have form letter 1 D466, letter 1 D465, equals letter 1 D44, letter 1 D465, 2. Our equation will need to pass through the point 6, 18, from which we can solve for the stretch factor a. 18 letter 1 D44e equals letter 1 D44e, 62,183,612. Our parabolic cross-section has the equation letter 1 D466. Letter 1 D465 equals 12 letter 1 D465, 2. We are interested in the surface area of the water. So we must determine the width at the top of the water as a function of the water depth. For any depth y, the width will be given by 2x, so we need to solve the equation above for x and find the inverse function. However, notice that the original function is not one-to-one. And indeed, given any output, there are two inputs that produce the same output, one positive and one negative. To find an inverse, we can restrict our original function to a limited domain on which it is one-to-one. In this case, it makes sense to restrict ourselves to positive x values. On this domain, we can find an inverse by solving for the input variable. White a letter 1 D466, letter 1 D465, therefore letter 1 D466 equals 12 letter 1 D465 to letter 1 D465, 2 plus, or minus 2 letter 1 D466 square plus 2 letter 1 D465 square. This is not a function as written. Since we are limiting ourselves to positive x values in the original function, we can eliminate the negative solution, which gives us the inverse function we're looking for. letter 1d466 equals 2 letter 1d465 square. Because x is the distance from the center of the parabola to either side, the entire width of the water at the top will be 2x. The trough is 3 feet, 36 inches long, so the surface area will then be area letter 1d459 letter 1d464 36 2 letter 1d465 72 letter 1d465 722 letter 1d466 square. This example illustrates two important points. When finding the inverse of a quadratic, we have to limit ourselves to a domain on which the function is 1-to-1. The inverse of a quadratic function is a square root function. Both are toolkit functions and different types of power functions. Functions involving roots are often called radical functions. While it is not possible to find an inverse of most polynomial functions, some basic polynomials do have inverses. Such functions are called invertible functions, and we use the notation letter 1d453-1, letter 1d465. Warning: letter 1d453-1, letter 1d465 is not the same as the reciprocal of the function letter 1d453, letter 1d465. This use of 1 is reserved to denote inverse functions. To denote the reciprocal of a function letter 1d453, letter 1d465, we would need to write letter 1d453, letter 1d465. Minus 1 equals 1 letter 1d453, letter 1d465. An important relationship between inverse functions is that they undo each other. If letter 1d453-1 is the inverse of a function f, then f is the inverse of the function letter 1d453-1. In other words, whatever the function f does to x, letter 1d453-1 undoes it, and vice versa. Letter 1d453-1, letter 1d453, letter 1d465 equals letter 1d465. For all letter 1d465, in the domain of f and letter 1d453, letter 1d453 minus 1 letter 1d465 equals letter 1d465. For all letter 1d465, in the domain of letter 1d453 minus 1, note that the inverse switches the domain and range of the original function. Verifying two functions are inverses of one another. Two functions, f and g, are inverses of one another if for all x in the domain of f and g. Letter 1d454, letter 1d453, letter 1d465 equals letter 1d453, letter 1d454, letter 1d465 equals letter 1d465. How to given a polynomial function, find the inverse of the function by restricting the domain in such a way that the new function is 1-to-1. Replace letter 1d453, letter 1d465 with y. Interchange x and y. Solve for y and rename the function letter 1d453-1, letter 1d465. Example 1. Verifying inverse functions show that letter 1d453, letter 1d465 equals 1 letter 1d465 plus 1, and letter 1d453 minus 1, letter 1d465 equals 1 letter 1d465 minus 1 are inverses. For letter 1d465 not equal to 0, minus 1. Solution: we must show that letter 1d453 minus 1, letter 1d453, letter 1d465 equals letter 1d465 and letter 1d453, letter 1d453 minus 1 letter 1d465 equals letter 1d465. Letter 1d453 minus 1, letter 1d453, letter 1d465. Letter 1d453, letter 1d453 minus 1, letter 1d465 equals letter 1d453 minus 1, 1 letter 1d465 plus 1 11 letter 1d465 plus 1 minus 1, letter 1d465 plus 1, minus 1 letter 1d465 letter 1d453, 1 letter 1d465 minus 1, 1 letter. Therefore, letter 1d453, letter 1d465 equals 1 letter 1d465 plus 1, and letter 1d453 minus 1, letter 1d465 equals 1 letter 1d465 minus 1 are inverses. Try it. 1. Show that letter 1d453, letter 1d465 equals letter 1d465 plus 53, and letter 1d453 minus 1, letter 1d465 equals 3 letter 1d465 minus 5 are inverses. Example 2, finding the inverse of a cubic function, find the inverse of the function letter 1d453, letter 1d465, equals 5 letter 1d465 3 plus 1. Solution: this is a transformation of the basic cubic toolkit function, and based on our knowledge of that function, we know it is 101. Solving for the inverse by solving for x. Letter 1d466, letter 1d465, letter 1d465, minus 1, letter 1d465, minus 15, letter 1d453, minus 1, letter 1d465, equals 5, letter 1d465, 3, plus 15, letter 1d466, 3, plus 15, letter 1d466, 3, letter 1d466, 3, letter 1d465, minus 15 square 3 analysis. Look at the graph of f and letter 1d4531. Notice that one graph is the reflection of the other about the line letter 1d466 equals letter 1d465. This is always the case when graphing a function and its inverse function. Also, since the method involved interchanging x and y, notice corresponding points. If AB is on the graph of f, then BA is on the graph of letter 1d4531. Since 1 is on the graph of f, then 10 is on the graph of letter 1d4531. Similarly, since 16 is on the graph of f, then 61 is on the graph of letter 1d4531. See Figure 4. Graph of f, x equals 5x3 plus 1 and its inverse, f minus 1, x equals 3 sqrt, x1/5. Figure 4, try it too. Find the inverse function of letter 1d453, letter 1d465 equals letter 1d465 plus 4 square 3. Restricting the domain to find the inverse of a polynomial function. So far, we have been able to find the inverse functions of cubic functions without having to restrict their domains. However, as we know, not all cubic polynomials are one-to-one. Some functions that are not one-to-one may have their domain restricted so that they are one-to-one, but only over that domain. The function over the restricted domain would then have an inverse function. Since quadratic functions are not one-to-one, we must restrict their domain in order to find their inverses. Restricting the domain: if a function is not one-to-one, it cannot have an inverse. If we restrict the domain of the function so that it becomes one-to-one, thus creating a new function, this new function will have an inverse. How to: given a polynomial function, restrict the domain of a function that is not one-to-one, and then find the inverse. Restrict the domain by determining a domain on which the original function is one-to-one. Replace letter 1d453, letter 1d465, with y. Interchange x and y. Solve for y, and rename the function or pair of function letter 1d453 minus 1, letter 1d465. Revise the formula for letter 1d453 minus 1, letter 1d465, by ensuring that the outputs of the inverse function correspond to the restricted domain of the original function. Example 3, restricting the domain to find the inverse of a polynomial function. Find the inverse function of f. A letter 1d453, letter 1d465 equals letter 1d465 minus 4 2. Letter 1d465 greater or equal to 4b letter 1d453, letter 1d465 equals letter 1d465 minus 4 2. Letter 1d465 less or equal to 4. Solution: the original function letter 1d453, letter 1d465 equals letter 1d465 minus 4 2 is not one-to-one, but the function is restricted to a domain of letter 1d465 greater or equal to 4 or letter 1d465 less or equal to 4 on which it is one-to-one. See Figure 5. Two graphs of f x equals x4, 2 where the first is when x greater or equal 4 and the second is when x less or equal 4. Figure 5. To find the inverse, start by replacing letter 1d453, letter 1d465 with the simple variable y. Letter 1d466, letter 1d465 plus or minus letter 1d465 square 4 plus or minus letter 1d465 square equals. Letter 1d465 minus 4 2 letter 1d466 minus 4 2 letter 1d466 minus 4 letter 1d466 int erch a ng e letter 1d465 a ndy. Take the square root, add 4 to both sides. This is not a function as written. we need to examine the restrictions on the domain of the original function to determine the inverse. Since we reversed the roles of x and y for the original letter 1d453, letter 1d465, we looked at the domain, the values x could assume. When we reversed the roles of x and y, this gave us the values y could assume. For this function, letter 1d465 greater or equal to 4. So for the inverse, we should have letter 1d466 greater or equal to 4, which is what our inverse function gives. The domain of the original function was restricted to letter 1d465 greater or equal to 4. So the outputs of the inverse need to be the same, letter 1d453, letter 1d465 greater or equal to 4, and we must use the plus case. Letter 1d453 minus 1, letter 1d465, equals 4 plus letter 1d465 square b. The domain of the original function was restricted to letter 1d465 less or equal to 4. So the outputs of the inverse need to be the same, letter 1d453, letter 1d465, less or equal to 4, and we must use the case. Letter 1d453 minus 1, letter 1d465, equals 4 minus letter 1d465 square. Analysis on the graphs in Figure 6. We see the original function graphed on the same set of axes as its inverse function. Notice that together the graphs show symmetry about the line letter 1d466 equals letter 1d465. The coordinate pair 4, 0 is on the graph of f, and the coordinate pair 0, 4 is on the graph of letter 1d453 minus 1. For any coordinate pair, if AB is on the graph of f, then BA is on the graph of letter 1d453 minus 1. Finally, observe that the graph of f intersects the graph of letter 1d453 minus 1 on the line letter 1d466 equals letter 1d465. Points of intersection for the graphs of f and letter 1d453 minus 1 will always lie on the line letter 1d466 equals letter 1d465. Two graphs of a parabolic function with half of its inverse. Figure 6 example 4, finding the inverse of a quadratic function. When the restriction is not specified, restrict the domain, and then find the inverse of letter 1d453, letter 1d465 equals letter 1d465 minus 2, 2 minus 3. Solution: we can see this is a parabola with vertex at 2, 3, that opens upward. Because the graph will be decreasing on one side of the vertex and increasing on the other side, we can restrict this function to a domain on which it will be 1-to-1 by limiting the domain to letter 1d465 greater or equal to 2. To find the inverse, we will use the vertex form of the quadratic. We start by replacing letter 1d453, letter 1d465 with a simple variable, y, then solve for x. Letter 1d466, letter 1d465, letter 1d465, plus 3 plus or minus letter 1d465, plus 3 square 2 plus or minus letter 1d465, plus 3 square letter 1d453 minus 1, letter 1d465, equals. Letter 1d465 minus 2, 2 minus 3, letter 1d466, minus 2, 2 minus 3. Letter 1d466 minus 2, 2, letter 1d466, minus 2, letter 1d. Letter 1d465, a n dy. Add 3 to both sides, take the square root, add 2 to both sides, rename the function. Now we need to determine which case to use. Because we restricted our original function to a domain of letter 1d465 greater or equal to 2, the outputs of the inverse should be the same. Telling us to utilize the plus case, letter 1d453 minus 1, letter 1d465, equals 2 plus letter 1d465 plus 3 square if the quadratic had not been given in vertex form. Rewriting it into vertex form would be the first step. This way, we may easily observe the coordinates of the vertex to help us restrict the domain. Analysis: notice that we arbitrarily decided to restrict the domain on letter 1d465 greater or equal to 2. We could just have easily opted to restrict the domain on letter 1d465 less or equal to 2, in which case letter 1d453 minus 1, letter 1d465, equals 2 minus letter 1d465 plus 3 square. Observe the original function graphed on the same set of axes as its inverse function in Figure 7. Notice that both graphs show symmetry about the line letter 1d466 equals letter 1d465. The coordinate pair, 2, minus 3, is on the graph of f, and the coordinate pair, minus 3, 2, is on the graph of letter 1d453 minus 1. Observe from the graph of both functions on the same set of axes that domain of letter 1d453 equals range of letter 1d453, 1 equals 2, infinity, and domain of letter 1d453, 1 equals range of letter 1d453 equals 3, infinity. Finally, observe that the graph of f intersects the graph of letter 1d453 minus 1 along the line letter 1d466 equals letter 1d465, graph of a parabolic function with half of its inverse. Figure 7 try it 3 find the inverse of the function letter 1d453, letter 1d465 equals letter 1d465 2 plus 1 on the domain letter 1d465 greater or equal to 0. Solving applications of radical functions, notice that the functions from previous examples were all polynomials, and their inverses were radical functions. If we want to find the inverse of a radical function, we will need to restrict the domain of the answer, because the range of the original function is limited. How to given a radical function, find the inverse. Determine the range of the original function. Replace letter 1d453, letter 1d465 with y, then solve for x. If necessary, restrict the domain of the inverse function to the range of the original function. Example 5, finding the inverse of a radical function, restrict the domain of the function letter 1d453, letter 1d465, equals letter 1d465 minus 4 square, and then find the inverse. Solution: note that the original function has range letter 1d453, letter 1d465 greater or equal to 0. Replace letter 1d453, letter 1d465 with y, then solve for x. Letter 1d466, letter 1d465, letter 1d465, letter 1d465 to letter 1d465 2, plus 4 letter 1d453 minus 1. Letter 1d465 equals, letter 1d465 minus 4 square letter 1d466, minus 4 square letter 1d466, minus 4 square letter 1d466, minus 4 letter 1d466, letter 1d465 2, plus 4 replace. Letter 1d453, letter 1d465, with y. Interchange letter 1d465 at n dy square each side. Add 4. Rename the function letter 1d453 minus 1, letter 1d465. Recall that the domain of this function must be limited to the range of the original function. Letter 1d453 minus 1, letter 1d465, equals letter 1d465 2 plus 4. Letter 1d465 greater or equal to 0 analysis. Notice in Figure 8 that the inverse is a reflection of the original function over the line letter 1d466 equals letter 1d465. Because the original function has only positive outputs, the inverse function has only positive inputs. Graph of f, x equals sqrt, x4, and its inverse, f minus 1, x equals x2 plus 4. Figure 8 try it 4 restrict the domain, and then find the inverse of the function letter 1d453, letter 1d465, equals 2 letter 1d465 plus 3 square. Solving applications of radical functions are common in physical models, as we saw in the section opener. We now have enough tools to be able to solve the problem posed at the start of the section. Example 6, solving an application with a cubic function park, rangers. Construct a mound of gravel in the shape of a cone with the height equal to twice the radius. The volume of the cone in terms of the radius is given by letter 1d449 equals 23 letter 1d70b letter 1d45f 3. Find the inverse of the function letter 1d449 equals 23 letter 1d70b letter 1d45f 3 that determines the volume v of a cone and is a function of the radius r. Then use the inverse function to calculate the radius of such a mound of gravel measuring 100 cubic feet. Use letter 1d70b equals 3. 14. Solution: start with the given function for v. Notice that the meaningful domain for the function is letter 1d45f0, since negative radii would not make sense in this context, nor would a radius of 0. Also note the range of the function. Hence, the domain of the inverse function, is letter 1D4490. Solve for r in terms of v using the method outlined previously. Note that in real-world applications, we do not swap the variables when finding inverses. Instead, we change which variable is considered to be the independent variable. Letter 1D449, letter 1D45F, 3, letter 1D45F equals 23, letter 1D70B, letter 1D45F, 33, letter 1D449 to letter 1D70B, 3, letter 1D449 to letter 1D70B, square 3 solve for R3. Solve for R. This is the result stated in the section opener. Now evaluate this for letter 1D449 equals 100 and letter 1D70B equals 3. 14. Letter 1D45F equals approximately 3, letter 1D449 to letter 1D70B, square 30, 3, 1023. 14 square 347. 7,707 square 33. 63. Therefore, the radius is about 363 ft. Determining the domain of a radical function composed with other functions when radical functions are composed with other functions. Determining domain can become more complicated. Example 7, finding the domain of a radical function composed with a rational function. Find the domain of the function letter 1D453. Letter 1D465 equals letter 1D465 plus 2, letter 1D465 minus 3, letter 1D465 minus 1 square. Finding inverses of rational functions. As with finding inverses of quadratic functions, it is sometimes desirable to find the inverse of a rational function, particularly of rational functions that are the ratio of linear functions, such as in concentration applications. Example 8, finding the inverse of a rational function. The function letter 1D436 equals 20 plus 0. For n 100 plus n represents the concentration C of an acid solution after n ml of 40% solution has been added to 100 ml of a 20% solution. First, find the inverse of the function. That is, find an expression for n in terms of C, then use your result to determine how much of the 40% solution should be added, so that the final mixture is a 35% solution. Solution, we first want the inverse of the function in order to determine how many ml we need for a given concentration. We will solve for n in terms of C. Letter 1D436, letter 1D436. 100 plus letter 1D45B, 100 letter 1D436, plus letter 1D436, letter 1D45B, 100 letter 1D436, minus 20,100 letter 1D436, minus 20 letter 1D45B equals 20 plus 0. 4n100 plus n20 plus 0, 4n20 plus 0, 4n0. 4 letter 1D45B minus letter 1D436 letter 1D45B, 0. 4 minus letter 1D436, letter 1D45B, 100 letter 1D436, minus 200. 4 minus letter 1D436, now evaluate this function at 35%, which is letter 1D436 equals 0. 35. Letter 1D45B equals 100, 0. 35 minus 200, 4 minus 0, 35,150. 5,300, we can conclude that 300 ml of the 40% solution should be added. Try at 5, find the inverse of the function letter 1D453. Letter 1D465 equals letter 1D465 plus 3 letter 1D465 minus 2. Media access, these online resources for additional instruction and practice with inverses and radical functions. Graphing the basic square root function, find the inverse of a square root function, find the inverse of a rational function, find the inverse of a rational function, and an inverse function, value inverse functions 5. 7 section, exercises verbal 1. Explain why we cannot find inverse functions for all polynomial functions. 2. Why must we restrict the domain of a quadratic function when finding its inverse? 3. When finding the inverse of a radical function, what restriction will we need to make? 4. The inverse of a quadratic function will always take what form? Algebraic for the following exercises, find the inverse of the function on the given domain. 5. Letter 1d453, letter 1d465 equals letter 1d465 minus 4, 2, 4 infinity 6. Letter 1d453, letter 1d465 equals letter 1d465 plus 2, 2, minus 2 infinity 7. Letter 1d453, letter 1d465 equals letter 1d465 plus 1, 2 minus 3, minus 1 infinity 8. Letter 1d453, letter 1d465 equals 3 letter 1d465 2 plus 5, infinity 0, 9. Letter 1d453, letter 1d465 equals 12 minus letter 1d465 2, 0 infinity 10. Letter 1d453, letter 1d465 equals 9 minus letter 1d465 2, 0 infinity 11. Letter 1d453, letter 1d465 equals 2 letter 1d465 2 plus 4, 0, infinity. For the following exercises, find the inverse of the functions. 12. Letter 1d453, letter 1d465 equals letter 1d465 3 plus 5, 13. Letter 1d453, letter 1d465 equals 3 letter 1d465 3 plus 1, 14. Letter 1d453, letter 1d465 equals 4 minus letter 1d465 3, 15. Letter 1d453, letter 1d465 equals 4 minus 2 letter 1d465 3. For the following exercises, find the inverse of the functions. 16. Letter 1d453, letter 1d465 equals 2 letter 1d465 plus 1 square 17. Letter 1d453, letter 1d465 equals 3 minus 4 letter 1d465 square 18, plus 4 letter 1d465 minus 4 square 19. Letter 1d453, letter 1d465 equals 6 letter 1d465 minus 8 square plus 520, plus 2 letter 1d465 square 321. Letter 1d453, letter 1d465 equals 3 minus letter 1d465 square 322. Letter 1d453, letter 1d465 equals 2 letter 1d465 plus 823. Letter 1d453, letter 1d465 equals 3 letter 1d465 minus 424. Letter 1d453, letter 1d465 equals letter 1d465 plus 3 letter 1d465 plus 725. Letter 1d453, letter 1d465 equals letter 1d465 minus 2 letter 1d465 plus 726. Letter 1d453, letter 1d465 equals 3 letter 1d465 plus 45 minus 4 letter 1d465 27. Letter 1d453, letter 1d465 equals 5 letter 1d465 plus 12 minus 5 letter 1d465 28. Letter 1d453, letter 1d465 equals letter 1d465 2 plus 2 letter 1d465 minus 1 infinity 29. Letter 1d453, letter 1d465 equals letter 1d465 2 plus 4 letter 1d465 plus 1 minus 2 infinity 30. Letter 1d453, letter 1d465 equals letter 1d465 2 minus 6 letter 1d465 plus 3, 3 infinity. Graphical. For the following exercises, find the inverse of the function and graph both the function and its inverse. 31. Letter 1d453, letter 1d465 equals letter 1d465 2 plus 2, letter 1d465 greater or equal to 0, 32. Letter 1d453, letter 1d465 equals 4 minus letter 1d465 2, letter 1d465 greater or equal to 0, 33. Letter 1d453, letter 1d465 equals letter 1d465 plus 3 2 letter 1d465 greater minus 3, 34. Letter 1d453, letter 1d465 equals letter 1d465 minus 4 2 letter 1d465 greater or equal to 4, 35. Letter 1d453, letter 1d465 equals letter 1d465 3 plus 3, 36. Letter 1d453, letter 1d465 equals 1 minus letter 1d465 3, 37. Letter 1d453, letter 1d465 equals letter 1 d465 2 plus 4 letter 1 d465. Letter 1 d465 greater minus 238. Letter 1 d453. Letter 1 d465 equals letter 1 d465 2 minus 6 letter 1 d465 plus 1 letter 1 d465 greater or equal to 339. Letter 1 d453 letter 1 d465 equals 2 letter 1 d465 40. Letter 1 d453 letter 1 d465 equals 1 letter 1 d465 2 letter 1 d465 greater or equal to 0 for the following exercises. Use a graph to help determine the domain of the functions. 41. Letter 1 d453 letter 1 d465 equals letter 1 d465 plus 1 letter 1 d465 minus 1 letter 1 d465 square 42. Letter 1 d453 letter 1 d465 equals letter 1 d465 plus 2 letter 1 d465 minus 3 letter 1 d465 minus 1 square 43. Letter 1 d453 letter 1 d465 equals letter 1 d465 letter 1 d465 plus 3 letter 1 d465 minus 4 square 44. Letter 1 d453 letter 1 d465 equals letter 1 d465 2 minus letter 1 d465 minus 20 letter 1 d465 minus 2 square 45. Letter 1 d453 letter 1 d465 equals 9 minus letter 1 d465 to letter 1 d465 plus 4 square technology for the following exercises. Use a calculator to graph the function. Then, using the graph, give 3 points on the graph of the inverse with y-coordinates given. 46. Letter 1 d453, letter 1 d465 equals letter 1 d465 3 minus letter 1 d465 minus 2 letter 1 d466 equals 1, 2, 347. Letter 1 d453, letter 1 d465 equals letter 1 d465 3 plus letter 1 d465 minus 2. Letter 1 d466 equals 0, 1, 248. Letter 1 d453, letter 1 d465 equals letter 1 d465 3 plus 3 letter 1 d465 minus 4. Letter 1 d466 equals 0, 1, 249. Letter 1 d453, letter 1 d465 equals letter 1 d465 3 plus 8 letter 1 d465 minus 4. Letter 1 d466 equals minus 1, 0, 150. Letter 1 d453, letter 1 d465 equals letter 1 d465 4 plus 5 letter 1 d465 plus 1. Letter 1 d466 equals minus 1, 0, 1 extensions for the following exercises. Find the inverse of the functions with a, b, c positive real numbers. 51. Letter 1 d453. Letter 1 d465 equals letter 1 d44 letter 1 d465 3 plus letter 1 d44f 52. Letter 1 d453. Letter 1 d465 equals letter 1 d465 2 plus letter 1 d44f letter 1 d465 53. Letter 1 d453. Letter 1 d465 equals letter 1 d44 letter 1 d465 2 minus letter 1 d44f square 54. Letter 1 d453. Letter 1 d465 equals letter 1 d44 letter 1 d465 plus letter 1 d44f square 355. Letter 1 d453. Letter 1 d465 equals letter 1 d44 letter 1 d465 plus letter 1 d44f letter 1 d465 plus letter 1 d450. Real-world applications for the following exercises. Determine the function described, and then use it to answer the question. 56. An object dropped from a height of 200 meters has a height, letter 210e, letter 1d461, in meters after t seconds have lapsed, such that letter 210e, letter 1d461, equals 200 minus 4. 9t2. Express t as a function of height, h, and find the time to reach a height of 50 meters. 57. An object dropped from a height of 600 feet has a height, letter 210e, letter 1d461, in feet after t seconds have elapsed, such that express t as a function of height h, and find the time to reach a height of 400 feet. 58. The volume, v, of a sphere in terms of its radius, r, is given by letter 1d449, letter 1d45f equals 43 letter 1d70b letter 1d45f3. Express r as a function of v and find the radius of a sphere with volume of 200 cubic feet. 59. The surface area, A, of a sphere in terms of its radius, r, is given by letter 1d434. Letter 1d45f equals 4 letter 1d70b letter 1d45f2. Express r as a function of A and find the radius of a sphere with a surface area of 1,000 square inches. 60. A container holds 100 ml of a solution that is 25 ml acid. If n ml of a solution that is 60% acid is added, the function letter 1d436, letter 1d45b, equals 25 plus 6n 100 plus n gives the concentration, C, as a function of the number of ml added, n. Express n as a function of C and determine the number of ml that need to be added to have a solution that is 50% acid. 61. The period t, in seconds, of a simple pendulum as a function of its length L, in feet, is given by letter 1d447, letter 1d459, equals 2 letter 1d70b letter 1d459, 32. 2 square. Express L as a function of t and determine the length of a pendulum with period of 2 seconds. 62. The volume of a cylinder, V, in terms of radius, r, and height, h, is given by letter 1d449 equals letter 1d70b letter 1d45f2h. If a cylinder has a height of 6 meters, express the radius as a function of v and find the radius of a cylinder with volume of 300 cubic meters. 63. The surface area, A, of a cylinder in terms of its radius, r, and height, h, is given by letter 1d434 equals 2 letter 1d70b letter 1d45f, 2, plus 2 letter 1d70b letter 1d45f letter 210e. If the height of the cylinder is 4 feet, express the radius as a function of A and find the radius if the surface area is 200 square feet. 64. The volume of a right circular cone, V, in terms of its radius, r, and its height, h, is given by letter 1d449 equals 13 letter 1d70b letter 1d45f2h. Express r in terms of v if the height of the cone is 12 feet and find the radius of a cone with volume of 50 cubic inches. 65. Consider a cone with height of 30 feet. Express the radius, r, in terms of the volume, v, and find the radius of a cone with volume of 1,000 cubic feet. Learning objectives in this section, you will solve direct variation problems, solve inverse variation problems, solve problems involving joint variation. A pre-owned car dealer has just offered their best candidate, Nicole, a position in sales. The position offers 16% commission on her sales. Her earnings depend on the amount of her sales. For instance, if she sells a vehicle for $4,600, she will earn $736. As she considers the offer, she takes into account the typical price of the dealer's cars, the overall market, and how many she can reasonably expect to sell. In this section, we will look at relationships, such as this one, between earnings, sales, and commission rate. Solving direct variation problems in the example above, Nicole's earnings can be found by multiplying her sales by her commission. The formula letter 1d452 equals 0. 16s tells us her earnings. E come from the product of 0, 16, her commission, and the sale price of the vehicle. If we create a table, we observe that as the sales price increases, the earnings increase as well, which should be intuitive. See Table 1. S, sales price letter 1d452 equals 0. 16's interpretation $4,600 letter 1d452 equals 0. 16, 4, 600 equals 736. A sale of a $4,600 vehicle results in $736 earnings. $9,200 letter 1d452 equals 0. 16, 9, 200 equals 1,472. A sale of a $9,200 vehicle results in $1,472 earnings. $18,400 letter 1d452 equals 0. 16, 18, 400 equals 2,944. A sale of a $18,400 vehicle results in $2,944 earnings. Table 1. Notice that earnings are a multiple of sales. As sales increase, earnings increase in a predictable way. Double the sales of the vehicle from $4,600 to $9,200, and we double the earnings from $736 to $1,472. As the input increases, the output increases as a multiple of the input. A relationship in which one quantity is a constant multiplied by another quantity is called direct variation. Each variable in this type of relationship varies directly with the other. Figure 1 represents the data for Nicole's potential earnings. We say that earnings vary directly with the sales price of the car. The formula letter 1D466 equals letter 1D458 letter 1D465 letter 1D45B is used for direct variation. The value k is a non-zero constant greater than 0 and is called the constant of variation. In this case, letter 1D458 equals 0, 16, and letter 1D45B equals 1. We saw functions like this one when we discussed power functions. Graph of y equals 0, 16x, where the horizontal axis is labeled S, sales price in dollars, and the vertical axis is labeled E, earnings. Figure 1 direct variation if letter 1D465 and letter 1D466 are related by an equation of the form letter 1D466 equals letter 1D458 letter 1D465 letter 1D45B. Then we say that the relationship is direct variation, and y varies directly with, or is proportional to, the nth power of x. In direct variation relationships, there is a non-zero constant ratio letter 1D458 equals letter 1D466 letter 1D465 letter 1D45B, where k is called the constant of variation, which defines the relationship between the variables. How to give a description of a direct variation problem, solve for an unknown. Identify the input, x, and the output, y. Determine the constant of variation. You may need to divide y by the specified power of x to determine the constant of variation. Use the constant of variation to write an equation for the relationship. Substitute known values into the equation to find the unknown. Example 1, solving a direct variation problem. The quantity y varies directly with the cube of x. If letter 1D466 equals 25 when letter 1D465 equals 2, find y when x is 6. Solution: the general formula for direct variation with a cube is letter 1D466 equals letter 1D458 letter 1D465 3. The constant can be found by dividing y by the cube of x. Letter 1D458 equals letter 1D466 letter 1D465 32,523,258. Now use the constant to write an equation that represents this relationship. Letter 1D466 equals 258 letter 1D465 3. Substitute letter 1D465 equals 6 and solve for y. Letter 1D466 equals 258, 6, 3,675. Analysis: the graph of this equation is a simple cubic, as shown in figure 2. Graph of y equals 25/8, x3, with the labeled points 2, 25, and 6, 675. Figure 2Q and A. Do the graphs of all direct variation equations look like example 1? No, direct variation equations are power functions. They may be linear, quadratic, cubic, quartic, radical, etc. But all of the graphs pass through 0. Try it 1. The quantity y varies directly with the square of x if letter 1D466 equals 24 when. Find y when x is 4. Solving inverse variation problems: water temperature in an ocean varies inversely to the water's depth. The formula letter 1D447 equals 14, 000 letter 1D451 gives us the temperature in degrees Fahrenheit at a depth in feet below Earth's surface. Consider the Atlantic Ocean, which covers 22% of Earth's surface. At a certain location, at the depth of 500 feet, the temperature may be 28 degrees F. If we create Table 2, we observe that, as the depth increases, the water temperature decreases. D. Depth letter 1D447 equals 14, 000 letter 1D451 interpretation 500 FT14 000500 equals 28 at a depth of 500 FT. The water temperature is 28 degrees F. 1000 FT14 000100 equals 14 at a depth of 1000 FT. The water temperature is 14 degrees F. 2000 FT14 000200 equals 7 at a depth of 2000 FT. The water temperature is 7 degrees F. Table 2, we notice in the relationship between these variables that as one quantity increases, the other decreases. The two quantities are said to be inversely proportional, and each term varies inversely with the other. Inversely proportional relationships are also called inverse variations. For our example, Figure 3 depicts the inverse variation. We say the water temperature varies inversely with the depth of the water because, as the depth increases, the temperature decreases. The formula for inverse variation in this case uses letter 1D458 equals 14, 000. Graph of y equals 14,000/x, where the horizontal axis is labeled depth d ft, and the vertical axis is labeled temperature T degrees Fahrenheit. Figure 3 inverse variation. If x and y are related by an equation of the form letter 1D466 equals letter 1D458 letter 1D465 letter 1D45b, where k is a non-zero constant, then we say that y varies inversely with the nth power of x. In inversely proportional relationships, or inverse variations, there is a constant multiple letter 1D458 equals letter 1D465 letter 1D45b letter 1D466. Example 2, writing a formula for an inversely proportional relationship. A tourist plans to drive 100 miles. Find a formula for the time the trip will take as a function of the speed the tourist drives. Solution: recall that multiplying speed by time gives distance. If we let t represent the drive time in hours, and v represent the velocity, speed, or rate at which the tourist drives, then letter 1D463 letter 1D461 equals distance. Because the distance is fixed at 100 miles, letter 1D463 letter 1D461 equals 100. So, because time is a function of velocity, we can write letter 1D461, letter 1D463, letter 1D461, letter 1D463 equals 100 letter 1D463, 100 letter 1D463, minus 1. We can see that the constant of variation is 100, and although we can write the relationship using the negative exponent, it is more common to see it written as a fraction. We say that time varies inversely with velocity. How to, given a description of an indirect variation problem, solve for an unknown. Identify the input, x, and the output, y. Determine the constant of variation. You may need to multiply y by the specified power of x to determine the constant of variation. Use the constant of variation to write an equation for the relationship. Substitute known values into the equation to find the unknown. Example 3, solving an inverse variation problem. A quantity y varies inversely with the cube of x. If letter 1D466 equals 25 when letter 1D465 equals 2, find y when x is 6. Solution: the general formula for inverse variation with a cube is letter 1D466 equals letter 1D458 letter 1D465 3. The constant can be found by multiplying y by the cube of x. Letter 1D458 equals letter 1D465 3 letter 1D466 25,200. Now, we use the constant to write an equation that represents this relationship. Letter 1D466 letter 1D466 equals letter 1D458 letter 1D465 3 letter 1D458 equals 200,200 letter 1D465 3. Substitute letter 1D465 equals 6 and solve for y. Letter 1D466 equals 200,632,527. Analysis: the graph of this equation is a rational function, as shown in Figure 4. Graph of y equals 25/x3 with the labeled points 2, 25, and 6, 25, 27. Figure 4. Try it 2. A quantity y varies inversely with the square of x. If letter 1D466 equals 8 when Find y when x is 4. Solving problems involving joint variation, many situations are more complicated than a basic direct variation or inverse variation model. One variable often depends on multiple other variables. When a variable is dependent on the product or quotient of two or more variables, this is called joint variation. For example, the cost of busing students for each school trip varies with the number of students attending and the distance from the school. The variable c, cost, varies jointly with the number of students, n, and the distance, d. Joint variation occurs when a variable varies directly or inversely with multiple variables. For instance, if x varies directly with both y and z, we have letter 1 d465 equals letter 1 d458, letter 1 d466, letter 1 d467. If x varies directly with y and inversely with z, we have letter 1 d465 equals letter 1 d458, letter 1 d466, letter 1 d467. Notice that we only use one constant in a joint variation equation. Example: for solving problems involving joint variation, a quantity x varies directly with the square of y and inversely with the cube root of z. If letter 1 d465 equals 6, when letter 1 d466 equals 2, and letter 1 d467 equals 8, find x when letter 1 d466 equals 1 and letter 1 d467 equals 27. Solution: begin by writing an equation to show the relationship between the variables. Letter 1 d465 equals letter 1 d458, letter 1 d466 to letter 1 d467 square. Root 3, substitute letter 1 d465 equals 6, letter 1 d466 equals 2, and letter 1 d467 equals 8 to find the value of the constant k. Now we can substitute the value of the constant into the equation for the relationship. Letter 1 d465 equals 3 letter 1 d466 to letter 1 d467 square root 3 to find x when letter 1 d466 equals 1 and letter 1 d467 equals 27. We will substitute values for y and z into our equation. Letter 1 d465 equals 3 1 227 square root 31 try it 3. A quantity x varies directly with the square of y and inversely with z. If letter 1 d465 equals 40 when letter 1 d466 equals 4 and letter 1 d467 equals 2, find x when letter 1 d466 equals 10 and letter 1 d467 equals 25. Media access: these online resources for additional instruction and practice with direct and inverse variation. Direct variation, inverse variation, direct and inverse variation 5. 8-section exercises verbal 1. What is true of the appearance of graphs that reflect a direct variation between two variables? 2. If two variables vary inversely, what will an equation representing their relationship look like? 3. Is there a limit to the number of variables that can vary jointly? Explain. Algebraic: for the following exercises, write an equation describing the relationship of the given variables. 4. Y varies directly as x, and when letter 1 d465 equals 6, letter 1 d466 equals 12. 5. Y varies directly as the square of x, and when letter 1 d465 equals 4, letter 1 d466 equals 80. 6. Y varies directly as the square root of x, and when letter 1 d465 equals 36, letter 1 d466 equals 24. 7. Y varies directly as the cube of x, and when letter 1 d465 equals 36, letter 1 d466 equals 24. 8. Y varies directly as the cube root of x, and when letter 1 d465 equals 27, letter 1 d466 equals 15. 9. Y varies directly as the fourth power of x, and when letter 1 d465 equals 1, letter 1 d466 equals 6. 10. Y varies inversely as x, and when letter 1 d465 equals 4, letter 1 d466 equals 2. 11. Y varies inversely as the square of x, and when letter 1 d465 equals 3, letter 1 d466 equals 2. 12. Y varies inversely as the cube of x, and when letter 1 d465 equals 2, letter 1 d466 equals 5. 13. Y varies inversely as the fourth power of x, and when letter 1 d465 equals 3, letter 1 d466 equals 1. 14. y varies inversely as the square root of x, and when letter 1d465 equals 25, letter 1d466 equals 3. 15. Y varies inversely as the cube root of x, and when letter 1d465 equals 64, letter 1d466 equals 5. 16. Y varies jointly with x and z, and when letter 1d465 equals 2, and letter 1d467 equals 3, letter 1d466 equals 36. 17. Y varies jointly as xz and w, and when letter 1d465 equals 1, letter 1d467 equals 2, letter 1d464 equals 5, then letter 1d466 equals 100. 18. Y varies jointly as the square of x and the square of z, and when letter 1d465 equals 3 and letter 1d467 equals 4, then letter 1d466 equals 72. 19. Y varies jointly as x and the square root of z, and when letter 1d465 equals 2 and letter 1d467 equals 25, then letter 1d466 equals 100. 20. Y varies jointly as the square of x the cube of z and the square root of w. When letter 1d465 equals 1, letter 1d467 equals 2, and letter 1d464 equals 36, then letter 1d466 equals 48. 21. Y varies jointly as x and z, and inversely as w when letter 1d465 equals 3, letter 1d467 equals 5, and letter 1d464 equals 6, then letter 1d466 equals 10. 22. Y varies jointly as the square of x and the square root of z, and inversely as the cube of w. When letter 1d465 equals 3, letter 1d467 equals 4, and letter 1d464 equals 3, then letter 1d466 equals 6. 23. Y varies jointly as x and z, and inversely as the square root of w and the square of t. When letter 1d465 equals 3, letter 1d467 equals 1, letter 1d464 equals 25, and letter 1d461 equals 2, then letter 1d466 equals 6. Numeric for the following exercises, use the given information to find the unknown value. 24. Y varies directly as x. When, then letter 1d466 equals 12. Find y w letter 1d465 equals 20. 25. Y varies directly as the square of x when letter 1d465 equals 2. Then letter 1d466 equals 16. Find y when letter 1d465 equals 8. 26. Y varies directly as the cube of x. When, then letter 1d466 equals 5. Find y when letter 1d465 equals 4. 27. Y varies directly as the square root of x when letter 1d465 equals 16. Then letter 1d466 equals 4. Find y when letter 1d465 equals 36. 28. Y varies directly as the cube root of x. When letter 1d465 equals 125, then letter 1d466 equals 15. Find y when letter 1d465 equals 1, 0, 0, 0. 29. Y varies inversely with x when, then letter 1d466 equals 2. Find y when letter 1d465 equals 1. 30. Y varies inversely with the square of x. When letter 1d465 equals 4, then letter 1d466 equals 3. Find y when letter 1d465 equals 2. 31. Y varies inversely with the cube of x when, then letter 1d466 equals 1. Find y when letter 1d465 equals 1. 32. Y varies inversely with the square root of x. When letter 1d465 equals 64, then letter 1d466 equals 12. Find y when letter 1d465 equals 36. 33. Y varies inversely with the cube root of x when letter 1d465 equals 27, then letter 1d466 equals 5. Find y when letter 1d465 equals 125. 34. Y varies jointly as letter 1d465 at nd letter 1d467. When letter 1d465 equals 4 and letter 1d467 equals 2, then letter 1d466 equals 16. Find y when letter 1d465 equals 3 and letter 1d467 equals 3. 35. Y varies jointly as letter 1d465, letter 1d467 a, n d letter 1d464. When letter 1d465 equals 2, letter 1d467 equals 1, and letter 1d464 equals 12, then letter 1d466 equals 72. Find y when letter 1d465 equals 1, letter 1d467 equals 2, and letter 1d464 equals 3. 36. Y varies jointly as x and the square of z when letter 1d465 equals 2 and letter 1d467 equals 4. Then letter 1d466 equals 144. Find y when letter 1d465 equals 4 and letter 1d467 equals 5. 37. Y varies jointly as the square of x and the square root of z. When letter 1d465 equals 2 and letter 1d467 equals 9, then letter 1d466 equals 24. Find y when letter 1d465 equals 3 and letter 1d467 equals 25. 38. Y varies jointly as x and z and inversely as w when letter 1d465 equals 5, letter 1d467 equals 2, and letter 1d464 equals 20, then letter 1d466 equals 4. Find y when letter 1d465 equals 3 and letter 1d467 equals 8, and letter 1d464 equals 48. 39. Y varies jointly as the square of x and the cube of z, and inversely as the square root of w. When letter 1d465 equals 2, letter 1d467 equals 2, and letter 1d464 equals 64, then letter 1d466 equals 12. Find y when letter 1d465 equals 1, letter 1d467 equals 3, and letter 1d464 equals 4. 40. Y varies jointly as the square of x and of z, and inversely as the square root of w and of t. When letter 1d465 equals 2, letter 1d467 equals 3, letter 1d464 equals 16, and letter 1d461 equals 3, then letter 1d466 equals 1. Find y when letter 1d467 equals 2, letter 1d464 equals 36, and letter 1d461 equals 5. Technology for the following exercises. Use a calculator to graph the equation implied by the given variation. 41. Y varies directly with the square of x, and when letter 1d465 equals 2, letter 1d466 equals 3. 42. Y varies directly as the cube of x, and when letter 1d465 equals 2, letter 1d466 equals 4. 43. Y varies directly as the square root of x, and when letter 1d465 equals 36, letter 1d466 equals 2. 44. Y varies inversely with x, and when letter 1d465 equals 6, letter 1d466 equals 2. 45. Y varies inversely as the square of x, and when letter 1d465 equals 1, letter 1d466 equals 4. Extensions for the following exercises. Use Kepler's law, which states that the square of the time, t, required for a planet to orbit the sun varies directly with the cube of the mean distance. A. That the planet is from the sun. 46. Using Earth's time of 1 year and mean distance of 93 million miles, find the equation relating t and A. 47. Use the result from the previous exercise to determine the time required for Mars to orbit the sun if its mean distance is 142 million miles. 48. Using Earth's distance of 150 million kilometers, find the equation relating t and A. 49. Use the result from the previous exercise to determine the time required for Venus to orbit the sun if its mean distance is 108 million kilometers. 50. Using Earth's distance of 1 astronomical unit, AU, determine the time for Saturn to orbit the sun if its mean distance is 9. 54 AU. Real-world applications for the following exercises. Use the given information to answer the questions. 51. The distance s that an object falls varies directly with the square of the time, t, of the fall. If an object falls 16 feet in 1 second, how long for it to fall 144 feet? 52. The velocity v of a falling object varies directly to the time, t, of the fall. If after 2 seconds, the velocity of the object is 64 feet per second, what is the velocity after 5 seconds? 53. The rate of vibration of a string under constant tension varies inversely with the length of the string. If a string is 24 inches long and vibrates 128 times per second, what is the length of a string that vibrates 64 times per second? 54. The volume of a gas held at constant temperature varies indirectly as the pressure of the gas. If the volume of a gas is 1200 cubic centimeters when the pressure is 200 millimeters of mercury, what is the volume when the pressure is 300 millimeters of mercury? 55. The weight of an object above the surface of Earth varies inversely with the square of the distance from the center of Earth. If a body weighs 50 pounds when it is 3960 miles from Earth's center, what would it weigh at 3970 miles from Earth's center? 56. The intensity of light measured in foot candles varies inversely with the square of the distance from the light source. Suppose the intensity of a light bulb is 0. 8-foot candles at a distance of 3 meters. Find the intensity level at 8 meters. 57. The current in a circuit varies inversely with its resistance measured in ohms. When the current in a circuit is 40 amperes, the resistance is 10 ohms. Find the current if the resistance is 12 ohms. 58. The force exerted by the wind on a plane surface varies jointly with the square of the velocity of the wind and with the area of the plane surface. If the area of the surface is 40 square feet surface and the wind velocity is 20 miles per hour, the resulting force is 15 pounds. Find the force on a surface of 65 square feet with a velocity of 30 miles per hour. 59. The horsepower, HP, that a shaft can safely transmit varies jointly with its speed, in revolutions per minute (RPM) and the cube of the diameter. If the shaft of a certain material 3 inches in diameter can transmit 45 HP at 100 RPM, what must the diameter be in order to transmit 60 HP at 150 RPM? 60. The kinetic energy K of a moving object varies jointly with its mass m and the square of its velocity v. If an object weighing 40 kilograms with a velocity of 15 meters per second has a kinetic energy of 1,000 joules, find the kinetic energy if the velocity is increased to 20 meters per second.